Good morning, everyone.
Good morning, sir.
Good morning, Ramesh sir.
Good morning, Gansilan. How are you?
Fine. How are you?
So I request you. I'll have to leave at 12:30. Later on, you manage, please.
Fine. Okay, no problem.
And one of the oral presentations are not there, so we will have more time.
Correct. Yeah. We'll have more time.
So we'll ask 20 minutes for lead speak and invited, and rest we'll give 10 to 12 for others.
Fine.
Then there will be ample time for discussion also.
Right. Okay.
Good.
Okay.
Hello, Somesh.
Hi, Ramesh, how are you?
Good morning, Professor Somesh.
Yeah, good morning. How are you?
नमस्कार सर. नमस्कार.
नमस्कार यार पटनायक, क्या हाल है?
नमस्कार सर, कैसे हैं साहब?
हाँ, बढ़िया.
ओके, थैंक यू.
दिखाओ जरा वीडियो को ऑन करके फेस तो दिखाओ आपको.
वीडियो नहीं है, बैंडविड्थ नहीं है, that is the problem.
Excuse me, sir.
Yeah, please.
Can we start now?
Yeah, let us start.
Okay. Good morning, everyone. Welcome to the day 2 technical session TS2B of INTROMET-2021 on climate variability and extreme weather events. In this session, we have 2 lead talks by Dr. D.R. Patnaik, Scientist F and Head of Numerical Weather Prediction Division in India Meteorological Department, New Delhi, and Professor Someshwar Das from Central University of Rajasthan, who is a former Scientist G advisor at National Center for Medium Range Weather Forecasting and IMD. The session is followed by one invited talk by Dr. Susmita Joseph, Scientist E, Indian Institute of Tropical Meteorology, Pune. After the lead and invited talks, we have 3 short oral presentations. This session is chaired by Dr. K.J. Ramesh and Dr. C. Nanasheelan. Dr. K.J. Ramesh is the former Director General of Meteorology, India Meteorological Department. He holds immense research experience in the field of numerical weather prediction with specialization in weather forecasting, hazard and climate risk assessment, and early warning. He was a member of Indian delegation for UNFCCC negotiation on climate change related issues. Dr. C. Nanasheelan is Scientist G from Indian Institute of Meteorology, Pune. He holds immense research experience in climate variability, decadal prediction, and ocean modeling. He received Platinum Jubilee Lecture Award by Indian Science Congress in 2018 and Certificate of Merit Award from MOES. The lead talk is for 20 minutes plus 5 minutes discussion. Invited talk is for 13 minutes presentation plus 2 minute discussion, and short oral presentation is for 9 minutes plus 1 minute discussion. We request speakers to adhere to the time allotted. The selected questions in the chat box will be conveyed to the chairs by the rapporteurs. Now, may I request the honorable chairs to kindly take over the session. Thank you.
Yeah, thanks very much for introduction, and welcome to the lead and invited speakers for the session, and congratulations to the organizers for nicely conducting the event through remote fashion. Lot of effort by QSAT faculty, students, and research scholars. We appreciate all that effort, and without losing further time, I will have the pleasure of inviting Dr. Patnaik, who has been instrumental in making extended range forecasts operational in India, and he will explain more on that. Now I hand over my co-chair for his comments, Dr. Gansilan, please.
Welcome all of you for this today's event. So without wasting much of our time, so first of all, I thank the organizers for giving us this responsibility, and I wish all the best for all the speakers. So looking forward for the enlightening talks from the lead speakers and the invited speakers and the session speakers. Thank you all. So we'll start, sir.
Yeah, Dr. Patnaik, floor is yours.
Yeah, good morning to all of you, sir. So can you see the screen?
Yes, please go ahead.
It is moving. Oh, sorry.
Yes,
sorry.
moving.
Oh.
Go ahead, please.
Okay, so I'll be slightly talking in a different, means not purely on extended range, as sir was telling, but yeah, it is a climate change in extreme weather. As you know, this is a burning topic now. Okay, so here, if you see here, I just did my layout. What is the climate system and how the variability and change can be distinguished? What are the observed changes that we have noticed in over India, and how these changes are associated with the increasing frequency, or how the changes in the extreme weather frequency over India, and some of the climate change scenario, and how the implication, particularly the organization like IMD, because the increasing frequency, how it will lead to the problem for the disaster manager and also the forecasters. I'll be talking on that one. So if you see the climate system, it is that means it is a very complex system: atmosphere, lithosphere, hydrosphere, biosphere. So these all things are interacting with each other. And when you come to the right panel figure, if you see this climate system, it is a very complex system. A lot of physical processes are taking place. The interaction with the surface condition, boundary condition, ocean, sea, exchange there, atmospheric, there are gases, I mean greenhouse gases, other gases are there, radiation interaction. So all these processes are that we have to incorporate when we want to study into climate system. That's why the climate model for prediction or etc. It is very complex modeling system that we are dealing, and the prediction part is very complex. Okay. Now, addition to now the what are the sphere, all these things. Now there is another thing is nowadays very common. It is called anthrosphere. That means anthrosphere is human-induced interaction with climate is taking place. There are systems where the climate change is taking place because of natural variability, like long-term climate change. Yes, in natural process also, that also one or two slides we will show here. But the anthrosphere means some part of what is the part of the that is affected by climate change or human induced or habitat, all this thing. So this is now the area because a lot of changes are taking place due to the human induced part. So that is our concern, how that can be minimized. So then people are when you come to the journalist or they are always, any event will occur sometime or a heavy rainfall or one day or particularly, then automatically everything will be accounted for climate change. But it is not like so. The climate variability has a different component and climate change is different. So we have to distinguish what is the variability part and what is the change part. So simple definition, variability and change. If you look at the variability part, it is just year-to-year variation. Some year can be very frequency of heavy rainfall or high temperature can be there, but suddenly next year also it can reduce. Opposite can happen. So this type of year-to-year variation, season-to-season variation, that is exists. That is natural variability, natural climate variability, because it is not that there is some standard deviation of that. So it is not that everything will be too close to mean always. So there will be some variability. Okay. Yeah. So then, but this is the variability. But when you come to climate change, if this variability, a particular pattern, suppose increasing temperature, if you systematically, if you for a long period of average, long period and over a average over a bigger domain, if you are getting this type of detection changes, then we will call it climate change. That's why the climate change is not a one year or 2 year phenomena. It is a systematic change. And minimum from the WMO definition point of view, we take actually at least minimum 30 years period. So 30 years period average, if we get significant difference from the previous 30 years, let us say, then we can say there is a climate change or there is a trend in increasing or decreasing frequency. So that for that we need to have a long period. Okay, so this is the just different long-term climate change. If you because the world exists from very billions of years ago, but for climate change we are talking the observational records available only for, let us say, 140 or 150 years. So before that we do not have, but there are techniques where people have detected ice age, etc. So the long-term climate change are basically the orbital parameters, this like your eccentricity of the earth, then your obliquity and your precision. So all this Milankovitch theory, that is for a long-term climate change. So these three are causing the systematic change in climate, because it changes the received Earth radiation received by the Earth due sun, all of it, and also the obliquity, means this angle, how the weather will occur. Then also the precision. So one is 1 lakh period, the obliquity, this is the eccentricity, then obliquity you 41,000 years, and this precision is about 22,000 years. So this is very long-term climate change, that is famous Milankovitch theory. We are okay. So this is the just periodicity here. Let me something. It is overlapping where some. Okay. So now when you come to human-induced climate change, it's the greenhouse gases. So when you greenhouse gases means the 5 gases, let us say carbon dioxide is the major component of greenhouse gases, and there is a systematic increase of greenhouse gases, and that is changing the radiation balance, and Earth becoming more warm from year to year, and that because that it is trapped radiation going from Earth's surface, it trapped, and this is causing the warming of the Earth's surface. And if you see the carbon dioxide increase, yes, it is now, this is current thing also 450 parts per million. So this is November 22, day-to-day monitoring also going on. So systematic rise of carbon dioxide, and this systematic rise of carbon dioxide has caused the systematic rise of greenhouse gases, and the impact of global warming also gradually. I mean, after last, if you say last 30-40 years, this rise in trend in CO2 increase is systematic, and that is also manifested in your radiation balance, and the net loss of carbon dioxide or net gain. So totally you are getting means loss, the because ocean, all these things, vegetation, that sinks the carbon dioxide, but the major amount is emitted by the other processes like this thing, and net is there is increase of carbon dioxide, and due to this increase of radiation balance is totally changing, and we are heading towards a warmer climate or greenhouse gases. So, and if you see that the greenhouse gases is very systematically manifested in the regional level also. This is the mean surface air temperature over the Indian region. And this for the last 100 years, if you look at also, so it is clearly increasing a trend. And this decadal mean also, if you see the decadal mean also, there is last 50 years, it is actually very in systematic increase. And that we have noticed in maximum temperature, minimum temperature, and also the mean temperature. All the maximum temperature, minimum temperature, there is a systematic rise of temperature at least last 30 and 40 years. Yes, so this is the annual minimum temperature. Okay, now how this thing, this is climate change. Actually, detection means mainly there are indices you can detect, but measure is temperature and precipitation. These are the two fundamental parameters, means met parameters from where we can detect the climate change. And that observational record what is available, without that going for the isotope, that long-term climate change, even the observational record what is available 150 years onwards, that is also very clearly indicating the systematic rise of temperature. That means this is the climate change. So now when we come to the weather, because climate change is one part, how it is affecting the weather over the year. So for that, what we should see is that how the observed weather pattern, if there is observed weather pattern also, we have the long period data, 130, 140 year data is there. So how the changes are detected observationally, then models, how the models are working, and the model projection. That's once we validate the model for the current climate, then if that is it is capturing the observed pattern, then the projection of that model is for the future, so that we will get the future projection for the climate change. Now coming to the extreme weather, this is since climate change and extreme weather, this is a, let us say, weather pattern, means how throughout the year India is affected by one or other the severe weather pattern. Starting from December, if you could North India, yes, WD, your cold wave, fog, etc. seasons are there, and at the same time South Peninsula also gets rainfall because of the easterly waves. Okay, so this is the winter or post monsoon, sometime December. This is the current time actually, if you get. But when you come to pre-monsoon, March, April, May, these regions are thunderstorm regions, prone to thunderstorm activity. and the northeast India and the say, Bihar, all these regions. So this is prone to more thunderstorm, heating and moisture supply there. That's why large part of tornado. Even sometimes we get the tornado also. Pre-monsoon. Occasionally pre-monsoon we get also tropical cyclone. And yes, you have seen that some good severe cyclone also occur during the pre-monsoon time. May month also you get severe cyclone like Amphan, etc. That super cyclone was also in the month of May. So that is the cyclone season. And then when we come to monsoon season, June to September, yes, monsoon trough is there, mid-tropospheric cyclone, west coast vortex, west coast trough, monsoon trough. This will give the entire India many parts of the thing heavy rainfall, because this is a tropical country and very urbancy, moisture is bringing a lot of moisture, and the Himalaya is there at the north, and so turning wind. Now it is your trough is there, low pressure and depression is also forming. So we get many parts flooding over the during June to September. So that is also severe weather. Coming to after the September, yes, severe cyclones are there. With post monsoon mainly occur, but sometimes pre-monsoon also occur. But post monsoon are the major is the major season for the tropical cyclone, and we get very heavy rainfall associated with the cyclone. Also strong wind and other damages, storm surge, etc. So that's why the India is a land where you will get all type of severe weather during the entire year, we can say. So natural hazards means, or if you convert that into the hazards, yes, earthquake also there, but our point of this was not earthquake. This is not hydrometeorological disasters, seismological disasters. But heavy rainfall frequency region, if you see large area of central India, we get the mean heavy rainfall. Then entire 7,000 kilometers of this coastal belt, yes, prone to your tropical cyclone, and sometimes it is storm surge also, storm surge. And cyclone frequency, though it is very less, but Bay of Bengal cyclones are very only within 3 days something it will cross the coast and it will have a lot of damage because of bathymetry, etc. And this is the rainstorm during the monsoon time. This is the area where we get the formation of the monsoon depression. And heavy rainfall, yes, our country, we get 90 centimeter average rainfall over the India, but there are pockets where we get many heavy rainfall days. And this heavy rainfall, because of heavy rainfall, all the river basins are flooded during the monsoon season. And when there is a failure of monsoon, large part of the India also is affected by drought or severe drought. So all type of severe weathers are there, and this is the thunderstorm. How the thunderstorm more prone to the northeast India, and even 100 and 110 days, 20 days on year, that is average, that we get the thunderstorm, and sometimes associated with your hailstorm and also tornado. So this India is a major land where all type of disaster, and that's a climate change and other factors like population density. These are also the other factor where the impact of climate change on country like South Asian country are more damaging, because your all configuration, population density, and nature, all type of severe weather. That's why this is a more that impact of climate change really is more on adverse impact or more on our tropical country like India. So this is just a statistics. So already I mentioned this one: heat wave, cold wave, landslide. Even the landslide also, mountainous regions due to heavy rainfall, we are getting frequent landslide due to heavy rainfall, particularly during the monsoon season. Okay. So these are some of the things. JK plots. Right. A few days back also, Chennai, you have seen that Kerala, Chennai, southern part of the India got heavy rainfall and flooding over the day. And it is very frequent during monsoon season over the northern part. Yes, but it opposite, that drought also can lead to the severe problem of water scarcity and even food security, etc. Cloud burst. Okay, so heat wave, cold wave. Now the climate change. So how that means, why it is happening? Why it is happening that climate change is causing the more severe weather? Because if you see, yes, there was a mean pattern. This is the mean distribution, and in the changing climate, the right pattern is this. So as a result, the mean is shifted toward the higher. So more area is vulnerable, more hot weather, more heavy rainfall. So that's why now it is more frequency is increasing for the heavy severe weather. And when we want to detect two parameters, that is temperature and precipitation for the climate change, and it is also more hydrological cycle that is changing. As a result of this high temperature, so the process natural hazards, that the frequency of natural hazards increasing, and because of natural hazards, for hydrometeorological hazards, the losses due to the hydrometeorological hazards are 90% of event, 70% of casualty, and 65% of economic losses are due to the hydrometeorological hazards. This is a statistic from the WMO. So if you see, just mean all the hydrometeorological hazards are vulnerable, means life also, taking life, economic loss, damages to property, life and property, and also the event wise also, this is the mood. Okay, so temperature, when we come to temperature and rainfall over the Indian region, yes, more number of heat waves. So coming to the heat wave, let us say temperature wise, high temperature more than 37 degree, on average it is about 30 days are more than 37 degree. So we get in the pre-monsoon season. As a result of heat wave area is also increasing. That means on average, so this is a heat wave front belt, North India, even some coastal part of east coast of India and central India, Northwest India. So this is the heat wave region, and the trend, there is an increasing trend of heat wave. That means observational fact record has shown that there is a systematic increase of heat wave frequency over the most part of India, and during this last 40 years. So if you see the 40 years, observed climate change indicated increasing frequency of heat wave. Similarly, when we come to the monsoon rainfall, sorry.
You have 5 minutes.
Okay, sir. Yeah, I will be coming. So monsoon rainfall. So this is a more frequent droughts are there now, but seasonal totally not changing. But when we come to the extreme rainfall event, so that is increasing. Extreme rainfall frequency, that means less number of days you will get rain, but the quantity wise heavy rainfall you will get. But urban area it is more now because of the pollution, etc. The cloud condensation nuclei availability. So more effect is on the urban than rural part. And yes, drought frequency and drought frequency also increasing. And this is a recent analysis done by our IMD Pune group. Yes, so they have also shown different category of rainfall. So most part of here, if you see the heavy rainfall, wherever the blue region, that is increasing. It is a red region is increasing and the blue region is decreasing. So many parts it is increasing frequency of it. So what is the implication of this increasing? It is a disaster risk management. Disaster risk management is a critical component of climate change adaptation. That's why since the extreme rainfall is increasing, it is leading to the problem for the disaster management. But what is our role? Another part is that disaster manager will be face a severe problem for this increasing frequency. But when we want to provide the service like IMD, organization like IMD, so if there is a problem, that we have to give the early warning, we have to give the impact or forecast. That's for that. But the one challenging area, if you look at this figure, how the global warming is changing, rising temperature, increasing evaporation, increasing moisture content of the atmosphere, increasing small scale, mesoscale convective error, and heavy downpour. So that's why that is also reflected. There is increasing frequency of heavy rainfall. At the same time, decreasing the error, average error doubling time. That means very moderate forecast error means you are getting the large error immediately. That's why the problem of predicting the model heavy rainfall event is also challenging. And that's why we have to improve our model so that the heavy rainfall event, particularly this 20 centimeter or more, should be predicted accurately. Then projection wise, yes, the observed changes we have seen. Projection wise, IPCC, the Intergovernmental Panel of Climate Change, they assess all the report, and now AR5 also there. So basically, this is the summary. Yes, there is an increasing shift of this thing that also indicated in the future climate change. So more hot weather will get, and also the lower panel is more heavy rainfall. So projected changes are also in the similar line like the observed changes, and that is also there means you are going to get the more induced heavy rainfall, particularly 5 days due to human induced global warming has led to an increase in the frequency, intensity, amount of heavy rainfall. So that way, that is a more clearly visible in signal, we can say, from the climate change assessment. On the regional scale, yes, we have also done our CCCR group in IMD Pune. They have brought out a report. All those are indicated, and it is also in similar line with that. What are the changes that reported to AR5 or AR6? So why that since sorry. Since this is the fact that we are leading to going towards increasing frequency of heavy rainfall. So our means how the mitigation or for that we have to switch over from our simple weather forecasting to impact weather forecasting. That means impact weather forecasting means not that this much rainfall will happen, model indicating that's sufficient. But that if that rainfall will lead to flooding over particular river basin, also it will be entering to the mountainous region, then it will lead to the landslide. So all the impacts, what are the possible impacts, but that need all other impact data from the state government, all levels. So once that is integrated to your weather forecasting, integrated with the geophysical parameters from the different region, then we can have a proper impact by forecasting, and that will help little bit to minimize the impact of adverse impact of the climate change by the disaster managers. So yes, their priority area, all the sectors will be affected due to climate change, and our forecast is also we are trying to provide the services to all these sectors by our super improving in the model and synthesizing all the outputs of the model and giving a proper impact where forecast to the disaster manager. So that way, so to in summary, what I would like to summarize here, the climate change is leading to increasing frequency of extreme weather. That is very clearly visible. That is also seen in the observed fact and also the model projection part. The risks of climate change are inequitable. With a developing country like India will be impacted more because the severe weather is in land of severe weathers, and there are other factors like population density, coastal large coastal area, and all bathymetry that places. So all these factors are added to the vulnerability of the Indian due to climate change. It is not only India, on entire South Asian country. So with respect to IMD has taken many steps toward improving the early warning of disaster weather in recent times. So as you have seen, observational improvement, model improvement, how the forecast strategy improvement, how we can go for the impact backs. So that's why this is one way of partly contributing toward the improvement of the services arising due to the climate change. And impact-based forecasting will be very useful in minimizing the adverse impact of weather, severe weather, particularly through a effective disaster management. I think with that thing, I just complete my talk. Thank you, sir.
Thank you, Dr. Patnaik. There is a question in the question box.
Yes, sir.
Please answer briefly. Is heavy rainfall in recent days in peninsular India is due to climate change? Please answer. Thank you.
Yeah. Okay. So, okay, now, so if you see the heavy rainfall over particularly the Southern Peninsula, there is one part that is very clearly visible is that the monsoon season, southwest monsoon season has been extending toward the October also, and that we have seen. As a result, monsoon that is very systematic, and we are getting more rainfall over that part. But this particular event, like Kerala event or South India event, it can be a part of the climate change, but we have not particularly analyze the heavy rainfall event over that region for last 60 or 70 years. So, but certainly it is contributing to because of the climate change, but detailed analysis that we have to need by taking the station level observation, station level data for a longer period.
And please carry out attribution study. Now, attribution of extreme weather event to climate change or not becomes a very important question. Please make efforts to do a regular attribution study of extreme weather events.
Yes, sir. Yeah. Yes, sir.
Thank you. Thank you. Thank you, Dr. Patnaik, for wonderful talk.
Thank
I
you,
request
sir.
my co-chair to take the proceedings forward. Thank you.
Thank you, sir.
Thank you, Patnaik.
Yes, sir. Thank you.
Welcome, Professor Someshwar Das for his talk on challenges in predicting extreme weather over South Asian region. He has done a lot of work on the Himalayan meteorology, extreme weathers in the Himalayan region, the cloud processes, cloud modeling, general circulation. And he has done a lot of work. So he has published several papers on these topics. So looking forward to listen. Please, sir. Yeah.
Yeah, thank you, Dr. Gansilan. And thank you, organizers, for giving me opportunity to present my talk here. Am I audible and visible clearly?
Yes, please share your presentation. Thank
Okay,
you.
Great. All right. Can you see my screen?
Yes, please.
Okay, great. Thank you. All right. So basically, I'm going to summarize some of the challenges in predicting extreme weather over South Asian region. My focus is mostly on the short to medium range forecasting. Okay. This is the outline of my talk, starting with the introduction. I'll talk about the challenges in observations, challenges in modeling and prediction, and the future. So, first of all, what is severe? When we talk about the severe or extreme weather, what is severe? And most of you know that anything which is anomalous, okay, anomalous from the mean state of the atmosphere, it can become severe. But then it is a relative term. For example, the amount of rainfall that occurs in Cherrapunji, okay, if that amount of rainfall occurred in somewhere in Rajasthan, then for Cherrapunji, although it is a normal thing, but for Rajasthan, it will become extreme. And similarly, the kind of temperature, the maximum temperature that occurs in Rajasthan, if that occurred somewhere else in India, for example, in Simla or in elsewhere in hilly region, then that becomes extreme for that region. So basically, when we say extreme or severe, it is a relative term. And our challenge is to be able to predict that anomaly, okay, from the mean state. Well, you know about what kind of severe weather systems affect us in our Indian region. Just now, Dr. Patnaik has elaborated about most of the severe weather systems that affect India, starting with thunderstorms, cyclone, fog, cloud burst, heavy rainfall, heat and cold waves, droughts, etc. But the fact is that despite the existence of many global and regional models producing wide varieties of forecasts, the meteorological disasters continue to take its toll on the human lives and economy of the country. So that is the challenge, that how, with the existing observational systems and the modeling and the understanding of our atmosphere, how can we accurately predict these kind of severe weather systems and minimize the casualties? Okay, I'll just highlight some of the recent examples of severe weather that occurred. For example, in 2018, during March to June, about 44 storms affected 16 states of India, and about 423 people were killed. Okay, and thunderstorms are such events that they occur many times during a season and keep taking its toll in terms of 10 or 20 people, and then when we accumulate the entire thing over the season, that becomes too many, right? This is one of the example of the severe storm that occurred on 2nd of May 2018. As per the observation, that particular storm recorded 125 kilometer per hour wind speed by one of the Air Force stations. And if we included all the casualties that occurred because of that storms, we find that UP, Rajasthan, Telangana, Uttarakhand, and many were affected, and altogether on that day, on 2nd of May 2018, 129 people were killed. Okay, so this is just one example of the severe thunderstorm, right? Similarly, the lightning, okay, which is associated with the severe thunderstorm. Nowadays, you know that lightning is treated or counted as one of the most severe event that causes a lot of death. It is estimated that more than 2,000 thunderstorms take place around the world at any given instant. Okay, the number of lightning strikes over the earth per second is about 100, of which 80% are in cloud flashes, and 20% are cloud to ground flashes. And this 20%, which is the cloud to ground flashes, are the one which affect directly us. Okay, this implies that there are about 86 lakhs and 40,000 lightning strikes over the earth per day. Okay, so the average casualties due to the lightning is several hundred per year. If you count together all the casualties that occurs because of the lightning, it becomes several hundred. Okay, and somehow that becomes more than the casualty that occur nowadays because of the cyclone, which used to be the biggest killer a few years ago. Recent statistics have shown that Bihar tops the list of states with maximum death due to lightning strikes since 2019. Okay, according to the report, Bihar has reported the most deaths due to the lightning between April 1, 2020 to March 31st, 2021. About 401 deaths, followed by UP, 238 deaths, MP, 228, Odisha, Jharkhand, and so on. Okay, Bihar saw about 168% increase in lightning strikes in 2021, followed by Haryana, which showed 164% rise, Puducherry, 117%, Himachal Pradesh, 105%, and so on. There has been a 34% rise in lightning strikes in the country. It has advanced from 1.38 crore strikes in 2019-20 to 1.85 crore strikes in 2021. So this has become one of the biggest hazard. Hailstorm is another severe storm, severe weather system. This is a very interesting image which shows the hailstorm that occurred over the Delhi NCR region on 7th of February 2019. And it appears that snowfall occurred. This is the image of Noida, and it appears that snowfall occurred over Noida. So this was a very severe storm, a severe hailstorm case. Okay, cyclones already Dr. Patnaik has elaborated. Cyclone occurs every year during the pre-monsoon and the post-monsoon season. Again, these are the recent examples of cyclone Gulab, cyclone Amphan, and because of the advancement of our observational technology and also the modeling system, we have been able to minimize the deaths because of the cyclone. As you remember now, a few decades ago, for example, Odisha's super cyclone of 1998 caused more than 10,000 deaths because of that event. Whereas many cyclones have occurred of the same intensity even afterwards also, say for example, Phylin or Hudhud or many more after that. And in those severe cyclonic storms, the casualties have been very less, and that is because of the advancement of the modeling system as well as the observational systems. This kind of diagrams are very familiar to you, I know. As soon as the cyclone forms, the IMD starts giving this kind of forecast, the cone of uncertainties of the tracks, and also the areas of the uncertainties about the intensity of the cyclone in terms of the wind speed. Okay. Also, because of the advancement in the modeling system, now we have been able to reduce the errors in the point of landfall, in the intensity at the landfall, in the time of landfall forecasting. All those things have been improved a lot in the recent years because of the advancement of the technology. Okay, fog. This is another severe event that occurs mostly in the winter in the northern part of India, and it is estimated that due to the severe fog in the winter season, about 18 to 20 crores rupees are lost in about 1 week time because of the diversion of the flights or the delays of the flights by the airlines. And so it becomes very important to be able to forecast the occurrence of the fog, not only the occurrence, but the time of the onset, the time of the maximum fog, that means the least visibility, as well as the time of the dissipation of the fog. These things are the challenges which have to be, which are there to the meteorologists and the forecasters. Okay, cloud burst, another example of the severe weather events. This is one of the events that most of you know that occurred our Kedarnath shrine in Uttarakhand in June 2013. About 340 millimeter of rainfall, which was 375% of the daily normal, occurred over there, and it caused more than 5,000 deaths, almost 6,000 deaths. 4,200 villages were affected because of that event. And this is in statistics of the cloud burst in about 30 years time, from 1970 to 2015, uh, uh, by different authors. And it shows that over the western and central Himalayas, these cloud burst locations are concentrated. The maximum cloudburst is concentrated over the Uttarakhand region, over this season, and that occurs mostly during the monsoon season, when the easterly monsoon current and the westerly system they collide each other, and then it causes lots of instability as well as thunderstorms and the heavy rainfall, and suddenly the cloudburst outburst of the rainfall. Okay, this is an example of a very old heavy rainfall event that occurred over Mumbai in July 2005. In one day time, 944 millimeter rainfall occurs in 24 hours at Santa Cruz area, whereas just 30 kilometers away at Colaba, only 74 millimeter of rainfall occurred. So this is such a contrast in such a small distance, and clearly it was because of the some mesoscale system that formed over that region. If you recall, more than 1,000 people were killed in Mumbai. About 5,000 crores rupees were lost. The ATM network of several banks stopped functioning. No electricity in certain areas in Mumbai city for 5 days. 1 million people rendered homeless. About 1,100 flights cancelled, and airport closed for 2 days. So these are some of the effects of the severe weather. Okay, and this is a challenge to the meteorologists and the forecasters. Still, although we are able to forecast the signature of such events, but still to be able to forecast timely the specific location of the event, time of the event, intensity of the event is a big challenge to the meteorologists. This is an example of the Kerala flood, which occurred in 2018. During August 1st to 19, about 758 millimeter rainfall occurred, which is more than 164% of the normal rainfall that occurred in Kerala. Okay, these are some examples. So challenges in the observation. Okay. Now the question is that how much observations are required to accurately predict the physical phenomena. Okay. Now this depends on the spatial and temporal scale of the phenomena, whether we are going to predict a very small scale phenomena or a large scale phenomena. Okay, depends on that, how much observations are required. Generally, good density of observations can resolve a phenomena better. That is a well-known fact. Okay. Now, the success in modeling and prediction depends on two major challenges. Okay. Number one, as for the modeling is concerned, most of you know that now the NWP, the numerical weather prediction models, they require a very good initial condition because they are initial value problem. And so the initialization of the correct structure at time zero by data assimilation is far from solved problem, embedded in correct large scale sounding to be able to represent the cape and the wind shear accurately in the atmosphere. That is a challenge. Okay. Even with the perfect initial conditions, the physics parameterization, especially the microphysics, are not and cannot be perfect within the bulk parameterization framework, because the way we parameterize the chemical processes in the model is very, very difficult, and we really cannot perfectly resolve these systems in the large scale model. Okay. Now, so what kind of observation systems we have? This is a very familiar diagram. As you know that the entire Earth is now covered by many types of satellites which continuously monitors atmosphere three-dimensionally, and then passes the informations to all the forecasting centers, the biggest forecasting centers. Okay, and as you know, we need the three-dimensional structure of the atmosphere to be able to predict the weather. And this is a very familiar diagram again. All kinds of observation systems like satellite, the Doppler weather radar, the aircraft, the automatic weather stations, etc., etc. They continuously give us the observations of the atmosphere. We need the three-dimensional structure of the atmospheric observations. And the point is that how much observation network is available our region, that is our southeastern region. Now, this is an example of the Doppler weather radar network over India. Okay, the present coverage of the Doppler of India by the Doppler weather radar. About 27, I think, DWR are presently located in different parts of India by IMD, and many more are coming up in the coming time in the future. And similarly, the right panel shows the AWS automatic weather station network. That's out India. India is by and large covered very well by the observation system. But what about the nature? I mean, neighboring countries, because for the meteorological phenomena, we need the observations on a large scale, not only in India but also in the neighborhood and elsewhere, globally rather. Okay, so this is just an example.
Dr. Somesh,
Yes.
you have 5 minutes left. Thank you.
Okay, then I'll quickly try to move. Okay. So these are the examples of the Doppler radar coverage over Bangladesh, over Nepal, over Myanmar, over Pakistan, over Sri Lanka, and so on. Okay, and the point is, out of all the observations that we get, how many really are of good quality, and how many really enter the assimilation system? How many get rejected? How many get accepted? That's very important. Okay, and because of this lack of observations, we see the forecast by the SASC for the monsoon, then there is not always a consensus. There are some locations where the forecast is quite good, but there are some other locations where the consensus is not there. Okay, so in order to be able to understand the systems properly, many forecast demonstration projects have been designed in recent years. For example, we also had done the high resolution forecast over a small area during the Commonwealth Games. Before that, in Beijing 2008, Sydney 2000, we also had storm program, the SARC storm program earlier. Now this is a storm program which is conducted annually. The BOPTEX, the Bay of Bengal Tropical Cyclone Experiment, the FDP on fall, that is a YFX, SWFDP, that is Severe Weather Forecast Project of WM, and so on. Okay, this is an example of the elsewhere the Japanese TOMAX severe project. This is about the YFX which was conducted during December, January of 2015, 16, and 17. Okay, this is the domain of the SARC storm. We had 3 phases in which India, Nepal. In the first phase, India, Nepal, Bangladesh, and Bhutan were covered. In the second phase, India, Pakistan, Afghanistan were covered. And in third phase, India, Sri Lanka, and Maldives were covered. So these are the examples of that SARC storm. So what about the challenges in prediction? Okay, in modeling system? Okay. Now, weather is a result of the motion of air caused by a balance between various forces, and all of us know. This may be described by the equations of governing the atmosphere. Some of these equations are nonlinear partial differential equations. So the question is, if we know the laws and the variables, why can't we make perfect forecast, even with a short lead time? Right? There may be many reasons for this. Some of them are summarized here, like inaccuracies in the initial conditions, multi-scale interactions between the systems, like from turbulent scale to the large scale, the chaos and limit of deterministic predictability, and resolutions, both vertical and horizontal resolutions. Also recently, nowadays people have started applying the AI, the artificial intelligence and machine learning in making the weather forecast at different ranges. Okay, the major achievements in NWP in the last 30 years are because of the high resolution modeling, data estimation techniques, improvement in that, ensemble forecasting, high performance computing systems, and so on. Just there are the examples of the operational forecast on the lightning that is given by different centers like NCMRWF, IITM about the lightning flash rate, about lightning potential indices, etc., which are given every day on routine basis, 3-hourly forecast. So the challenges ahead are like a very high resolution modeling at the cloud scale or at the turbulent scale, to be able to do on routine basis the rapid update and convective data assimilation. What we do are nowadays the large scale data assimilation, not the convective scale data assimilation. So that the convective data scale data assimilation has to be done to be able to more accurately forecast the small scale phenomena like thunderstorms and so on. Maybe every 10 minutes or at least every 1 hour, cycle the data has to be assimilated in the model. Nowadays, the smartphones have sensors for measuring the surface pressure, and there are millions and millions of smartphones all around the world. So if we are able to utilize the surface pressure and assimilate them in the model, that will also make a great change in the improvement of the forecast. So assimilation of the smartphone surface pressure will revolutionize the rapid update convective scale data assimilation system. Okay, so the future of course is always a dream system of convective scale NWP, in which there are 4-dimensional ensemble Kalman filter hybrid data assimilation system done every 5 minutes at 1 hour, 1 kilometer resolution, and of course demands a huge amount of computing power. At 1 kilometer resolution, ensemble forecast launched every 10 minutes up to 6 hours. Reduce 2 to 4 kilometer resolutions, ensemble forecasting up to 72 hours. Okay, deterministic forecast from ensemble mean analysis at up to 250 resolution. I mean, at the turbulent scale, so to say, and at reduced resolutions beyond 6 hours. Explicit forecast from MCS down to tornado vortex scales with probability estimates. Okay, they are the dream lists. So with this, I thank you very much once again, and I think my time is up, so I stop here. Thank you.
Thank you, Professor Someshwar Das, for
Yes.
very interesting talk on the challenges of extreme weather predictions. So we don't have any questions from the audience, but I have a small question. So you mentioned about the future challenges. So how realistic the 1 kilometer ensemble Kalman filter or the ensemble prediction which you have proposed?
Well, this is a dream list, obviously. I mean, it's a long way to go. The assumption is that by doing the 4D ensemble Kalman filter, we will have a much better initial conditions, which are very, very important for any NWP system. So if we are able to initialize the model with very accurate observations, so that we are able to represent the 3-dimensional structure of the atmosphere, then our forecast or the solution of the model equations will be more accurate. And at such a small scale, at least at doubling the scale up to 50 meter resolution, or even at 1 kilometer resolution, we assume that we will be able to resolve explicitly the processes that take place within the clouds. And with that assumption, we believe that the forecast or the solution of the model will be more accurate. So they are the kind of a dream list now, which is going to take a long time to come. So this is what is.
Okay. Thank you. We have a question now. So you mentioned that some observations are accepted and some are rejected.
Right.
Explain some of the main criteria that are considered for accepting and rejecting any observation or data. Maybe he is talking in the context of data assimilation.
Data assimilation, right. Yeah, well, the point is that when we take the observation from different types of instrumentations, now we incur different kinds of error. For example, every instrument has an instrumental error. Okay, no matter what, how accurate it is calibrated in the laboratory, the instrument has its instrumental error, whether it's a thermometer or whether it's a radar or whether it's sensors of the satellite. Okay, they all have the instrumental error. So those errors, and with those errors, whatever observations we get on real time, okay, that also get contaminated because of the transmission error through the telecommunication. Because as you know, most of the data is received at the broadcasting center through the GTS, the global telecommunication system. So sometimes the telecom errors are also included in the transmission of the data. Then with all that, when we try to assimilate them in the model, then there are constraints like now, all those observations are supposed to represent the known laws of the atmosphere. For example, when we use all the observations, they must obey the certain constraints like the conservation principles, right? Like the hydrostatic balance, like the conservation of entropy, etc. So if the observations are not able to obey the known principles of the atmosphere, then they're supposed to be of output quality. Okay, so certain checks are included in the assimilation system, which checks every observation point by point, okay, at every time step. And if they find that the observations
Professor Das,
right.
Professor Das, we are already behind schedule. Please answer him through the chat box. Thank you for wonderful presentation.
Thank you, Dr. Ramesh. Thank you.
Yeah. Now I'll have the pleasure of inviting Dr. Sushmita Joseph for presenting her talk on recent changes in the spatio-temporal characteristics of monsoon intra-seasonal variations. Dr. Sushmita Joseph is a active scientist from IITM Pune. I request her for her presentation. Floor is yours, Dr. Sushmita.
Dr. Ramesh, I'm sharing my screen. Hope my screen is visible. My screen is visible?
Not yet, it's coming, it's coming.
Yeah, it's now visible. Go to the presentation mode, that's all.
So my screen is visible. It is
yeah. Please go ahead. Yeah.
okay. Thank you, everyone. I really thank the organizers for giving me this opportunity. So today I'm going to talk about the recent changes in the spatial and temporal characteristics of monsoon intraseasonal oscillations. So this is based on a recent work published in Theoretical and Applied Climatology. So already my earlier speakers have set the preamble for this talk that the global warming has risen substantially and the extreme events are increasing. So there are studies that show that the Indian summer monsoon rainfall is also showing an increasing trend in the recent years. And they are attributing this to the increasing trend in the forming of these oceans and land. So as we are experiencing a lot of extreme events, and we expect that the monsoon intraseasonal oscillations, which we experience in the form of active and break spells, they would also exhibit a more of spatial and temporal variability. So this was the motivation for the study. And for this, we have seen the spatial pattern of, we have selected two periods, that is 1982 to 2000 and 2001 to 2019. So here we have seen the seasonal rainfall for the two periods. And if we plot the difference between these two periods, we can see that there is an increased rainfall over this western parts of the country, and there is a reduction in the central as well as the eastern parts of the country. So we have seen the intra-seasonal variability also we calculated. This is the standard deviation of the 10 to 90 day filtered rainfall. So here also we can see that the difference in the intra-seasonal variability is also having a similar spatial pattern. So they are sharing a commonality in the spatial scale. So then there are studies that have seen the changes in the characteristics of active and break spells. Some one or two studies are there. So our focus was on the different duration spells, that is the short as well as the long spells, how they are behaving in this global, under this global warming. So that was the main objective of this study. So here we can see the year-to-year variability in the number of short as well as the long active and break spells during this 38 year period. So here this blue line actually separates the two periods. So here this first one is for the long actives, then long breaks, short actives and short breaks. So here we can see that in the recent years, the occurrence of long actives and long breaks are more. Here I have given the total number of days in each period, this long actives and every spell it is given. So here you can see that in the first period it was 212 and it has increased to 301. And this is a 42% increase in the number of long active days. Then for the long breaks also there is an increase, but it is 32%. Then for the short actives, we can see that there is a reduction, considerable reduction, that is from 106, it has become 54, which is a 49% decrease. Then for the short breaks, from 129, it has become 88, and this is 32% reduction. So this in the brackets, I have given the number of spells in each period. So the active and break spells we have identified using the standardized 10 to 90 day filtered rainfall anomalies over the monsoon zone of India, which was defined by Dr. Rajivan's paper. And this is the composite rainfall anomalies for the different periods and for the different spells, that is short actives, long actives, short breaks, and long breaks. So here, as we saw in the spatial pattern of the intraseasonal activity as well as the seasonal rainfall, we can see that the rainfall is more over this western parts of the country. So this is the lower panel shows the difference in the anomalies, and these are significant at 95% confidence level. So here we can see that in the shorter duration spells have become more intense compared to the longer ones over this Gujarat region. But here we can see that here in the western part of the Maharashtra and all, we can see that the longer spells have also intensified. And when we see the central and eastern parts, we can see that there is a reduction in the anomalies. So for the breaks, we don't see much difference, but here also there is some indication that the break spells are actually diminishing in the western part of the country. Then coming to the Hartley circulation, this is for averaged between 65 to 95 east. So here we can see that the first panel is for short actives, long actives, then short breaks and long breaks for the two periods and the difference. So here we can see that the active spells, long active spells have intensified in the around 20° north, where we have seen that maximum rainfall anomalies. So here when we plot the difference also, we can see that the ascending motion has become very strong in the recent period. Then coming to the break spells, we can see that the long, both the short as well as the long, though it is not that significant here in the shorter duration, but here you can see that over this region, even the break spells have become weak. So these are the findings from this. So this also confirms the intensification of active spells and weakening of break spells around this 20° north region in the recent period. Now this is the low-level moisture anomalies as well as the vertically integrated moisture transport up to 500 HPA. So here also we can see that if we see the difference plot, over this part, western parts, you can see more of moisture anomalies preponderating over this western parts of the country. Even during the break spells, we can see that the moisture anomalies are more, even the moisture transport is there. So these actually can weaken the break conditions over this region. So this now coming to the low-level convergence as well as the upper-level divergence. So there are studies that show that these two parameters play an important role in the intensification of monsoon low pressure systems into the monsoon depressions. So here we have seen that over the Arabian Sea region, the low-level convergence has significantly increased, and then the Bay of Bengal, it is not that as in the Arabian Sea. And also the upper level divergence has also decreased in the Bay of Bengal region. So these factors can actually decline the formation of this monsoon lows and also their intensification into the monsoon depressions. So this can also lead to reduction in the occurrence of active spells over the central and eastern parts of the country. Now, we have seen that in the recent period, the longer spells are more favored. So we wanted to see what could be the possible reason for the lengthening of these active and break spells in the recent period. So this figure shows the power spectra of JJS rainfall over the monsoon zone of India. So interestingly, you can see that in the earlier period, when we see the periodicity was around 30 days in the first period, that is 1982 to 2000. And as we move to the recent period, the periodicity has increased and also the power has increased. So it is clearly seen that in the recent period, the longer periods are favored more. Then, so we have we have a paper published in 2009 which showed that the MJO, Madden Julian oscillation, can play an important role in lengthening the break spells. So we have seen just the Euler anomaly for the different spells, short duration and long duration spells for the 2 periods, and also the difference. So here also, if we see, we can see that in the longer periods, there is a positive negative anomaly over this region. Generally, we call it as the quadruple structure. And this is much more stronger in the recent periods. And also, if we see the Walker circulation also, we can see that for the longer periods here, we can see the alternating pattern of the negative as well as the positive anomalies, which represents the suppressed as well as the increased convection. And this is much more stronger in the equatorial region during this long active and break spells of the recent period. And this could be an indication of the presence of an eastward propagating MGO. So we have also seen the hormular plots for different regions. So this is for the equatorial region, that is the 5 south to 5 north. So here we can see that this is for the recent period. So here we can see that a clear eastward propagation is there, although here we can see the alternative patterns, but it is not that means stronger as compared to the recent period. And this breaks also, we can see a clear eastward propagation. Then over the region 10 to 25 degree north averaged also, we can see that there is a stronger movement, westward movement. These are unfiltered anomalies. And if we see the filtered anomalies, the signal becomes much more stronger. So here we can see that this pattern is, although here there is some indication, but it is not as strong as in this. And here also we can see that for the break spells, there's alternating pattern, which indicates a clear northwestward propagation from the maritime continents to the Indian region is clearly seen. So here the negative anomalies, this is for the active spells, and this positive anomalies are for the breaks. And also we can see that the northward propagation also, this is much more stronger. So what we propose is that this MGO is a Kelvin-Rossby couplet, and as over the maritime continents, when it reaches, there is the divergent pattern or the converging pattern from the maritime continents that will move to the western, move westward to the Indian region. And once it couples with the northward already northward propagating the mesospell, if it combines with that, then it can further strengthen and lengthen the mesospell, which is already there. So
you have about 5 more minutes.
Yes. So we wanted to see why the MGO was playing an important role in this. So we just saw the seasonal features. So here clearly it is showing that in the recent period, the Madden-Julian oscillation has become much stronger in the recent periods with a periodicity in the 45 days maximum, and it is much stronger in the recent period. So this is for the JJS thing. So this boreal summer, it has become more stronger in the recent period. And so here, some recent studies show that due to the increased warming in the equatorial region and over this maritime regions, the MGO has become much stronger. There are some studies by Roxy and all, which shows that the MGO has become more frequent in the recent years. So we speculate that it is the rising temperatures which are actually favoring this increased frequency of this MGO, and this is actually favoring the is actually modulating the active and break spatial as well as the temporal features of the characteristics of the monsoon spells. So coming to my conclusion, so mainly we have seen 2 things in this. There is a spatial east-west asymmetry in the spatial pattern, and also the longer spells are more. So these are the conclusions. So east-west, some asymmetry with increased or decreased rainfall activity in the western or the central and east northwestern parts of the country is existent in the recent period. And also the shorter spells have intensified compared to the longer ones. So the increasing temperatures over the oceanic and land areas can lead to increased diabatic heating over the Western India, which in turn increases the instability as well as the moisture convergence and transport over the region. This can actually intensify the circulation as well as the rainfall over the region. This can lead to intense and long-living active spells and dwindle break spells over the region. Also, we have seen that the longer mesospells are favored compared to the shorter spells, and the periodicity as well as the power of rainfall in the monsoon zone region have augmented, which is indicating a proliferation in the rainfall variability. So it is also noticed that the equatorial MGO has intensified in the recent periods owing to the warming in the Indian and Pacific oceanic regions. This increased prevalence of MJO influences the northward propagating active as well as break spells through the westward moving convergent or the divergent part of the Rossby waves emanating from the Kelvin-Rossby coupler. So this interaction between the MJO and mesospells can lengthen the active and break spells over the Indian region. So thank you.
Thank you. Thank you, Dr. Susmita. So I don't find any questions from the audience. So you mainly attribute the changes in the periodicity of active and break conditions to the changes in the MJO characteristics, right?
Yes, yes. So we are not denying the other factors also, but we have seen that this is playing an important role in the lengthening of the preference of longer spells in the recent period.
So could you look at the Indian Ocean SST perspective without coupling with the MJO?
Yeah, there are studies that are linking this variability in the monsoon spells to the Indian Ocean SSTs are all. We have this was purely an observational study. So are doing some modeling studies, means dedicated modeling studies for this on making this on Indian Ocean SST on and off. So like that, some sensitivity experiments, if we do, then we can clearly bring out such a role. So here we have not seen any, this is purely an observational study. It was actually the extension of MSc project from one student from Cochin University itself. So
Okay.
yeah,
Yeah,
we just extended that study. That's it.
Nice study. But I mean, you can also look at the ARC interaction over the Bay region.
Yeah, sure.
Yeah. So nice study. Thank you for the nice presentation. So I would like to add that I mean Susmita is also part of the team who has developed the extended range prediction at IITM, and in fact development and implementation. Yeah, thank you, Susmita. So we will now move on to the oral presentations. We have Susmita can give now.
Yeah, thank you, sir.
Stop sharing the screen. Yeah, okay. And now we have 3 oral presentations today. So we have enough time. I mean, I think we can all 3 speakers can have 10 minutes each. So okay, please go ahead. I'm first talk by Manish Joshi. He will be talking on changes in characteristics of hot extremes over India and their driving mechanisms. Manish Joshi, please.
Is my screen visible?
Yeah, please go ahead.
Just. Okay, so.
You can make it full screen and.
Yeah, I am doing. Is it okay?
Yeah, please.
So first of all, good afternoon to all of you, and thanks for providing me this opportunity to present my recent work. So myself, Dr. Manish Kumar Joshi, and presently I am working as climate scientist at Genesis Ray Energy India Private Limited, where I am heading the climate modeling department. So today I'm going to talk about the changes in the characteristics of hot extremes over India and their driving mechanisms. So the objective of this study is to diagnose the change in the characteristics of hot extremes over India before and after the 1976 climate shift, and explore the driving mechanisms which are responsible for such changes. That includes the atmospheric circulations, local factors, and the natural variability, which are responsible for such changes. The data sets used in the present study are the maximum temperature data from the India Meteorological Department, which is at 1 degree cross 1 degree resolution, to analyze the relationship of atmospheric circulations with these atmospheric circulation parameters with hot extremes. The NCEP and CAR reanalysis data has been used, and to investigate the SST forcing of hot days frequency, the sea surface temperature data from ERSST version 5 has been used. Okay, So now I will just come to the results section. So this figure shows the spatio-temporal trends in the frequency of hot days for the April, May, June season in the reference period, which is from 1958 onwards up to 2018, the non-global warming period, which we have defined as 1951 to 1975, and the global warming period, which is from 1976 to 2018. During the reference period, there is a widespread increase in the frequency of hot days over all India has been seen, except over the Indo-Gangetic plains. On the other hand, during the non-global warming period, the eastern and the southern parts of India have experienced the significant increase in the frequency of hot days, whereas in the global warming period, the frequency of hot days has significantly increased over the northwestern parts of interior peninsula and along the western coast, which indicates a spatial shift of significant increasing trends in the frequency of hot days. Now, this figure shows the variation and the linear trend in the frequency of hot days area average over all India. It can be seen that during the non-global warming period, there is a significant increasing trend in the frequency of hot days, which is increasing at a much faster rate as compared to the global warming period. So this value is around 2.2 hot days per decade in the past climate, and in the recent period, it is around 0.8 hot days per decade. But the average increase is much higher as compared to the past climate. So the average increase in the frequency of hot days is around 9.78, which is greater than the past climate, which is around 7.84 hot days. Now, to explore the change in the characteristics of hot extremes, the climatological mean difference between the two periods, that is the global warming period minus the non-global warming period, have been constructed in the frequency of hot days, their average intensity, and their seasonal maximum intensity. As we have seen in the previous slide, that the frequency of hot days has significantly increased at a much faster rate during the non-global warming period, but their average is significantly higher in the global warming period compared to the non-global warming, which indicates a clear shift in the climate towards warmer temperatures. That is, most parts of India have experienced the occurrence of more hot days and having higher temperatures in the recent period compared to the past, except the Indo-Gangetic plains. Now the question arises why the Indo-Gangetic plains have experienced the less occurrences of hot days, having lower temperatures in the recent climate compared to the past. For this, we have computed the climatological mean difference of sensible and latent heat fluxes during the two periods. Well, it is well known that the Indo-Gangetic plains is the heavily irrigated regions of the world, and this irrigation affects the surface energy budget by enhancing the latent heat flux and deteriorating the sensible heat flux. Due to this intensive irrigation over the Indo-Gangetic plains, the vegetation and evapotranspiration has increased substantially. This increase in evapotranspiration has led to the smaller portion of sensible heat flux over this region and compared to the latent heat flux, which has resulted in a decrease in near surface air temperatures over that region in the recent climate compared to the past. Now, to explore the physical mechanism allied with these hot extremes, the composites of atmospheric and surface parameters like geopotential height and omega at 500 HPA and upward long wave radiation flux anomalies at top of the atmosphere and soil moisture have been computed for the three periods as shown here. Now, that is for the reference period, non-global warming period, and the global warming period. Well, in contrast to non-global warming period, the global warming and the reference period shows positive geopotential height anomalies. As you can see, positive geopotential height anomalies over the northern parts of India. This high pressure system over the northern parts of India causes a sinking motion that leads to surface warming due to adiabatic compression that in turn causes more hot extremes. Now, to verify this, the composites of vertical velocity at 500 HPA have been computed for the three periods, and it can be seen that in contrast to non-global warming period, the global warming and the reference period shows positive omega values over the Indian landmass that indicates the sinking motion that is subsidence over the respective region. Now, this descending motion is further allied with the clear skies, which is well depicted in the upward long wave radiation flux anomalies. The positive upward long wave radiation flux anomalies indicates the presence of comparatively less clouds in the recent climate as compared to the past. As a consequence of this, more solar radiation energy has been received at the Earth's surface, during the recent decades, which has led to the warmer temperatures over the Indian landmass. In addition to this, the depleted soil moisture in the recent decades has been seen, which has led to the larger portion of sensible heat flux versus latent heat into the atmosphere, inducing a positive feedback between the atmospheric heating and further drying of the soil, resulting in an increase in the near surface air temperatures. Now, to further explore this relationship of atmospheric variables, atmospheric and surface parameters allied with hot extremes, several scatter plots have been considered. For example, the scatter plots between the frequency of hot days, area average over all India, versus the geopotential height anomalies and the upward long wave radiation flux anomalies, area average over this region, and the vertical velocity and soil moisture anomalies, area average over this region. Well, it can be seen that for the first three scatter plots, the relationship is positive, which indicates that during larger geopotential height, vertical velocity, and upward long wave radiation flux, the India has experienced more number of hot extremes. On the other hand, the soil moisture is anti-correlated with the frequency of hot days, which reveals that that during the years when the soil is wet or having higher values, India have experienced less frequency of hot days. Now, further to examine the SST forcing of hot days, the preceding DGF sea surface temperature, DGF means December, January, February, sea surface temperature anomalies have been regressed onto the standardized frequency of hot days. And the results clearly indicate that the ENSO is providing the substantial forcing for the hot days in the Indian region during the all periods considered. In addition to this, the scatter plot between the frequency of hot days, area average over all India, versus the preceding DGF sea surface temperature anomalies, DGF sea surface temperature anomalies, area average over the Nino 3.4 region, further confirms this relationship, as a strong positive correlation between the two has been obtained. And the mechanism
now, 2 more minutes.
Yeah. And the mechanism for the lag of several months is likely related to 3-4 months delayed response of Indian Ocean SSTs to ENSO. Now, this figure shows the scheme. This is my last slide. So this figure shows the schematic illustrating the physical mechanism associated with hot extremes. Well, in the recent period, the amplified geopotential height anomalies over the northern parts of India has caused the sinking motion, which has led to the surface warming, which in turn causes more hot extremes. Now, this sinking motion is allied with the reduced cloud cover, which has allowed more solar radiation energy to receive at the Earth's surface. That in turn leads to the surface warming, which in turn causes more hot extremes. In addition to this, the depleted soil moisture in the recent climate has led to the larger portion of sensible heat flux versus latent heat into the atmosphere, inducing a positive feedback between atmospheric heating and further drying of the soil, which has resulted in the augmentation of the near surface air temperatures, which in turn causes more hot extremes. So this paper has been recently published in scientific reports and has been outlined in many news outlets, more than 70 news outlets, including Times of India, Business Standard, and NDVA. Thank you.
Okay, thank you, Dr. Manish Joshi. So I don't see any question for you. I mean, you said the El Nino is partially responsible for the hot extremes, right?
Yeah.
How, I mean, whether that is El Nino responsible or the Indian Ocean warming is responsible?
Well, we have regressed the preceding DGF sea surface temperature anomalies onto the sea surface temperatures. So as you can see, there is a clear indication of ENSO over there. So that indicates that ENSO is providing a substantial forcing onto the hot days frequency. Though we are seeing a bit warming over the Indian Ocean, that too is related to the coupled phenomena of Indian Ocean and the ENSO through the Walker circulation. So that too has some influence on the hot extremes.
You can also explore that the ENSO response on the Indian Ocean is not stable.
Okay.
So the warming of the Indian Ocean continues for more time, especially the pre-monsoon period in the recent years.
Yeah.
So that could be primarily responsible for the extremes
Okay. Thanks for this session. I will
please look at that.
Yeah.
Otherwise, nice talk.
Thank you.
Thank you. Please stop sharing it.
Yeah.
So we now move on to the next presentation by Deepanshu Agarwal. He will talk on how well Indian high-resolution regional reanalysis represents extreme rainfall events over Northwest India. So Deepanshu, please.
Yes, thank you, sir.
Yeah, so please make it full.
Yeah, I cannot share my.
Yeah.
Yeah,
It was coming.
now
It was coming. Actually, it was coming.
No, it wasn't.
No, I
mine.
see.
It wasn't mine.
Oh. Then can you please fix that issue and we move on to the next presentation in the meantime? So you can fix it with them, with the organizers.
Just
come back. Are you try once again? See what you do. You click
yeah, I'm trying.
share screen.
Yeah, I'm not able to share the screen.
No. Please click.
The
Please
share
click
option
on the.
is disabled.
No. Click inside the box. There's a box there.
Okay.
Please click there.
Yeah,
Share will be active and click now.
Okay.
Yeah, it's coming.
Okay. Yeah. Okay, you can see the slide.
Yeah, we can see. Then please make it. Fine. Please go ahead.
So please stop me if the slides don't change. All right.
Yeah.
So, hello. So hello everyone. This is Deepanshu, and I'm delighted to present before you briefly some work that I did during my MS thesis at IISER Mohali. So as you can see from the topic, just a second, I'll take the pointer. So as you can see from the topic, we have used a high resolution regional reanalysis dataset to study the extreme rainfall events over Northwest India. So to set the context, I'll just give a brief background. So we are studying the Indian summer monsoon. And as we know that the monsoon is basically a seasonal reversal of the winds from northeasterly to southwesterly. And it marks the beginning of the rainy season over India, and which lasts for about 4 months. And India receives almost 60 to 90% of its annual precipitation from this monsoon. But as we know, there are high temporal and spatial variations in monsoon, and that's what makes it so interesting to study. So the extreme rainfall events associated with monsoon are a cause of concern because they generally result in flash floods, landslides, and loss of human lives and displacement also. So the simulations that are being conducted till now, they have shown that due to the climate change, we can expect an increase in the frequency as well as intensity of extreme rainfall events. But there are studies which say that models may overpredict the probability of these extreme events. So a proper assessment of the likely future trends of such events is critical for disaster preparedness as well as resource optimization strategies. So when we talk about Northwest India, it receives almost 50 to 75% of its total annual rainfall from monsoon. And we know that this region is also called the breadbasket of our country and has high population and intensive urbanization, which makes it highly vulnerable. Furthermore, the region is less explored till now, and the few studies that are available for this region have contrasting results. So that's why it is very important to study this region in comprehensive manner. So we have used a recently released monsoon data assimilation and reanalysis product by NCMRWF, and it has a high resolution of 12 kilometer over the Indian subcontinent. The upper image that I'm pointing, this is the spatial coverage of IMDA, and the below one is the preparation scheme of IMDA. So the objectives are summarized as like we first performed the scrutiny of IMDA over the Northwest India during Indian summer monsoon. So we studied how well it represents the rainfall characteristics as well as the monsoon circulation characteristics. Then we proceed on to study the trends associated with the mean precipitation as well as the extreme events. And then we'll proceed.
Yeah. So Deepanshu has some problem. See, he will connect it back. See, we move on to the next presentation by Shrutin Vijay. He will be talking on variability of extremes and floods over India. Shrutin, please. So, Dipanshu can join later.
Hi, sir. Am I audible?
Yeah, you are audible. Yeah. Yeah, please make it the PowerPoint mode.
So can you see my screen?
Yeah. Full screen. It's not changing to full screen. Can you stop sharing and then again start it again and click, you share the entire screen. Please share your entire screen. You can stop sharing now. There is a cross mark, right? See,
Is it visible, sir?
now you start. Share your screen. Click inside the box and share the entire screen. Yeah, good. Yeah, please go ahead. Yeah.
Hi, sir. Hi, everyone. Thank you for giving me this opportunity. The work I am going to share is my dissertation report, actually, which was done at IITM Pune under the guidance of Dr. Periyar Bhaskar. My topic is about variability of rainfall extremes and floods over India. I will give a
can you switch off the the YouTube channel from there, from your, so there is an echo if you are logging. Yeah. So please start. Yeah.
Okay. As we are well aware that the Indian subcontinent experienced an increase in frequency of extreme rainfall events and floods. In this report, a detailed investigation of the rainfall extreme and floods are carried out for Indian subcontinent as well as Kerala. Here, we investigate about the climatological spatial pattern and interannual variability of rainfall extremes and floods. So, in order to get the climatological spatial pattern and interannual variability, we need data sets. So, we have chosen from IFI flood database, which contains sources from DFO, EMDAT, and IMD. DFO is Dartmouth Flood Observatory, which contains the events from 1985 to 2020, and emergency database, which contains 2020. And we have the disasters weather event by IMD, which is from 1979 to 2019. The other data set we used for the rainfall extremes was daily rainfall data from IMD. For further investigation, we took the indices, rainfall indices like rainfall, which is the total rainfall during a year, and the count of the rainy days when precipitation is greater than 0.1 millimeter. The rainfall daily intensity, which is SDIA, which is the ratio of the total rainfall and the number of days. Then we have the 1-day maximum rainfall of a month and the 5-day maximum rainfall of a month. We are going to plot for all the extreme rainfall indices in order to get our ultimate aim on rainfall extremes data. So our aim and objective is just to understand the variability of rainfall extremes over India as well as Kerala, and variation of over India as well as Kerala. This is of the rainfall extremes. It is from 1985 to 2020. It's since climatology, it's about 35 years climatology. Climatological mean annual is plotted. Here we have the rainfall, which is our first index. This is R01 millimeter, which is number of days, which is our second index. They depict a similar spatial pattern as we can see around the west coast. See the similar spatial pattern, and on the northeast also. Then we have the other three rainfall indices, that is SDII, RX1 day and RX5 day. They also depict a similar spatial distribution. The first two will depict a similar spatial pattern, and the rest of the three depict a similar spatial pattern. Then plotted against the seasonally, that is January, February, pre-monsoon, monsoon, and post-monsoon. Here, indices of the rainfall extremes. Indices of the rainfall extremes during summer monsoon depict similar spatial pattern as that of annual rainfall indices. In June, February, we can see the plot that is on the north of the India. We can see more of the rain events, and summer monsoon, they depict the most extreme events, because we all know that during the summer monsoon, that is JJS, we can find more amount of events, thus by more flood and more extreme rainfall events. This is the annual seasonal plot. Then we have climatology, rainfall extremes. Annual cycle of indices of rainfall extremes for all India and Kerala for the period 1985 to 2020. The blue bar is the mean annual plot, and the piston-like red is the standard deviation. So India and Kerala is studied. So the left part is India and the right part is Kerala. For all India, 75% of the annual rainfall and 68% of the annual rain days occur during summer monsoon season. Like you can see the high bar being higher during JJS. Like see, June, July, August, September, they have the highest mark. For all India, 75% of the annual rainfall, like this part, 75% will be on the summer monsoon season. For activity peaks during July. You can see the annual rainfall is peaking during July for Kerala, for India. And for Kerala, 68% of the annual rainfall and 57% of the annual rain days occur during summer monsoon. Here also JJS, you can see the bar. Rainfall extremes has a primary peak in July. You can see the primary peak in July, and there's a secondary peak in October. Like it's decreasing and it's increasing in October. That's the secondary peak. Then we will discuss about the interannual variability. It's noted from 1901 to 2020. The rainfall indices, rainfall and the number of rainy days, you can see a declining trend in the annual and summer monsoon season. The blue line is the annual, and the red one is the monsoon season reading. So it's evident from the left first two figures that there is a declining trend in rainfall and rainy days for annual and summer monsoon season. And there is almost a similar trend in rainfall in this intensity indices, SDI, RX1 day, RX5 day. And large variability during recent decades post 1980 period. Then we will see the case of all Kerala rainfall extremes, and it's also from 1901 to 2020. It's almost similar and comparable to the all India extreme. There is, you can see the declining trend in rainfall and rainy day for annual and summer monsoon season. And there is similar trend in rainfall indices, intensity indices, the last three figures. And there is large variability during recent decades post 2000 period. After 2000, there is large variability in the rainfall extremes in all Kerala. Next, I will be talking about the flood events. So this is actually a spatial pattern. Spatial distribution of flood event for a pattern similar to that of rainfall. The heavy rainfall regions of West Coast, East Coast, Northeast India, and foothills of Himalaya seems to have large number of flood events annually. As we have seen in the previous slide, the rainfall extremes are mostly found at the west coast, east coast, northeast India, and foothills of Himalaya. So they also, I can say that rainfall extremes and floods have a connection actually. The summer monsoon season, which experience good rainfall activity, reports a higher number of flood events. So you can see the summer monsoon, which experience good rainfall activity, that is extreme rainfall activities, reports the highest number of flood events. So the colors here are severity classes actually. Class 1 is green in color, class 1.5 is yellow, and class 2 is red in color. So class 1, it's actually a large flood event with a recurrence period of 1 to 2 decades. And class 1.5 is bigger flood events where the recurrence period is between 2 decades and less than 100 years. And class 2 is an extreme flood event where the recurrence level is more than 100 years. So here is the annual pre-monsoon, monsoon, and the post-monsoon spatial plot is shown. So the next is the annual cycle of frequency of flood events over India and Kerala. The flood events are more during the summer monsoon season for all India as well as Kerala. You can see from JJS. JJS, the more events are more during JJS. It's applicable to India as well as Kerala. Increase in flood frequency from January till July, with a peak during July, and a decrease from July to December is seen from all India floods. You can see here, like there is peak during July and there is a decrease till December. For Kerala, two peaks are seen: a primary peak in July and a secondary peak in August, with January being the month with least frequency. The analysis thus suggests that variation in flood frequency similar to the variation of rainfall extreme over all India as well as Kerala. So the flood frequency of India as well as Kerala are comparable and are similar. Temporal evolution of frequency of annual flood events over India. Considerable increase in the flood frequency seen after 2000 for all India. You can see that the frequency of floods under the severity class 1 has decreased post 2000. Class 1 represents the a flood event which has a recurrence level of 1 to 2 decades. It's seen very rarely now. Most of the floods here seen here in the comes in the severity class 1.5 and 2. It is therefore noticed that the severity of floods has also increased along with increase in frequency of flood events over the Indian subcontinent. Then we are talking about the case of Kerala. Temporal evolution of frequency of annual flood events over Kerala.
2 more minutes.
Considerable increase in the flood frequency seen after 2000 for Kerala also. Frequency of floods has decreased for severity class 1 after 2000, and it's been increased for class 1.5 and 2 after 2000. It is therefore noticed it's similar to the India that severity of floods has also increased along with the increase in frequency of flood events over Kerala. Then it's the conclusion for floods. It's the summarizing the whole plotting and figures. Flood events follow a variability similar to that of extreme rainfall indices. Like indices of rainfall extreme, all India flood events has shown an increase from January to July with a peak in July and a decrease from July to December. Whereas for Kerala, the rainfall indices and flood frequency increases from January till July, with two peaks, a primary peak in July and a secondary peak in October, and January having the least frequency. Then there's a severity class thing. Severity class 1 has decreased since 2000 and 1.5 and 2 has increased nowadays. Then the conclusion for extreme rainfall events. The climatological spatial pattern of the rainfall indices follows similar spatial pattern distribution as that of summer monsoon season. The interannual variability of the indices of the rainfall extreme during summer monsoon depict a similar temporal evolution and are comparable with that of the annual indices. We have seen that in the figures and plots I showed. thus indicating that rainfall extremes of an year occur mainly during the summer monsoon season, as most of the events are found during the JJS period. Kerala region received a large amount of rainfall and experiences an extreme rainfall activity comparable to all India average. In spite of a declining trend in total rainfall and rainy days over all India and Kerala, and an increasing trend in the intensity indices are seen for all India. However, a large variability of the intensity indices are seen for all India as well as Kerala for the recent decades, particularly after 2000.
Thank you.
And scope for future. Sir?
Thank you. Thank you, Sudhan. I mean, we don't have, thank you for.
Okay, sir. Fine. Yes.
Yeah, and we don't have any questions in the chat box, but I have a question. So you said that from 2000 onwards, there is an increase in the higher intensity, the class 1.5, class 2 categories in these Kerala and India. So what is responsible for that? I mean, could you look at the possible reasons?
It's actually depicted from the data sets of DFO. From that DFO data sets have a column called severity, which shows the event severity. So that's
please look at the reasons, like what happened, why it's changing after 2000. So you can examine that. Okay, you can continue that work. Good.
Yeah, it's still on work, sir.
Yeah. Thank you.
Thank you.
Thank you, Shrudan. And we will now continue the talk of Dipanshu. Dipanshu, please join.
Yeah. Yes. Thank you, sir.
You can share. Yeah.
Yeah. So I'll resume my talk from where I left.
Yeah. Okay.
So the objectives of our study is to conduct a proper scrutiny of IMDA's performance during Indian summer monsoon, and we shall study the monsoon rainfall characteristics as well as the circulation characteristics to verify that. Then we'll proceed to the trend analysis of mean precipitation and the extreme rainfall events, and later on to gaining a physical understanding of the observed trends.
See, there is a tag in the tag in the bottom. Divanshu, see, can you press that? Yes, hide? So there is a.
Okay. Yeah, sure. Okay. So for the verification as well as comparing the results of IMDA with other datasets, we have used the precipitation datasets of IMD, TRMM, and we have also used the reanalysis data from ERA5. The ERE, the extreme rainfall events identification, has been done using POT approach, and we have used composite analysis to understand the synoptic configurations, and the significance tests of the trends has been done using the fit linear regression of MATLAB. So coming to the results, these are the climatological comparison of various meteorological parameters. I'll use the pointer. So the first one, the upper one, shows the surface temperature, and as we can see, the heat low over this northwestern region. Then below is the MSLP, that is the mean sea level pressure, and we can see the low pressure area over northwest India again. The below one is 850 hectopascal winds, and we can clearly see the southwesterly winds as well as the cyclonic vorticity over central India. Then the rainfall spatial variability is also well represented by IMDA. So overall, if we see the climatological patterns, they are well represented in IMDA. And in fact, due to the high resolution of IMDA, as I told, it has a high resolution of 12 kilometer. It also captures some small scale variation which are missed by other Corsair datasets. So this is the comparison of climatology, the daily climatology of IMDA with other datasets of IMD and TRMM, as well as the comparison of interannual variation. And we have got good correlation results of IMDA with both IMD and TRMM. The lowermost figure is the probability distribution of rainfall over northwest India. And as you can see, the blue line is for the range of rainfall captured by IMDA. And as we can see, IMDA captures the highest range of the rainfall, which is almost double the range of IMD. Then proceeding to trend analysis, this is the trend analysis of mean precipitation from 1979 to 2018. And from the spatial maps, we can see that over the northwest India, this is our region, over northwest India, we have homogeneous increasing trends, as well as we have some decreasing trends over the regions of eastern IGP, this is this one, and northeast India. And from the area averaged mean precipitation over northwest India, these are the line plots of that. We can see significant increasing trends from both the three data sets. Then the trend analysis of extreme precipitation events. From the spatial plots, again, we can see that our region of northwest India, it has significant areas which shows increasing trends, and most are even significant. And when we see the widespread extreme precipitation events, now the widespread extreme precipitation events were defined as the events or as the days when there were more than 10 extreme rainfall events over the study region. So if we compare these, the widespread events from the three data sets, we can see that there are increasing trends from both the three data sets. And IMDA shows a significant increasing trend of one event every 2 years, the increase of one event in every 2 years. Now, to understand the physical reasons behind these observed trends, as we know that the monsoon precipitation mainly consists of the convective precipitation. So we studied the convective variables such as the convective available potential energy, that is CAPE, and the convective inhibition energy, that is SIN, and specific humidity. So CAPE is a measure of atmospheric instability, and we can see the red one is from the trend from ERA, and the blue one is from IMDA. And we can see the rising trend in CAPE, and the SIN then corroborates this observation, and it shows a decreasing trend. Similarly, specific humidity shows an increasing trend, which means that the moisture content in the atmosphere during the monsoon is rising. Uh, then we have performed to see from where the moisture is coming to the northwest India and feeding these events. We have done a composite analysis of the days of widespread events and the normal days, and we have compared them. So as we can see that during the normal days, which is these B and E, the normal days, the northwest India receives a nominal moisture flux from Arabian Sea mostly. Okay, and for the widespread events, however, we can see that the cyclonic vorticity is enhanced over central India, and which draws more moisture from Arabian Sea as well as Bay of Bengal, and it transports it to the northwest India. When we compare IMDA and ERA, we can see that IMDA has less magnitude of this moisture transport compared to ERA. Then finally, we have, as we can, so till now we came to the conclusion that the convective precipitations, convective variables are indeed the one that are responsible for EREs. So we did a interparameter correlation analysis for both ERA 5 and IMDA to see who has the better correlations between these variables. And we, from the figures, it is clear that IMDA has higher correlations compared to ERA 5, which means it can better represent the physical linkages between the different variables of moisture availability, the atmospheric instability, and the convective precipitation. So the key findings can be summarized as follows. We performed an evaluation of IMDA, and the conclusion is that IMDA realistically represents the monsoon circulation futures as well as the spatio-temporal variation in precipitation during monsoon. Coming to the trends, we saw that the mean precipitation as well as the extreme rainfall events over northwest India are increasing, and we have significant trends for that. Furthermore, we saw that widespread extreme rainfall events are occurring in concurrence with the active spells over central India, because we have enhanced cyclonic vorticity during widespread events, which draws more moisture from the Arabian Sea and Bay of Bengal and transports it to northwest India. Later, also we analyzed the trends in convective variables such as CAPE and SIN, and from there we concluded that the atmospheric instability during monsoon is rising, which means the capacity of atmosphere to hold more moisture is increasing. Finally, when we did when we examined the interrelationships between the physical variables and EREs from both ERA 5 and IMDA, we saw that IMDA has better relationships between these variables, which means that it is quite suited to study such extreme rainfall events over Northwest India. So with that, I'll end. Thank you.
Thank you, Himanshu. I don't see any questions in the chat box. So you said there is an increase in moisture availability and moisture holding capacity, and in the recent years, right? So, and you
Yes, sir.
from what is the source? So could you see whether it is the increase is coming from the Arabian Sea or the Bay of Bengal? Do you make any statement?
So we didn't do that separate analysis for both Arabian Sea and Bay of Bengal, and because we have a continuous flow of westerlies from Arabian Sea to Bay of Bengal, and then they come towards Northwest India. So we didn't separate analysis, but can be a potential future topic.
Okay. Okay. Thank you, Divanshu. Yeah. I thank all the speakers.
Thank you,
so for giving informative talks. And I also thank my co-chair, Dr. KJ Ramesh. And so it was a wonderful experience. Thank you all. So now I hand over to the organizers. Thank you all.
We thank Dr. KJ Ramesh and Dr. C. Gnanasheelan for chairing the session. We thank all speakers and delegates and those who watched the session online and offline. There is an announcement. After the lunch break, the next session in Hall 2, Periyar, will begin at 2:10 p.m. Thank you all.
Thank you. Thank you.
Hello.
Hello. Yeah, hello. Good afternoon.
Good afternoon, Uma Mahesh, sir.
Yeah, good afternoon.
Sir, in this session, one more person is chairing with you, Dr. K.K. Singh from IMD. So he has not yet joined. If he is not joining, means you have to, please, you have to handle this session.
Yeah, he has.
Okay. K.K. Singh, sir, joined. Yeah. Hello, K.K. Singh, sir. Hello.
Hello.
Yeah. Good afternoon, sir.
Good afternoon, Dr. Vilas. How are you?
Your friend is here, sir.
Hello. KK Singh ji, namaskar.
अरे वाह मजा आ गया.
Great. See you. All the best.
Thank you.
Anand Sharma sir came physically, so
that is good.
Okay, sir. I was just briefing Uma Mahesh sir regarding the session.
Good afternoon, Dr. Uma Mahesh sir.
Yeah, good afternoon. How are you?
Fine, sir.
Sir, our moderators, rapporteurs will introduce chairs, then the lead speakers. After that, you can take over the session. So,
okay.
Like that.
Okay, fine.
Do we know the time division, Dr. Uma Mahesh sir, time division or
yeah,
time
that's
management?
What I was about to ask the same question.
Okay.
What about time? Like, what is the time for the keynote speakers, and also what is the time given for
lead, invited, and oral?
Yeah.
Lead talk speaker can take up to 25 minutes, including 1 or 2 short questions. It is up to him to take 25 minutes. He can take 25 minutes, but including the discussion time.
Okay.
Maybe
each 2 lead speakers, so each 25 minutes.
Yeah. No, sir. Total 25 minutes.
Oh, okay. Both together 25 minutes. Okay.
Then invited talk, total 15 minutes they can take, including 2 minutes question. Maybe 1 question can take. Yeah.
Okay, fine. Yeah.
There will be a lot of questions coming, but due to this tight schedule, we cannot address all of them.
Yeah, right. I understand. Yeah.
And then for short oral presentation, it is only 10 minutes. Maybe questions
10 minutes each.
We can ask the speakers to reply to in the chat box, like that we can ask.
Okay. Yeah.
So means
first speaker, Dr. Atrisa he told that he is traveling. He may not be joining. Then we can straight away go to Nagesh sir for the lead talk.
Okay.
So if Atrisa is not joining, means we have maybe 20-25 minutes extra, so we can utilize that.
Yeah. Miss, you said 25 plus 15 is 40. 40 plus 40 is 1 hour 20 minutes. Yeah. Total is 1 hour 20 minutes. Okay. So maybe we can give 25 minutes to lead because only one speaker is there. 25 minutes to the lead speaker. We can say 20 minutes, maybe 22 minutes and 3 minutes for questions.
Yes. Maybe he can take together 30 minutes because one speaker is already.
Okay, fine. Yeah. Okay, fine. Yeah. So now regarding timing, say in fact we'll maintain the time, or any one of your people also are maintaining time.
What's that? I didn't get you.
So time maintenance, like time management. Say is anyone from your side is going to monitor the time?
Our moderator will let you know, Chair. The time means if session is extending, they will.
Okay. Yeah.
And we need to give just a signal 2 minutes before in advance to the speaker.
Yes, sir. Yes.
Yeah, that's right.
So I hope you can manage well because there's no more briefing.
Okay. Yeah.
Thank you, sir. So now our moderators will take over.
Good afternoon, everyone. Welcome to the Day 2 technical session, TS3B of INTROMET 2021 on water resources, agriculture, and climate change. In this session, we have two lead talks by Dr. S.D. Atri, Scientist G and Additional Director General of Meteorology, IMD, and Professor D. Nagesh Kumar, Indian Institute of Science, Bangalore, followed by an invited talk by Mr. Raju Mandal, Scientist C, IITM Pune. After the lead and invited talks, we have 4 short oral presentations. The session is chaired by Professor N.V. Uma Mahesh and by Dr. K.K. Singh. Professor N.V. Uma Mahesh is from the Department of Civil Engineering, NIT Warangal. He holds immense research and teaching experience. His specialization is on water resource engineering. Dr. K.K. Singh is Scientist G from India Meteorological Department, New Delhi. He holds immense research experience on agrophysics and environmental sciences. The lead talk is for 20 minutes plus 5 minutes discussion. Invited talk is for 13 minutes presentation plus 2-minute discussion. And short oral presentation is for 9 minutes plus 1 minute discussion. We request the speaker to adhere to the time allotted. The selected questions in the chat box will be conveyed to the chairs by the rapporteurs. Now, may I request the Honorable Chair to kindly take over the session. Thank you.
Yeah, thank you. Good afternoon, all the participants, and welcome to this session on water resources, agriculture, and climate change. So, as part of this conference on climate change and on changing climate, I think this is an appropriate topic because I think one or two areas where impact of agriculture is felt most significantly are water resources and agriculture. So it's, I think, an important session. So as part of the session, we have 2 lead speakers. And as I understand, the first lead speaker, Dr. S.D. Atri, is not present at the moment. So we have Professor D. Nagesh Kumar from ISC Bangalore as the first lead speaker. So he'll be speaking on climate change and its impact on water resources of a river basin. Professor Nagesh. Professor Nagesh Kumar is there.
Sorry, sir. I think he has not joined yet. We'll contact him over phone.
Okay.
Go to the next speaker, sir.
Okay.
I had just one suggestion, moderator. In the meantime, please just tie up with all the oral speakers also. So, right. Thank you, sir.
Okay, sir. We'll do that. Thank you.
Okay. I'm sorry for this. I think Professor Nagesh Kumar also has not yet joined. So maybe we'll go for the first invited talk by Mr. Raju Mandal from Indian Institute of Tropical Meteorology, Pune. Hope Professor Mr. Raju Mandal is present.
Sorry, sir. He is also not present. We will contact him. Can you please go to Lauleen? She is present.
Okay. Fine. Then okay, we'll start the oral presentations first. So the first presentation is by Ms. Lauleen Chopra from University of Kashmir. She'll be speaking on assessing glacier recession and dynamics under changing climate in Kishtwar Basin, Western Himalaya. So welcome, Ms. Lauleen. Please stick to your time. You have 10 minutes time. So please try to complete your presentation 8 minutes, so the 2 minutes can be there for discussions. Okay.
I'll make sure I'm just not able to share my screen because it's disabled, I guess. I cannot see the option.
I think the organizers have to allow you to share the screen.
You can actually select and you can share the screen.
Which option do I have to select? I see no option to so that I can share the screen.
Yeah, she wants to share.
You might have emailed also their presentation to organizer or not, please.
No, I haven't. They didn't ask me to. I cannot see the option to share the screen. I have been using Zoom a lot, and I can see that option is not available here. Okay, now it's available. Yes. Yeah.
Okay, please
Hope
start
my
your
screen is
presentation.
visible now.
Yeah, it's visible. Go ahead.
So, good afternoon, everyone. Welcome to my presentation. My name is Loveleen, and I am a master's student at University of Kashmir. And today I'll be presenting my ongoing master's dissertation that is titled Assessing Glacier Recession and Dynamics Under Changing Climate in Kishtwar Basin, that is Western Himalayas. So, firstly, the outline of my presentation. So to begin with, I'll give a brief introduction about the glaciers and the climate change, then the study area, later methodology that I've adopted and the data sets that I have used. Lastly, and finally, the results and the conclusion. So the introduction. So we say that the glaciers are important as an indicator of climate change because physical changes in the glaciers, whether they are growing or shrinking, whether they are advancing or retreating, they provide a visible evidence of the changes in the temperature and the precipitation. And the rising temperature of the earth has without doubt been responsible for the melting of these glaciers throughout the history. And studies show that approximately 75% of the Himalayan glaciers are retreating, and that too at an alarming rate. So since 1900, glaciers are melting, and with the human activities being at the root of this phenomenon. And if we specifically speak about the Industrial Revolution, the gases, the greenhouse gases and the carbon dioxide have raised the temperatures. So there is an article in World Wildlife Fund, which is a study in 2019. It says that even if we curb emissions in coming decades, still more than a third of the world's remaining glaciers will melt before the year 2100. So next is my study area. The study area is Kishtwar, which is a rugged terrain. Its altitude varies between 3,000 to 15,000 feet above the sea level. The temperature in the region typically varies from -4 degrees Celsius to 25 degrees Celsius, and it is rarely below -9 or above 28 degrees Celsius. And this image on this slide shows a synoptic view of the study region with the glaciers that are present in the study region. So coming to the methodology that I've adopted and the data sets I've used, I've employed Landsat imageries for the glacier changes, and on-screen digitization was done to assess the recession and the debris cover on the glaciers from the year 2000 to 2020. Again, I've employed the Landsat data for estimating the surface ice velocity of the glaciers using the COSICOR software, which is a feature tracking method. And to understand these changes and these dynamics of the glaciers, the climate data, that is the mean annual precipitation and the annual temperatures, were analyzed to have a better understanding of these changes that are occurring at the glacier surfaces. So finally, results. A total of 155 glaciers were selected from the study region. And the area of these glaciers range between 0.57 to 55.59 square kilometers. And the glaciers suffered a loss of approximately 76 square kilometers, indicating a change of 7.05%. And this image here shows the view of all these 155 glaciers that were selected in the study region and the recession they have suffered, with a few zoomed in views to have a better visualization and a better view of this of these glaciers and the recession. And from the legend, you can see that the white and blue are the glaciers from the year 2020, and the orange part are the parts of the same glaciers from the year 2000. So the recession can be clearly seen in this figure. So next, this slide here shows the debris cover on the glaciers, from which the analysis is believed to have increased with a total of 26 square kilometers, indicating 16.91% change. And the area of the debris cover ranges from 0.0 0.03 to 21.29 square kilometers, indicating, and this layout here shows the snapshot of few of the glaciers, where the debris cover has increased. So to understand the local morphology of these glaciers, how the morphology of the glacier has its impact on the glacier itself, the glaciers were categorized into 4 categories on the basis of the size, and it was observed that the glaciers that are smaller in size have recessed faster than the glaciers that are larger in size. And also to understand the impact of debris cover on the glaciers were categorized into 2 categories, firstly being the glaciers that are covered with debris, and secondly the clean ice glaciers. And it is evident from this table that the debris covered glaciers are receding at slower rates than the glaciers that are clean ice. Next, the second objective of my study was surface ice velocity estimates of these glaciers. So from these 155 glaciers, a total of 20 glaciers were selected, and it was made sure that there is no bias while selecting the glaciers. So we categorize the glaciers on the basis of the size. So which means from each size category, from the 4, we had 4 size categories. So from the each size category, 5 glaciers were selected. 5 glaciers were selected, obviously on the basis of the size. So, and the results show that these 20 glaciers during the year 1999 to 2000 have a mean velocity of 23.99 meters per year. And for the year 2020 and 2021, the mean velocity decreased to 14.48 meters per year. So it is an average decrease of 39.64%. So this layout here shows the first layout is of the glaciers for the time from 1999 to 2000, and the second here is from 2020 and 2021. So this graph here shows the velocity of all these 20 glaciers that were selected on the basis of the size, and it is evident from this graph that as the size of the glaciers is increasing, like larger the glacier, the more is the velocity. So as the size of the glaciers are increasing, the velocity increases as well. So to ascertain the long-term climate data analysis, a time series data from CRU, the temperature and precipitation data from CRU, that is Climatic Research Unit, was used because the physical weather stations are very less, let's say very less in the area because it's a rugged terrain. So the data from the CRU was acquired, and from this data, it was acquired, it is observed that the mean annual temperature of the study is showing a statistically increasing significant trend. On the other hand, the trend in the temperatures, and on the other hand, in this graph that is of total annual precipitation, there is a increasing trend, but there is no statistically significant increasing trend. So I would like to say that there are few studies, or I can say 2 to 3 studies in this region that say that the precipitation has not changed significantly, but the form of the precipitation has changed. So there is less accumulation on the surface of the glaciers. So yes, they are. So when there is less accumulation, they gain less mass, and because of the rising temperature, they are losing more mass. So conclusion. In this study, we have examined the recession and SIB of glaciers in Kishtwar, Western Himalayas using Landsat satellite imageries from 2000 to 2020 under changing climate. And it was observed that the study region has witnessed a loss of 76 square kilometers of the glaciated area has been lost during the last 2 decades. And also the surface ice velocity has decreased, and the decrease is about 39.64%. Besides the warming climate of the region, the local morphological parameters also have a strong influence on the variability of these glaciers that was observed. And furthermore, it is evident that from this study that the glacier cover is declining, and if this trend trend in this glacier retreat continues, it may pose a threat to the water reserves of this region. And like I said before, that 75% of the Himalayan glaciers are retreating, and these retreats will increase the variability of the water flow to the downstreams and endanger the sustainability of the water in the world's most crowded basins. Thank you.
Thank you, Ms. Lauleen, for sticking to the time. Taken exactly about 9 minutes. Any questions from the participants?
Yeah, sir, there is no question in the chat box, sir.
Hello.
Yes.
Yeah.
Yes,
hello.
Hello. I am
Yeah,
Venugopal, director, former director from AP Groundwater Department. So, if his glacier retreat is going to affect Ganges flow, is there any estimate that how much it is going to affect the flows in the rivers which are depending upon the glaciers, sir?
So I don't know the exact figure or the estimates that you're asking about, but it is definite that at this rate, at which the glaciers are retreating, it is definitely going to affect the water resources. So yes, there will be less water for irrigation, for hydroelectric power generation, and all. Yeah.
So does the perennial rivers will become seasonal then? Can you have any study throwing a light on that?
I have not really focused on whether the perennial is going to be seasonal or not, because this is my ongoing dissertation. I am still working on it. Like I am adding more to it. So yes, I will take that point. I will surely look into it.
Thank you, madam. Thank you very much.
Yes, thank you. Thank you so much.
Okay, no more questions. Thank you, Ms. Lovely, for your nice presentation. So we'll move to the next presentation.
Sir, next our Nagesh sir is joined, so maybe we can.
Okay, yeah.
Sir, sorry for the inconvenience because last minute broke. Yes.
It's okay. Yeah. Hello, Professor Nagesh.
Hello,
how are you?
Yeah.
Yeah. Nice seeing you. Yeah. So I welcome Professor Nagesh Kumar. He's an expert in the studies on impact of climate change, climate change and water sources. So he's going to talk about the climate change and its impact on water sources in the river basin. So Professor Nagesh, you have around 25 minutes time for presentation and 5 minutes for question and answers.
Sure.
Okay. So I hand over to Professor Nagesh Kumar.
Thank you. Can one of you please confirm whether you can see the first slide on climate change?
Yeah, we can see. We can see. We are able to see it. Yeah.
Thank you. So thank you very much for giving me this opportunity to interact with the participants of this very important symposium. I'll be talking about climate change and its impact assessment on water sources of a river basin. I must first of all acknowledge my former student, Anandi, who is now faculty in Florida A&M University. She did her PhD, and I'm presenting a portion of her PhD, along with my collaborators who worked with us. Professor Srinivas was co-supervisor for her, and Professor Ravi Ranjundaya, former director IIT Pune, was our major collaborator in doing this work. So what I'll try to present, because many of you may be quite familiar with climate change, I'll run through that portion and try to focus more on how we try to assess its impact on water sources. As we know, it's a phenomenon that is happening. There are many causative factors, and economic development, global development, the population rise, technology that we are using, energy that we are using, and the way we are going for agricultural intensive agricultural activities, etc. So all these things will result in climate change. So IPCC, or Intergovernmental Panel on Climate Change, try to come out with plausible scenarios based on some boundary conditions, like CO2 doubling, temperature increasing by certain degrees, and by 2100. Based on that, they come out with some plausible scenarios or plausible pathways. And based on that, we try to run based on these boundary conditions, we try to run a general circulation model to get various hydroclimatic variables values as these scenarios evolve. And for that, we try to use general circulation models. And these are excellent as far as global climate modeling is concerned. They try to use all kinds of physics behind and try to do the modeling. And basically, we try to do it on some spatial scale, which we call it as a grid resolution or something. So here, when we talk about GCM output, which is pretty good for a global scale when we talk about the boundary conditions, modeling them, etc. But when it comes to watershed scale or a river basin scale, we may require this data at a finer resolution. And regarding the pathways or the possible scenarios that IPCC is trying to come up, initially they come up with special report emission scenarios called A1, FI, B2, B1, etc. And then they came up with RCPs, or representative concentration pathways. And presently, with the CMIP6, we are talking about SSPs, or shared socioeconomic pathways. They all have some kind of analogy or comparison. Okay, basically the boundary conditions, like how the warming is going to be in terms of watts per meter square by 2100. That being one of the major boundary conditions, or COT equivalent in ppm. We try to look at each of these pathways. Okay, and for each of these pathways, we try to run the GCM and get all the global climatic variables that are essential for hydrologic modeling. Now, as I said, one major problem with the GCM to the river basin scale, spatial scale, is that if I look at the GCM, a topography like this would have been approximated like this because of the grid resolution. So many things would have happened within that one grid box, but that's all treated as average effect of it in that grid box. And like that, if you try to look at typically the GCM is available at about 300 kilometer by 300 kilometer resolution. Whereas for hydrological impact studies, we try to have it at least at 50 kilometer resolution. And for urban hydrology, we would like to have it at 10 kilometer resolution, or if not for biological investigations, etc., we may want to have it at much finer spatial resolution. So to bridge the gap between the GCM and the impact studies spatial resolution gap, we try to bridge this gap through some downscaling. And that downscaling here, we try to do it through one approach, which I'll explain in a minute. So basically, when we talk about downscaling, what we are doing is, you look at these grid boxes or these spoiled dots that you're seeing here. These are the dots at which the GCM output is available. When compared to that, the small yellow portion that you are seeing here is the basin over which we want to study the impact of climate change. And because it is relatively small in size when compared to the grid boxes size here, we will have to find some relation between what is observed here versus what is estimated or what is simulated at all the surrounding grid boxes. And based on that, we develop a functional relation, which may be highly nonlinear, and use that as a nonlinear relation to find the value of a variable at this scale based on the value of the variable available at all these locations. So that's what we call it as statistical downscaling. Otherwise, we can go for dynamical downscaling, where we try to develop a regional climate model and utilize it. So I am trying to talk about statistical downscaling for my study that I am presenting today. So here, what we did is that to develop that nonlinear relation, we try to use support vector machine-based machine learning algorithm to develop this nonlinear relation. The major advantage of this is that although each one of the dependent variable may have a very small influence on the outcome, they can still be considered appropriately through this support vector machine. And I will not go into details of it, but this is a tool that was used for statistical downscaling. Then, the broad framework for that is that, first of all, we try to identify a predictant. For example, let's say the rainfall in my basin or in our river basin. And that rainfall is what are the factors on which it is dependent on as far as GCM output is concerned. Precipitable water, relative humidity, wind speed, what are the causative factors? And we try to find the relation between them, and whichever the variables that are meeting our threshold of minimum correlation coefficient. Okay, so all those variables are selected as predictors, and those predictors themselves will be related to each other, like temperature and wind speed, or wind speed and humidity. They could be related, and if they are related, then to overcome that redundancy, we try to use principal component analysis, and based on that, we develop the predicted principal components and utilize them for developing a statistical relation through SVM. Once the relation is established, we try to validate it using about 75% of the observed data that is available with us, and then validate it over the remaining 25% of the data. Once that SVM tool is developed for each of the predictors, then we try to use them for future scenarios. So that's the way this downscaling approach was developed using SVM. Now, this is adopted, or this is demonstrated here through one river basin called Malaprabha River Basin, which is part of the Krishna River Basin, and it is located in Karnataka state. Its area itself is about 2,564 square kilometers, which is very large for any river basin scale. But if you look at the grid boxes, okay, you see these blue dots. They are from the one particular GCM called CGCM3, Canadian General Circulation Model, 3rd generation. Okay, so those blue dots are quite far off when compared to the small area, which is about 2,500 square kilometers. And then if you look at these plus points, these are actually for the past climate, when we try to simulate them, okay, NCEP, NCAR try to provide this data at a slightly better resolution than this GCM, okay, but even then, this is also at a coarser resolution when compared to the area that we are looking for. So we try to use the functional relation between NCEP, NCAR data and these grid boxes, grid points, and we also try to do the relation between these CGCM3 points and the area that is of interest. So we try to consider about 6 cardinal variables, and for each of them, we try to develop this kind of functional relation using SVM. They are precipitation in this basin, maximum temperature, minimum temperature, wind speed, relative humidity, solar radiation. All these things will play an important role for water resource assessment in a basin. So these are considered as cardinal variables, and for each one of them, we try to obtain the downscaled value of this GCM output to any of these variables. So here we try to do it for example, if you try to look at the precipitation for the river basin, which is about 2,500 square kilometers, okay, we found by correlation analysis that these variables that are available from GCM are correlated. Temperature at 925 millibars, 700 millibar pressure, 500 millibar, 200 millimeter, all are temperatures at different pressure levels. Then geopotential height, specific humidity, zonal and meridional wind, precipitable water itself as one of the variables, and surface pressure. So all these variables were found to be influencing the precipitation at our basin. So these variables at all the surrounding grid boxes that I mentioned here, okay, so all these 9 points, they were measured, they were obtained from the GCM output, and for the past data available from GCM, we find the relation between that and the precipitation in our basin. precipitation observed from IMD or by IMD. Okay, so once that functional relation is established, we assume that the relation will hold good into the future. So for the future, for the next year up to 2100, for a given climate change scenario, we obtain these output of all these variables, use them to obtain the corresponding precipitation. In the same way, for maximum temperature, these are the influencing variables. For minimum temperature also, same variables. And for wind speed, these are the influencing variables, relative humidity, cloud cover, and stream flow I'll briefly talk about in detail. I'll talk about in more detail. So that's how we try to estimate or try to find out the predictors for each of the predictants and then use them in support vector machine tool to obtain the downscaled climate data. Now, first thing that I have to do is, when I'm talking about a few long-term future, let's say for about 100 years on a daily time scale or on a 10 daily time scale or some weekly time scale or something like that, then we have a large amount of data to be presented. So what we try to do here is that I try to present this data in the form of box plots for every 20-year period starting from 2000 to 2100. Simulation was done at a very fine scale, temporal scale, but the results are aggregated to show it to you on a 20-year period, how the climate is going to change as far as this particular basin is concerned for all the 6 cardinal variables. So as such, a box plot will try to show these portions. One is the mean value of simulations, and this circle, hollow circle, talks about the historical observed mean. Okay, and then this is a median, this is upper quartile, this is a lower quartile, and then the 95% quantile and 5% quantile. These are basically talking about the variance or uncertainty that is there within the simulation. So this is the kind of box plot that I'm going to show you. And here, let me start with one variable called relative humidity to describe what is there in this slide. Okay, so for the past data, we try to look at the observed values. We try to look at the NCEP NCAR data, and we also looked at the GCM downscaled values. So we have the observed rainfall data here. Okay, and NCEP NCAR data was statistically downscaled to obtain the precipitation, and the GCM data was downscaled to obtain the precipitation. You can also see the whiskers. Okay, so if you try to see that all these 3 hollow circles are around the same horizontal line, around 75, what does it mean? It means that relative humidity as simulated and downscaled from NCEP as well as GCM is very close to what is observed. That basically tries to talk about the confidence of the SVM tool that we have developed to simulate the past, that is 1978 to 2000. Okay, but once that is done, then that SVM tool was used for the future. So here for different scenarios, A1, B scenario, A2, B1, commit, etc. Their equivalents I have already mentioned if you talk about RCPs or socio SSPs. Okay, so if you look at this particular box plot portion, what it is showing is for every 20 years, okay, for A1B scenario, how is the relative humidity is going to change in the basin. So you can see this horizontal line, which is basically historical observed data for the past. So it will be one horizontal line. Okay, but this median line that you are seeing here, it is rising, indicating that the relative humidity over the period is going to increase. And the whiskers are also of a higher length here when compared to what we have here. That means as we go into the future, our uncertainty in simulating the future is also increasing. Okay, and that is for A1B. In the same way for A2 and for B1. For commit scenario, there's not going to be much climate change because that is already breached. The Kyoto Protocol is breached. Okay, so in that case, there won't be much change. Okay, and so this is the way we simulated GCM output and downscaled it to the river basin scale. And what I have shown you is for one variable called relative humidity. And the next variable is rainfall or precipitation. Precipitation only form it happens here in Malaprabha is rainfall. Okay, so here also you can see the first one is actually we have multiple rain gauges within the basin. So we looked at the Thiessen weighted polygons and then obtained the represented rainfall for the basin. That with NCEP downscaled and GCM downscaled, and all of them are very close to each other, indicating that we could talk about precipitation reasonably well for the SVM downscaled data. And if you look at the A1B scenario, as you can notice very clearly, the precipitation is expected to increase substantially over the 20-year periods. Okay, and that change or the increase is different as far as A2 is concerned. For B1, after 8180, it is expected to decrease. And the commit, you can see that's almost same, but slight increase around 40s and 50s. Now, what is interesting here is that the increase in precipitation, okay, but I want to put with a small disclaimer that the precipitation is increasing, okay, but what is also happening is the number of rainy days are decreasing. That means the intensity of precipitation is going to be very high. So if you look at the annual rainfall, you may see some amount of rise, which may not be very alarming. But if that happens in a very short span of time with high intensity, that's a major problem, which will result in floods and things of that kind. So that's for rainfall. Then we have maximum temperature. I'm not going through details because I have explained all these box plots in detail. Okay, and minimum temperature and wind speed. Wind speed, there is no much change for almost all the scenarios because this is actually on the leeward side of Western Ghats. So wind speed is not going to change much as far as Malaprabha Basin is concerned. We also looked at the cloud cover, basically based on the solar radiation information. Okay, and we try to obtain the cloud cover using that. So you can notice that the cloud cover is also is increasing, but the uncertainty is also increasing as we look into the future. So these are the 6 cardinal variables which are very important as far as hydrology or study of hydrology of the basin is concerned. Then we try to use other components that are required for hydrologic modeling. Land use, land cover information is required. We try to use remote sensing for that. And we try to stack all these layers of information using GIS. And digital elevation model was used to derive the drainage pattern. And all of them are finally put into one hydrologic model. And the hydrologic model that we are using here is called SWAT model. Okay, SWAT is a soil and water assessment tool. When it is floated on GIS ArcView, it is called AV-SWAT, ArcView SWAT. So the heart of it is SWAT model, but there is a good front end to deal with remote sensing, digital elevation data, and other ancillary data available from IMD, etc. And using that, we try to talk about watershed delineation. And within that, we try to talk about subwatersheds. And in SWAT, they are called, we try to further refine them to what we call as hydrologic response units. Okay, and they would be used to convert rainfall and other cardinal variables that we have downscaled to the runoff or the stream flow of the basin. So that's what is done. So as I said, we try to use remote sensing information to obtain the land use, land cover information. Okay, and this is in case if you are interested, we try to use IRS list 3 data merged with the panchromatic data to get the detailed land use, land cover information for this basin. And in the same way, the soil type or soil groups are obtained from remote sensing, but they're also collaborated with the information that is available from NBSS and LUP of ICAR. So that's soil groups were derived like that, again from remote sensing. And these are 2 very important inputs as far as hydrology is concerned to decide what is the curve number and how much would be the percolation, infiltration, things of that kind. Then this is DEM data. We try to use SRTM or shuttle radar topography mission elevation data available freely. And we used it for Malaprabha Basin and use that to derive the drainage pattern. The drainage pattern using one simple algorithm called the D8 algorithm. And this is a drainage pattern. The main advantage once we have this kind of detailed drainage pattern is that we can try to see, well, this is one point where a lot of water is coming, and this is like a pour point. So we can consider this as one sub-watershed, this is one sub-watershed, etc. Okay, so we can try to identify all those 4 points using our digital elevation data or model. And once we have this, then we can try to talk about the sub-watersheds or hydrologic response units. Okay, so they are shown here. And this is all done in the GIS. So on the sub-watersheds, we can also put the drainage pattern and land use, land cover pattern, soil pattern, etc., which would then help us to estimate what would be the runoff for a given rainfall. Okay. So once we do that, once we put this model in position, then we try to estimate the runoff. And that runoff, and this place, actually, there's one dam here called Malaprabha Dam. So at that dam, what is the inflow that is already observed is used to compare what is simulated through our SWAT model. And when these two compare well, we say that the model is calibrated. Until then, we try to fine tune some of the parameters of the SWAT model and keep playing around with those parameters. Once that calibration is done, then we try to use a portion of the data which was not used for calibration for validation of the hydrologic model. So these are the parameters that will go into for every sub-basin. How much is pasture, how much is water body, urban area, forest area, agricultural area, etc. And soil type, pixel by pixel we can count and try to provide the detailed information to the hydrologic model SWAT. Once that is done, then we try to simulate the runoff. We don't not only simulate the runoff, but we also try to estimate the lateral flows, the evapotranspiration, percolation, groundwater component. All those components also will be estimated through this hydrologic model. Once that is done, as I told you, we have the observed runoff or observed stream flow at the mouth of the basin up to the dam site. Okay, and that is compared with SWAT simulated flows. And when those two compare well for the validation period, okay, then we say that our SWAT model is ready to consider all the cardinal variables in inputs and to predict the stream flow. So that's when we try to use all the downscaled 6 cardinal variables from 2000 to 2100 and simulate the stream flow and prepare again similar kind of box plots that I have been showing. So here, first of all, for the past, and this is for different climate change scenarios. And as you can notice, because rainfall is increasing, there is a runoff or the stream flow is also increasing. And uncertainty is also increasing as we go into the future. So the bottom line is that for a given climate change scenario, by developing a good hydrologic model, and if required a statistical downscaling approach, we can simulate what is going to be the water source condition in the basin for a given climate change scenario. So that's what I wanted to say. And the same thing or similar thing, we did it for many other river basins in our country. So just to close this, that COP21 agreement. So we have a signatory to that, our country. So we have to look at what is proposed and we have to stick to that. And based on that, we have to see how our water resources or the crop water demands and other things are going to change due to these adhered policies. And then how do we adapt ourselves to manage our water resources and our natural resources in a more informed manner. That's all I wanted to say. So all these tools will be very, very effective for water resource management and water resource assessment in climate change scenario. So these are there are some books that are maybe of use to you. Just wanted to mention. Thank you. Professor Umesh, I'm done.
Thank you, Professor Nagesh, for your excellent presentation, and also you presented the gist of the way we take up the studies of impact of climate change on river basins. I think it's really great of you that you have complete this in 25 minutes, exactly 25 minutes. Thank you very much. I think we have some time for questions. I would like the participants, any participants to either unmute themselves and ask questions, or they can put the questions in the chat box and then ask questions.
Sir, can I ask one question, sir, regarding flows in the Periyar this year?
Yeah.
Yeah, sure.
Periyar is the driest basin in the country, sir. But for the past 3 years, we are getting good rainfall. But this year, there is a heavy rainfall, and most of the villages were inundated in the past 1 week. So there is a perception that in the people also that this may be due to the climate change. And this may continue in the future also. If it continues, it may be good for the Periyar basin because they receive more water than what they are getting now.
Yeah. I tell you, unfortunately, it is true for some of the basins in the sense that floods are a boon for downstream riparian states. See, even actually, if you want Nagarjunasagar Dam or Srisalam Dam to fill up, only way it can happen is that Maharashtra and Karnataka should get floods in Krishna River basin. Okay, so that is one problem that we are anticipating, that we are also seeing. Due to climate change, one thing that can be unequivocally said is that frequency of low frequency events is going to increase. It means that droughts will be more severe, floods will be more severe. And since we get them at such a short span of time, we may not be able to store them in 1 or 2 locations, and therefore the water will reach almost up to the end of the basin. I see that some people will try to see that as a kind of a boon. As a matter of fact, WMO, World Meteorological Organization, also suggests that flood should not be seen as a curse. Flood should be seen as a kind of a boon for better management.
So it is actually a boon to arid areas.
Yeah, I would say with a pinch of salt because someone is flooded.
Okay. Thank you, sir.
Any more questions from the audience? Okay, I think there are no questions. Thank you very much, Professor Nagesh, for your nice presentation, excellent presentation. Thank you very much. So I'll move to the next presentation, the invited talk by Mr. Raju Mandal from Indian Institute of Tropical Meteorology, Pune. Mr. Raju Mandal.
Yeah, am I audible, sir?
Yeah, you're audible. Welcome, Mr. Raju Mandal. Mr. Raju Mandal is speaking on implementation of IMD extended range forecast in the Kharif rice yield prediction on experimental basis.
My slides.
Mr. Mandal, yeah, it's visible. So you can take around 15 minutes time to make your presentation, and we can have some short discussions after presentation.
Okay, thank you, sir. And also, I'm sorry that I could not join on time because I am suffering from some health issues and I had a visit. Anyway, so today I'll be presenting on the implementation of IITM IMD extended forecast in Kharif rice yield predictions. This will be a case study. And I would also like to thank all the co-authors for contributing in this study. Slides will not move. Slides is not moving. Organize Am I audible?
Yes, sir.
Yeah, yes.
Okay, sorry. Slides were not moving actually. So for this study, we have chosen a study area over the Gangetic West Bengal because the economy and livelihood of this area, people of this area are vastly dependent on the rice cultivation. And majority of the crop area comes under the rice production only. And the majority of the crop growing area is under rain-fed ecosystem, especially the kharif rice, which is harvested usually during the Indian summer monsoon month. So therefore, to cope with the adverse impact of various extreme weather phenomena on the crop productions, development of a forecast crop yields model for forecasting system is necessary. And for this, the decision support system for agrotechnology transfer DSAT developed by the International Benchmark Sites Network for Agrotechnology Transfer provides a common platform for various crop models like rice models, wheat, maize, different type of models are there. So we have taken a serious rice model for this study. And there are different weather variables like precipitations, incoming solar radiation, maximum minimum temperatures that plays a major role for the crop models. So there is a possibility incorporating the weather forecast parameters. We can have a crop models and crop products, and that may be and the crop predicts. There are studies that they have shown that crop yield can be made at the beginning of the crop growing season and the latter stage through the incorporation of historical climatological parameters. And other studies also have shown the possibility of seasonal forecast products, which can be another alternative to use for these crop models as input. But a major drawback of the seasonal forecast is it provides a quantum of rainfall for the season as a whole. But the monthly and weekly variability of the weather parameters is not seen in the seasonal forecast. So there is the motivations that we can use the sub-seasonal forecast parameters for these crop models, and we can get a better, if we can get a better results using this year extended prediction system, then it will be very much useful information for the stakeholders and decision makers. So for this, so based on this, we have defined the objectives that this study examines the potential application of ERP forecast to the serious rice models to predict the kharif price over Gangetic West Bengal, and also to see the sensitivity of crop yield using the state-of-the-art ERP products over the climatological forecast. And if we can get a better result over the climatological forecast, then that will be a very much useful information for the community. So this is the study area, 1 degree by 1 degree box over this Gangetic West Bengal. So this is the 22 to 20 north and 88 to 89 east. This is a 1 degree by 1 degree box is shown. And for this study, we have used the observation data sets. That is, ultimately we have used over this box 1 degree by 1 degree box average over this box. Maximum, minimum, and precipitation data sets are obtained from the IMD, and incoming solar radiations are obtained from the Ceres NASA website. And for forecast data sets, we have used a multi-model ensemble prediction system that is indigenously developed in IIT. Now that is operational in IMD every week on Thursday.
Excuse me, sir.
Sorry.
Sir, your audio is not clear. Can you just fix it?
My audio is not clear.
Yeah, it is getting it is breaking in between.
It could be internet maybe. Is it okay?
Yeah, it's okay. It's okay, sir.
Yeah, for 2003 to 2018, we have the hindcast period 2003 to 18. So all the data sets are the crop models also ran for this period 2003 to 18. And for crop, we have chosen the rice variety, and 3 planting dates are chosen. That is 15th June, 1st July, and 15th July. And soil, we have chosen clay loam, and management data sets are chosen as per the local practice. So this is the IITM IMD extended range prediction systems. We have total 16 members, and we run for CFS 2 resolutions, T11060, T382, and GFS also with bias corrected, forcing with bias corrected. That can be seen in details in this study listed here. So before showing the results of crop models output, I'd like to show the skill of ERP in simulating the large scale rainfall. We have shown only the rainfall because this rice is mainly driven by the Indian summer monsoon rainfall. So where we can see, this is June to July 3 IC, June 13, June 17, and July 11. So for this 3 IC, we can see the bars are shown for the correlation coefficient, and the dotted lines show the normalized RMS. So from this we can see for almost all ICs, and for this is different weekly, week 1, week 2, week 3, week 4. So as the lead increases, the skill decreases, but still up to 3 weeks, it has a good skill. And the similar thing is observed also for the other ICs in July, August, and September, October. So that gives the confidence to use the sub-seasonal forecast, ERP forecast for next 28 days in the crop model. And this is also shown the anomaly pattern correlations averaged over this box, 10 to 35 north and 70 to 100 east for this incast period. So here also we can see almost from all ICs up to week 4 lead, it has a significant scale. That means it could capture the spatial pattern of the rainfall over this region. And this is the bias, mean bias, shown over this period 2003 to 18, and the rectangular box shows that hatch box shows the study area. So we can see over the study area bias is very less, but in other parts bias is present. That is somewhere it is positive, negative. So for this we have used the ERP forecast after correcting the mean bias. And this is the forecast strategy. We have taken 3 strategies. Strategy one is observe. We named it as observing. And for this, we have used the 2003 to 18 all the real-time daily data sets. Simply real-time data sets for 2003 to 18 to run the crop. That is strategy one. Strategy two is ERPF. That means up to today, there will be real-time observed data sets, and from today to next 28 days, 4 weeks, it will be a bias corrected ERP data sets. And after that, it will be rest of the year's data set, daily data set will be based on the long-term climatological data sets. So this is ERPF. That ERP data sets for 28 days from today's initial conditions, next 28 days will be merged in between. And strategy 3 means up to today, it will be a today it will be a real-time observed data sets, and after that it will be all climatological data sets. So that will be a CLIME-F. This crop model driven by these data sets we will name as a CLIME-F. And we have chosen different forecast window as season progresses. So for 15th June planting dates, we have chosen the nearest initial condition 13th June. So up to 1st Jan to 30th June, it will be a real-time observation data set. 14 to next 28 days up to 11th July, it will be our ERP bias corrected data sets. And after that, the rest of the years, it will be climatology. So forecasting window 2 means again after 1 month, 28 days, again we incorporate the ERP forecast for 28 days. And like that for the whole season, we have chosen 4 forecasting window. And similar to the all planting dates, 1st July and 15th July as well. So based on this input data sets, 3 strategies obtained for different forecasting window, we have run these models, the rice model, and we have got this rice yields. This is kg per hectare listed here. This line shows the mean, and the next line shows the standard deviations, and for different 3 planting dates. And the rightmost column shows the observations. As I said, strategy 1. And this one is CLIME-F, and this is ERP-F. Here we can have the sub-seasonal predictions, outputs, impact of this sub-seasonal forecast. So from this, then board line shows the better skill as compared to the climatological with referred to the observed one. So most of the cases we can see the ERP performs better than the climatological driven model. And this also shows the root, normalized root mean square error and the correlation coefficient with respect to the observations. We have shown the ERPF driven model as well as climatological driven model for a different forecasting window. That means incorporating different initial conditions for the whole seasons. So as we can see in forecasting window 1, both the models shows less skill, but for next 3i forecasting window, the ERPF's driven model shows the better skill as compared to the climatological one. That means the ERP driven model could capture the interannual variability of rice yields better than the climatological, especially for this planting dates 2 and 3, 1st July and 15th July. And after the forecasting window 2 to 3, the skill has improved for this ERPF. And we have studied another categorical yield forecast. That is, we have categorized the forecast in 3 different categories, like below normal, above normal, and normal categories based on the tarsile method. So 1/3 greater less than 1/3 quantile means a lower tarsile. If the values are less than lower tarsile value, then it will call it as below normal. And if it is greater than 2/3 of the quantile values, it will be above normal, and in between it will be normal. So 3 categories are analyzed. And based on the 2x2 consistency table, we have calculated the probability of detection. That is nothing but the hit rate, false alarm rate, and the threat score. So 3 different skill scores are analyzed. So this figure shows the POD and FAR and TS for different planting dates. That is 15th June, 1st July, and the last row shows the 15th July planting dates. So the red color shows the below normal category, blue shows the normal category, and green color shows the above normal category. Hollow bars shows for climatological driven model, and solid bar shows the for ERP driven model outputs. So from this different forecasting window, we can see especially for the below normal and above normal category, ERP driven model performs better than the climatological one. But for the near normal category, the ERP has not that much superior skill for the normal category. So for the decision making and stakeholder point of view, the above normal or below normal, that is that type of anomalous forecast will be much more useful than the normal one. So in that way, we can interpret the impacts of the ERP driven models output. So in summary, we can say the ERP driven crop models has shown reproduce, observe mean and variability much better than the climatological driven model. And also changes in statistics of yield with the planting dates have been better predicted by the ERP driven models. And ERP driven model captured the interannual variability of varieties better than the climatological one for the 1st July and 15th July planting dates. However, the performance have been poor for the both forecast in case of forecasting window 1 in the beginning of the season in June, you can say. And then after that, the skill have been gradually improved for the ERP1. And for the categorical forecast also, ERP driven model shows better skill over the climatological one. So, stakeholder points of view, as I said, the anomalous events, that is below normal or above normal, will be much more useful information for them to make their decisions. But there are lots of limitations in the study. This is only one case study over a particular region and for a particular crops, that is rice. So that our goal is to extend this work for other regions and for other crops also, to see the robustness of this ERP driven model and the potential applicable applications of our products before implementing in operational mode, and to have the better forecasting systems. The effort is underway. So I would like to thank the organizing committee for giving this opportunity, MOES, Director ITM, and the former and present Deputy Project Directors of ERPS Group of ITM, and different data centers for providing me the inputs, the observed data sets, as well as to running the model, the initial conditions and all. So thank you for your kind attention.
Thank you, Mr. Raju Mandal, for an interesting presentation on the use of this extended range forecast on, say, forecast of rice yield. And thank you for sticking to time. Any questions from the audience, from the participants?
Sir, we have got doubt for the long time, sir, about long time. Regarding this global precipitation from GPM and actual rainfall on the land. So what are the causes, sir, for difference between this precipitation from the GPM and actual rainfall on the land? Is there any correction factors that we can apply on this? Because if we take the GPM values, they will deviate from the actual values we have got in the field. So, what is the reason for this?
You are talking about the GPM observed data sets, satellite data sets, and the ground station data sets that IMD provides.
Hello, Mr. Venugopal, can you clarify the question?
So we have taken earlier, we used to take when we were in the department precipitation from GPM, sir, global precipitation models, but they used to differ from the actual values on the field, and they are prone to certain errors when we calculate it in the field in realizing the soil moisture, runoff, and other things. So is there any causes for this difference between GPM and the actual rain in the fields?
Yeah, I understood your concern, but the thing is, we are just using the IITM output, means final products. We are also of IITM data sets. So they can, the IMD people can tell better what are the difference they are observing and what are the methodology or they are to calculate the merge data sets or station data sets.
Okay, sir. Thank you, sir.
Any more questions from the audience? Okay, if no more questions, thank you, Mr. Raju Mandal, once again for the nice presentation and in fact, a very interesting presentation. Thank you.
Thank you, sir. Thank you.
So we'll move now to the remaining oral presentations. There are 3 more oral presentations. I now invite Dr. Surendra Pratap Singh from Indian Institute of Tropical Meteorology, Pune. Dr. Surendra Pratap Singh?
Sir, he's not present.
Okay. Then the next presentation is Dr. Venugopal Karnool.
Yeah, sir. I am here. Yeah, I am present.
Yeah, fine. So welcome, Dr. Venugopal Karnool, and I will be presenting on uncertain rains, river flows, and interbasin transfer for meeting water scarcity in climate change. Dr. Venugopal, say you have 10 minutes time to present your presentation.
Okay,
so
sir.
request you to complete it in that time.
So can I start now, sir?
Yeah, I can start.
Okay, sir. Screen. So is it visible, sir? Present this first
Yeah, it's
slide.
visible. It's visible.
Yeah. Yes. So my concern is about the uncertainties of the rainfall because of this climate change. And we, as a practitioner, as a water manager, we used to face a lot of problems during the droughts and floods and spatial distribution of rainfall in space and time. So I have studied in the different basins, what are the causes for this droughts and what are the causes for this floods and uneven distribution of rainfall. And even if there is a surplus in some areas and they store water, but they do not release the water downstream areas and they hold it tight. So because there is some lacunae, gaps in the water management as of now, that gaps have to be filled so that we can have the better use of the water resources. So I have studied in the mostly in the Krishna basin, sir. Krishna is a deficit basin as of now, and like Kaveri, most of the water is being utilized in the Krishna basin. In the past decade, except for the last 3 years, there is a meager flows into the sea. In some years, there are no flows into the sea in the Krishna basin, and because there are a lot of riparian states, it cuts many administrative boundaries like Maharashtra, Karnataka, AP, Karnataka, Telangana, and AP. And because of these administrative boundaries, whatever water they got from the upstream areas, like in Western Ghats, because of the good rainfall, they hold it tight until they get floods and they get very heavy rains, and they have got no option to release the water to the downstream side. So this is causing some skewed water management that I am going to discuss now, sir. So interbasin transfer. So this is so these reservoirs along the Krishna basin are situated in under different conditions. In Western Ghats there is a heavy rainfall. So because of the slopes and geomorphological conditions, there is a heavy runoff from the Western Ghats, and most of these rain shadow regions are situated between this Bay of Bengal and the Western Ghats, and most of the diversion, most of the interbasin transfers are taking place in this rain shadow region. And here this is the crux of the problem. When there is a surplus water, like in Almaty, they store water, then they release the water to the Narayanpur, then they release the water to Jurala, then to Srisailam, and they hold it tight. They hold it tight until they are absolutely sure that there are floods. Then only they open the gates. And when there is a long period ahead for the southwest monsoon, they are not releasing the water to the downstream side. I mean, downstream sides like in Srisailam, lot of these canals are taking to this rain shadow regions to serve this irrigation and the drinking water needs. Because by the time water is released from the upstream areas, the crops are withered in those regions. Instead of that, if they can release the water, means keeping the time ahead for the southwest monsoon, that is going to save a lot of water, save a lot of these crops which are withering, and also for the people suffering from the drinking water. So water resources, particularly those serve the interbasin, has to look upon this issue of availability and scarcity in a holistic manner. Good forecast system must be in place so that there will be some certainty. There will be even if there is some certainty, the water management perspective has to be changed. Instead of this allocation on a static basis, they have to allocate on the dynamic basis, on the basis of the water resource position during this particular monsoon season. So this is the peninsular India. So we can see that most of the rain is received in the Western Ghats. All the major rivers like Godavari, Krishna, Kaveri, and Pennar, they take their origin from the Western Ghats. So here they receive a lot of rains, particularly in the Upper Krishna Basin, and in Pennar Basin there are no rains, and it is a drought-prone area. Most of the catchment area and the upstream, it is a drought-prone area. But in the past week, this season, we are seeing heavy rainfall. Maybe the earlier speaker has told that this may be attributable to the climate change, and floods also we have to look upon as an opportunity in such areas, because in climate change some of the basins are going to benefit and they get more rainfall than what they are getting during earlier periods. So Pennar is one such basin. We hope that climate change is going to give prosperity to the Pennar Basin, because in Pennar Basin they may receive more rainfall, and already there are good structures in place to conserve this water, and this is going to help in the long term, sir. And another point is here IMD data shows that highest rainfall. So 2 years back, I think in 2019 or 2020, highest rainfall in the world is received in the Mahabaleshwar. It has overtaken in that year even the Cherrapunji also. I think that in that year they have received about 10,000 mm of rainfall. But on the leeward side, rainfall is very less. And as you travel from leeward side to the Bay of Bengal, after certain distance, most of these rain-fed areas are being situated, where they need more water through the interbasin transfer of the water resources. And Krishna is one such river where where every drop is being utilized, and both sides of the Telangana and Andhra, they are competing for the meager water resources to take to their drought-prone areas to meet the needs of the crops and also the drinking water needs. But on the other hand, in Godavari, nearly 300 to 4,000 TMC are reaching the sea, because it is not like in Krishna. It is born in the Western Ghats. As it travels towards the Bay of Bengal, because in higher reaches in the Western Ghats, it receives more rainwater. It is more useful than the Godavari, which is most of the water is received from the Chhattisgarh area in the short run. So most of the water is going to the sea. So now they are planning a Polavaram project, and also in Telangana they have plans to utilize more Godavari waters in the future. And also Godavari is the potential area. And Tamil Nadu also, they wanted to take water from the Godavari to meet their drinking and other needs in the Tamil Nadu. So these interstate conflicts and the discussions are going on to utilize the surplus Godavari water. So meanwhile, so most of the rivers like Krishna, Kaveri and Penna, they are utilized to the potential, and Godavari we have got the opportunity to use because there is a surplus water in the Godavari through interbasin transfer of the Godavari rivers. So whatever shortfall is there in other basins like Krishna, Kaveri and Pennar, they can be made up. So, as you know, this Telangana is situated on the left side of the Krishna bank, and Andhra is situated in the right side of the river bank. There is a competition. There are more conflicts going on for the sharing of this water. And Bachawat Committee and our Krishna Commission is there. So, this conflicts, because of these conflicts, this water is not being utilized properly because of the lack of understanding, a holistic approach of the availability of the waters. So many water resources systems, especially characterized by institutional independent decision makers, they think that in idealistic approach, but they may not be realizable in the field. Perspectively is conceptually interesting to quantify the best achievable performance, but might have little practical impact given the real political and institutional setting because of the electoral politics and other things. So they wanted to have this conflicts. They keep the conflicts going on because if they can yield because they may going to lose the votes like that. It is all looked upon from the perspective of staying in power. So this holistic approach is needed in the river basin management. So the disputes and water sharing are running for years. So they are running for years, not yet resolved, without a thought for a timely water sharing to achieve more water use efficiency, forgetting parochial feelings. The author has, so we have discussed this in the rain response releases in the Krishna Basin in one of our papers presented in the international conference in Roorkee, and this is also published in the Springers. So if you see the Krishna River, so earlier in 1901, huge water is going into the sea because of the dams, major dams constructed across the Krishna, like Almaty, like other dams, Narayanpur and Vijurala, Srisailam, etc. So very little water in sometimes in drought years, in scarce rainfall years, little water is going into the ocean. But in the last 3 years, what we have observed is nearly 300 to 400 TMC of water reaching the sea. And in this year also,
Dr. Vedagopal, I'm sorry to interrupt you. Just please, you have another 1 minute to conclude.
Okay, sir. 500 TMC of water has reached sea. So whether this can be attributable to the climate change or not, we have to study. So this is the story about the Krishna Basin. And surface and groundwater is mostly dependent upon the monsoons in the peninsular India. A good monsoon will give a good groundwater rise in groundwater levels and also good surface water in the reservoirs. So we are depending on the monsoon. Whether this monsoon, how it is going to be affected due to the climate change, that is an interesting story we have to study, sir. So in summary, El Nino effects are there, and also Internet of Things are there, and also good forecasting system is there. With all this technology in place, I think that in future we are going to have a better management system, and availability of water will also be more in peninsular states because of this climate change. So how they can use this water, how can they use better for crops and also industry, and also for the meeting the drinking water needs. This is all my presentation, sir, today's seminar. So I thank the organizers for giving me this opportunity to present this paper on these uncertainties, which are interdepending upon the climate change. Thank you very much, sir.
Thank you, Dr. Vedagopal. So your presentation on the need for the interbasin river transfers.
Yeah.
So any questions? Okay, if there are no questions, I can call the next speaker, Dr. Anjani Kumar from ICAR.
Good afternoon, sir.
Yeah, good afternoon, Dr. Anjani Kumar. Welcome. And Dr. Anjani Kumar will be presenting on linking nitrous oxide emission and functional soil microbes from rice soil exposed to elevated carbon dioxide, a modeling approach. Dr. Anjani Kumar, you have 10 minutes time to complete your presentation.
Okay, sir. Thank you, sir.
Thank you.
Sir, my slide is visible?
Yeah, it's visible. It's visible.
Okay, sir. Good afternoon, one and all. Myself, Anjani Kumar, scientist at ICAR National Rice Research Institute, Cuttack, and today I will be presenting on the topic linking nitrous oxide emission and functional soil microbes from rice soil exposed to elevated carbon dioxide, a modeling approach. Now, coming to the rice scenario, we all can see that it plays an important role in India as well as the global economy, as it feeds around 65% of the Indian population, and it is grown by around 56% of the farmers, and it is a livelihood to around 40% of the poor people of Indian population, and its annual value is around $53 billion. And it also utilizes around 37% of the total chemical fertilizer used in our country. And it also emits around 18% of methane emitted from the agriculture. Thus, it is true to say that rice is the backbone of Indian as well as the global economy. Here we can see that the per capita water availability is decreasing, And in the year it was around in the year 2011 it was around 1545 cubic meters, but in the coming years it will further decrease, and by 2050 it will be around 1140 cubic meters. And we all know that our population is increasing at a faster rate, and with that less water we have to feed our growing population. And here we can see that this is the traditional way of growing the flooded rice, but due to the scarcity of water, due to the scarcity in the availability of irrigation water for rice growing, we have to change our approach, and we have to grow rice like this. It means we have to grow rice like wheat or maize. That is, there is no need of maintaining flooded water in the rice field. And keeping the scenario of the water scarcity in mind, we have to shift from the flooded rice to the non-flooded rice, and this is the only solution to feed our population, to feed our growing population in the time of the scarce water availability for the rice sector. And here we can see that in a paper published in a reputed journal, here it was shown that when rice was grown under aerobic condition, that is non-flooded, where no water was maintained in the field, the water productivity was increased. That is, the water required for growing a unit rice, it means for the water required for growing 1 kg of rice, the water requirement was less as compared to the traditional method of growing rice. Therefore, this aerobic rice, what we call the terminology aerobic rice, is a tested concept for maximization of water productivity. In other words, we can say more crop per drop. Then how the rice crop is going to be affected in the scenario of the elevated, in the anticipated elevated CO2 condition. And here we can see that the atmospheric CO2 concentration is increasing, and by around 2050 it will touch around 700 ppm, and by 2050 it will reach around 1000 ppm. As we all know that rice is a C3 plant, the CO2 saturation point of rice is around 1000 ppm, whereas the other C4 crops like maize, they have the CO2 saturation point of around 350 ppm. Therefore, it is expected that in the futuristic condition of the elevated atmospheric CO2 condition, the rice crop is going to be benefited. Then how it is going to be benefited, that a work was done and it was published in a reputed journal like Field Crops Research. It was shown that when rice was grown under ambient condition and under flooded condition, as compared to the elevated CO2 condition and under flooded condition, the yield increased around 14%. And when it was grown under ambient condition, that is the present atmospheric CO2 condition, when the rice was subjected to water deficit stress, the yield was declined up to 33%. But when the same rice crop, rice variety was grown under elevated CO2 condition, maintained at 550 ppm, the yield decline under water deficit stress was only 17%. It means that under the anticipated CO2, elevated CO2 condition, the effect of drought stress on rice is going to be minimized. And here we also see that there was an increase in the water productivity. Under well-watered condition, the increase was only 29%. But under condition of water deficit stress, the increase was 46% under elevated CO2 condition. Then coming to the research progress, what people have already done, that they have reported that under water deficit stress condition, there is a decrease in the microbial activity, there is a decrease in the nitrous oxide emission, there is also a decrease in the methane emission. But when the stress of combined stress of elevated CO2 and water deficit stress was given, then the water productivity was increased, the microbial activity was also increased, but there is no report telling that what would happen to the nitrous oxide emission and the methane emission from the rice field when they are exposed to the combined effect of elevated CO2 and water deficit stress. Therefore, we planned our experiment under split plot design under 3 CO2 levels, that is the ambient CO2, that is 400 ppm, elevated CO2 550 ppm, and elevated CO2 another level 700 ppm, and the experiment was conducted under open top chamber, where the elevated CO2 conditions were maintained by purging CO2 from outside cylinders. And also the 3 nitrogen levels were taken. There are no nitrogen at as control, and nitrogen at the rate of 100 kg per hectare, nitrogen at the rate of 150 kg per hectare. And the moisture conditions was, one was well watered, that is the traditional method of growing rice, and the another plots were kept under water deficit stress, that is minus 60 kPa, and if the stress was measured by the help of tensiometer installed in the field. Then our results showed that under elevated CO2, there was a decrease in the nitrifier population, whereas there was an increase in the denitrifier population. And both these conditions stimulated denitrification, and hence there was an increase in the nitrous oxide emission. And we also found that there was a decrease in the ammonical and nitrate content and nitrogen mineralization, whereas there was an increase in the microbial biomass nitrogen content. And about yield, we found that the yield was increased under elevated CO2 condition, under higher nitrogen dose, and under well-watered condition. And then coming to the nitrogen use efficiency, it increased under elevated CO2 and also under well-watered condition. Then coming to the nitrous oxide emission, we found there was an increase in the nitrous oxide emission under elevated CO2 condition, whereas the increase under high application of higher dose of nitrogen, the nitrous oxide emission was again increased, and it was also increased under well-watered condition. Then for understanding the interactions among the different parameters, we did the generalized linear mixed effect models using the R software, and we found that under maximum filtering stage of the rice growth, this equation was best explaining the N2O emission, and the RO square was around 0.98, and under panicle initiation stage of the rice growth, the equation was like this, and again the R square value was 0.96. Then we also did the principal component analysis for representing a low dimensional graphical spatial plot of multivariate data using the R software, and we found that under ambient CO2 condition, the nitrous oxide emission was higher under panicle initiation stage, and positively correlated with nitrogen mineralization, nitrifier, and denitrifier population. Whereas with increase in the atmospheric carbon dioxide concentration, and the highly positive correlated parameters were under panicle initiation stage were nitrifier and denitrifier population. And then we also did the PLS-PM modeling approach, that a partial least square modeling approach, to discriminate the direct and indirect factors influencing the nitrous oxide emission. With increasing CO2, the influence of microbe on nitrous oxide emission and the nitrogen mineralization increased. It is very clear from the graphs. And whereas the influence of nitrogen mineralization on nitrification potential was decreased. And the influence of different forms of nitrogen on nitrous oxide emissions showed a negative trend, with increase in the CO2 concentration, which might have affected the denitrification rate under elevated CO2 levels. And this model revealed that microbes, basically the nitrifiers and denitrifiers, directly affect N2O emission, and the effect was more pronounced than the elevated CO2 concentration as compared to the ambient CO2 level. And then coming to the conclusion, we conclude that under elevated CO2, it mitigates the effect of water deficit stress through soil enzymatic activity and a grain yield. And it increases the nitrous oxide emission, and the higher nitrous oxide emission was found at the vegetative stage, and the increase in nitrous oxide emission was due to the higher nitrifier population and the lower denitrifier population in rice soil under elevated CO2 conditions. And these are the future research work which people can take up. And I am thankful for my director and ICR NASA for fund support. Thank you.
Thank you, Dr. Anjali Kumar, for the nice and interesting presentation. Any questions?
There is no questions in the chat box.
Okay. Now, do we have Dr. Surendra Pratap Singh, one of the presenters who was supposed to present?
No, sir. He also conveyed his inconvenience by late.
Okay.
Yeah.
So I think with this, I think we come to the end of the presentations then. So we had an interesting session. We had a lead presentation, presentation by Professor D. Nagesh Kumar, who talked about the impact of climate change on the water resources. And he just gave explained how to model the impact of climate change on water resources in the river basin through a case study of river basin. And we had an invited talk by Mr. Raju Mandal, who in fact gave an interesting presentation on the usage of IITM IMD extended range forecast on prediction of Kharif rice yield. And then we had 3 presentations in the for oral presentations. The first one was Ms. Lauleen Chopra, who talked about say the recession of glaciers in the Himalayan regions because of the climate change, and a study that they have undertaken. And we had Dr. Venugopal, who spoke about the need for interbasin transfers because of the the uncertainty in rains and flows in rivers due to climate change. And the last presentation was Dr. Anjali Kumar, who talked about nitrous oxide emissions and then the functional microbials and due to the exposure of elevated carbon dioxide to rice, a model study that they have done. I thank all the presenters for maintaining time in their presentation. Thank you. Maybe I request Dr. K.K. Singh, my co-chair, to maybe give a summary of the session.
Thank you, Chair Dr. Mohammed Saab, and thanks to organizer to invite us to make us part of this important session, very important session as mentioned by you. And in fact, there are 2-3 papers which results really needs appreciation, and also to be part. I mean, such kind of output of the such study. Say our invited talk, lead talk from Professor Nagesh, and then another one is the assessing. By Dr. Venugopal. So this is relevant for to be included in the policy decision also while preparing the policy, not only at the national level but at the regional level also. So these studies are very, very important from that point of view, from regional perspective. And from Dr. Raju Mandal. So in fact, he mentioned about the 3 to 4 weeks forecast application. While we look from the farmer's angle, then definitely whole season forecast is also required. Otherwise, it will confine up to the tactical management with the lead time of 3 to 4 weeks. So we hope that Raju Mandal will extend this study using seasonal forecast also to allow that to trade off between the kind of yield target with a yield target set as well as the viable management package to achieve that target. But it's a very good study he has made with other colleagues in IITM. Lauleen Chopra, yes, that is another very good presentation, and of course she made the impact. She presented the impact of morphological character of the glacier on its recession and dynamic recession. But the area, I mean, recession in terms of the melting or is area spread, but also the mass study has to be done. So that may be the further expansion for her work. Then last one is the Anjani Kumar. Yes. Again, there is such kind of studies are very, very important. From very, very important. We are moving to the anaerobic from anaerobic condition to aerobic condition for the rice cultivation, and without compromising with the production level of rice crop. But his experimental results showed that nitrous oxide may increase. Of course, water deficit stress may be mitigated to certain extent under elevated CO2 condition. So some more study has to be done in this direction. And of course, there is a vast agricultural setup to conduct such kind of study. But he showed about his results only. So with these remarks, very bold presentation from all the authors, including our invited lead talk as well as invited speaker. On my own behalf, I thank all the speakers as well as lead speakers. Thank you very much to give me this opportunity. Thanks. And over to organizer, please.
Okay. Thank you. Thank you very much, sir, for nicely conducting these sessions, especially though we had dropped out two purpose, but still we try to maintain our time because it is just going to be 16 hours. So we have already scheduled this session up to 16 hours, 4 p.m. But we have only 10 minutes left with this session. But at the same time, this was a very relevant session as far as the whole theme of the conference is concerned, climate change, consequences and challenges. Though we have not discussed much about the agricultural part of it, but most of the papers were discussing about the water resource application in the climate change scenario. And with this changing climate and extreme events, the stakeholder demand is increasing, not in terms of varying from short range prediction to maybe seasonal prediction. All scales of forecast is going to be very critical, starting from day-to-day forecast, even medium range, extended range, up to seasonal forecasting. But the challenge is that in short range, we are not yet achieved the skill in predicting the exact quantity and the amount of rainfall in a local region. Localized rainfall events are not predicting because we are still achieve a lot, means we have to go a lot to achieve that, means in terms of quantity of the forecast, rainfall, and in terms of exact location. So that meaning means we have to go a long way under this in this climate change scenario. So this is maybe a starting point in of very big collaboration needed between the climate scientists and the water resource scientists. So in this aspect, we got two eminent personalities. Though KK Singh Saab is part of our MOS group, but special thank you goes to NV Uma Mahesh sir for accepting our invitation and staying with this time and conducting this session with his words. And thank you, sir. Thank you very much for accepting our invitation. Thank you very much, sir.
Thank you very much.
Thank you very much for joining with us. Thank you, sir. Now,
so thank you.
Thank you, sir.
Thank you.
Now over to moderators.
There is an announcement. After the tea break, the next session will start at 4:20 p.m. Thank you all.
ഷെയർ വന്നു കഴിഞ്ഞാൽ നമ്മൾ അങ്ങനെ സംസാരിക്കുന്നത് ശരിയല്ല. നമ്മളെ വീഡിയോ ഓൺ ചെയ്ത ശേഷം നമ്മൾ അൺമ്യൂട്ട്
Good evening. Manpreet Kaur and Kandla V. Subramaniam. You can check your audio and video quality now, if you wish.
Hello.
Yeah.
I'm audible, right?
Yeah.
Yeah. Okay. So can I check my like PPT once? Can I share my screen?
Yeah, you can share. You just check whether you can share or not.
Okay.
Yeah, it's okay. Yeah, it's okay. Fine.
Video program.
Yeah, we will. Can you please check your audio also?
Can I share that one? Try to see whether it is.
Your audio is breaking.
Yeah, audio. Hello.
Yeah.
Yeah, is it okay now? Audible, right?
Now it's better.
Yeah, let me see. Hello.
Yeah, it's okay. It's okay.
Yeah. Shall I check my slide?
Yeah, you can check. You can check.
So you ready to
Yeah. Okay, it's fine. It's fine.
Yeah. Okay. Thank you.
Okay, thank you.
Excuse me. I'm Santosh. I'm also having the presentation from the same location. I just wanted to share and check.
Yeah, you can.
Yeah. Just a minute. Share screen.
It's working. It's okay.
I'm not able to see the slide mode. Yeah. Am I audible?
Yeah, you're audible also. Okay.
It's clear, no?
Yeah, clear.
Okay, thank you.
Okay, thank you.
Am I audible?
Yes, sir. You are audible.
Maya sir has joined or? Meanwhile, you can check the presenters' availability. Maya sir will be joining. He called me. He will be joining soon.
Good evening, Anand. I joined. I'm Mahesh from MOES. Hello.
Yes, sir. Sir, your video is not visible, sir.
I didn't switch on my video. I'll just 1 minute.
Okay, sir.
Seen? No.
Yes, sir. It's fine, sir.
Sir, we can start by 4:25. Actually, we are waiting for the lead speaker. She's from Germany. We are waiting for her now.
Sri Rekha.
Yeah, Sri Rekha.
Do you have any idea for this lead talk? You will be giving an introduction to the speaker or no?
Sir, can you tell once more?
I was asking. This is the first talk is lead talk, no, Sri Rekha, right?
Yeah.
So this you will be giving an introduction to the speaker or no?
Yeah, we will give introduction.
Okay, from there only organization side only you will be giving introduction, right?
We are giving introduction about all the people actually.
Okay, fine.
If you wish, you can give introduction.
No, I don't have any information. I know Sri Rekha, but I don't have any information.
Okay, we have some information.
Fine. Okay. Good evening, Abhilash. You must be very busy.
Yeah, good evening, Mahesh sir.
Avilas, good evening. And whatever you sent that email, actually we started work on that.
Yeah.
It seems there will be no problem.
Okay. Thank you. Actually, this JV Singhs have informed only last moment, yesterday only.
Okay.
So there is only one dropout from this session. Others are already confirmed. I don't know whether they will. Yeah. Dr. Sri Rekha, who is the lead speaker, also joined.
Okay.
I think we can start, Mahesh sir.
Yeah, sure. We can start. Yeah. Anand, it's fine now. We are starting.
Yeah, sir.
Yes, sir. No issue.
Yeah.
This is organized like a lead talk will be for 25 minutes, including 2-3 minutes discussion.
Lead talk is for 25 minutes and the rest of the talks for 10 minutes each.
No, sir. That invader talk is 15 minutes and the rest of the short oral presentation is for 10 minutes.
Okay.
In this session only we have a lead talk and oral presentation, no invader talk.
Okay.
So maybe I will hand over to moderator of the session. She will announce.
Sure. Please.
Good evening, everyone. Welcome to the day 2 technical session TS4B of INTROMET-2021 on Early Career Researchers session on Earth
Earth observations.
Yeah, Earth observations. In this session, we have one lead talk by Dr. Srireka T, scientist, EU MedSat, Germany. She is an alumni of QSAT and an expert in satellite data application. The session is followed by 7 short oral presentations. This session is chaired by Dr. R.S. Mahesh Kumar and Dr. Anand Kumar Das. Dr. R.S. Mahesh Kumar is Scientist F, MOES, Government of India. He was instrumental in the conduct of CAPEX program of MOES. He holds immense research experience in the field of aerosol cloud precipitation interaction. Dr. Anand Kumar Das is Scientist E from India Meteorological Department, New Delhi. He holds immense research experience in numerical weather prediction with a specialization on the modeling of monsoon depression and tropical cyclones. The lead talk is for 20 minutes plus 5 minutes discussion. Invited talk is for 13 minutes presentation plus 2 minutes discussion. And short oral presentation is for 9 minutes plus 1 minute discussion. We request the speakers to adhere to the time allotted. The selected questions in the chat box will be conveyed to the chairs by the rapporteurs. Now, may I request the honorable chairs to kindly take over the session. Thank you, sir.
Thank you, madam. Thank you. Let us invite Dr. Srireka to present her paper.
Hi, good morning, everyone.
Good evening, Srireka.
Hi, hello. I will just share my screen, okay? Can you see the screen?
Yes.
Yeah, we can see it.
Okay, we make it full screen, maybe. Or was it full screen already?
No, it is in present, not yet in presentation.
Okay.
Mode. Yeah,
Is it good now? Is it good now?
Yeah, it's now okay, fine.
Okay. Thank you. I take this opportunity to thank Indian Meteorological Society for giving me this opportunity to talk in this conference. Actually, my memory goes back to about 20 years ago when when IMS organized the INTROMET in Cochin, and I participated in that conference as a student in COSAT in Cochin University. And today I feel it's a privilege to be here again, talking here and that too in a session called Early Career Research Session. So I hopefully in another 20 years time, we will see most of the participants here also giving presentations in that conference. So with that note, I just start my talk. So my talk is, I just remove this control here, it's disturbing me. Okay, today I will give an overview on the role of satellite observations on weather forecasting. This is not my work alone, so it's a collection of work that is done by eminent scientists all over the world. But I'm presenting it just to show you what kind of observations are existing presently, what are the application areas, and what are the research and development possibilities that exist from the use of satellite data. So that's almost what I have written here in the content. So I will talk about what satellites measure, how, and some examples, and a brief outlook into future. So excuse me if I have a EUMETSAT focus in this talk. That's only because I know a bit better about EUMETSAT satellites than others. Everyone around, all the satellite agencies around the world, including ISRO, NOAA, they are all doing amazing work in this field. And I'm just giving you a glimpse of this from my point of view, from my organization point of view, which is EUMETSAT. EUMETSAT is an intergovernmental organization. This is having its headquarters in Germany, and it is a user-governed organization in that we have 30 member states. We operate geostationary satellites and polar orbiting satellites, and that. So I will be going through a bit about our future programs towards the end of this talk. So why do we need observations? Of course, we all know that we need observations for our weather forecasting systems, for the nowcasting, for the verification of our forecasts, etc. But we have, if I have to classify the observations in these application areas, I would say there is a satellite observations versus conventional observations. And they both are important. They both are different. They both are complementary. And if you ask me to cite some difference between them, this is what I would say. Conventional observations, they are mostly direct measurements. They directly measure the meteorological parameters of interest. They measure temperature, they measure humidity, they measure rainfall. So they're easy to calibrate, and they do not need often they do not need a complex mapping operator, that is to go from a measurement space to a meteorological state space, let's say. But the problem is that they are measured only at specific locations at specific times. So in that sense, they have a poor coverage both spatially and temporally. There are many examples to show that. I'll just draw an example to illustrate this. We'll draw an example from the European Centre for Medium Range Weather Forecast, ECMWF. What data goes into one cycle of the data assimilation scheme. I just listed all these observations, conventional observations, and then try to compare it with the satellite observation coverage. So this is a coverage of the synopship meta observations, just one assimilation cycle, okay? And that consists of all synoptic and ship and meta observations that go into their cycle. And this is the buoy observations. You have the aircraft observations, and you have the radio sound observations. And what you can notice is that the coverage, there is, in general, there is a low coverage, the low spatial coverage over the poles. That's clear. Specifically, southern hemisphere is not well covered. Ocean surfaces are not covered. So in general, there is a non-uniformity in the coverage, and that is where the satellite observations come into picture. That's the coverage of data coverage from all geostationary radiances around the globe. So the colors indicate the data from different satellites, from Meteosat, from Himawari, and GOSTAR. And you have some of the polar sounders giving microwave humidity, polar humidity sounders giving information around the globe. You can see that there's, for the geostationary, you can see that the polar regions are not very well covered, but as a complement, you have the polar orbiting sounders, which are giving you coverage of the polar regions, but you see the gaps in the equatorial regions, and that holds for the microwave temperature sounders. So this is just to illustrate how all these kind of, this is just one cycle of ECMWF data assimilation scheme, how all these different kinds of observations go into the numerical weather prediction to give you the best forecast for the next 10 days. If you look at the number of observations that are going into this, it's also quite different if you compare the satellite and the conventional observations. This is about of the order of 100,000 observations of the SYNOP. You have about 2,000 buoy, 400,000 aircraft observations, and about 1,000 radio sound observations. And these are of the order of this is about 2 million observations from geostationary radiances. This is just to illustrate that fact. And having talked about geostationary and polar orbiters, I just thought it would be a good idea to introduce here why we need these two types of satellites. I think it was clear, it was a bit clear from that picture that I showed that we have good coverage over the equator from the geostationary satellites and around the equator, yeah, and around the polar regions from the polar orbiting satellites, which is critical for forecast. This is like a broad classification of the satellites, geostationary versus polar. So geostationary is looking at the surface at the Earth at one location continuously above that portion of the Earth, and polar orbiter that goes around the poles, and that is critical for weather forecasting, geostationary for nowcasting observations. And just so that you are not, you have some nice picture to look at. I've brought this, I don't know whether it is showing up there, but what you see here is that 3 geostationary satellites and 2 polar orbiting satellites. This is for a future EUMETSAT satellite constellation, but I'm just showing it for illustration purposes. You see that while for the polar orbiter, it is going around the poles, but because Earth is rotating, you get a global coverage. For the geostationary satellite, you're looking at the same part of the Earth continuously, you see, and imagine the observations that you're getting continuously, and imagine the observations that you get around the globe. So this is just to illustrate you. Again, with polar observations, you get, it's about 100 minutes to do that one orbit. So you get about 14 orbits, and about 2 location is covered at least 2 times a day. I think I stop this animation and go to my next slide. And so we said that conventional observations, they directly measure meteorological parameters. What about satellites? They do not directly measure temperature, humidity, or even water vapor concentrations or gaseous concentrations. So what they do is they measure the radiation that is reflected or emitted at specific frequencies, referred to as channels. So you might be familiar with this concept actually, but I thought it would be good to introduce, to do this as an introduction point of view. Everything on Earth has a spectral fingerprint, just like everyone has a unique fingerprint. They reflect, absorb, or transmit energy, but this amount of radiation depends on the wavelength. So that's just the physical processes that are happening with the radiation. It can scatter, absorb. This is a way of transmitting their energy. And if you look at these 3 pictures, it might be clear. So in a visible spectrum of the electromagnetic spectrum, the visible, that is what we see with your eyes. Snow has a higher albedo, that is, it reflects more than ocean. So it's about snow, the albedo is about 0.9, that's about 90% of the radiation, sun's radiation is reflected, while ocean has a very low reflection. And you have a satellite at this visible spectrum, with this visible part of the spectrum. If you have a channel, this is what you see. This is clear, right? This is a portion over Northern Europe or over Norway, where you see the snow versus ocean, or you can even see the land. So this is just a simple example of how satellites look at Earth's surface or Earth's features. And I talked about visible channels. So they measure radiation that is reflected from clouds or Earth's surface. But as it says, visible means it is operating only, it is useful only during the daytime. You also have channel. You can also put channels in any part of the spectrum. You can put in, so in that sense, if you put it in the infrared or microwave part of the spectrum, you measure thermal radiation that is emitted by the Earth's surface, clouds, gases, etc. And at this point, maybe it's good to introduce what kind of sensors are existing. You can have imagers and sounders. This is a picture I took today. This is about a couple of hours ago from IND, our INSAT picture, and this is an infrared channel picture. So images are more, what do the images do? They are more like a camera, taking 2D images of Earth's surface, cloud features, etc. And when you say that you have different frequencies, it is like not looking with 1 eye or 2 eyes, it is looking at the Earth's surface with 16 eyes. That's how I would keep an analogy for this kind of observations. You're looking at the Earth's surface with 16 eyes. What do you see? You see that at any particular frequency, all these atmospheric features, clouds, low clouds, high clouds, etc., they all emit or reflect differently. Why? Because they have different physical properties. Some of them have depending on the microphysical properties, they have, if you consider clouds, you have spherical cloud particles, you have elongated cloud particles, or you have big raindrops, small raindrops. So based on this, they interact differently with the radiation, and that is what is emitted back. So this is how you can differentiate the features that you see. And if you have 16 different frequencies, let's say, or 20 different frequencies on this sensor, you are seeing with, like I said, with different eyes, because each of these channels look differently. Each of these features look differently with these 16 channels, and you can have combinations. And that's the whole point about the nowcasting of, or that's the whole point about imaging satellites. You can use combinations to distinguish sea ice from snow, to old snow, to fog, to multi-year snow, you know, different kinds of features. So that's just an example of how an imagery looks like. Now moving to the other types, it's sounders. Sounders, if you can relate it immediately to radio sounds or sounders, they emit radiation that is coming from different heights of the atmosphere. They give profile information. So I'm just trying to illustrate it with this example. This is the microwave spectrum of the atmosphere. What you see here in blue is a water vapor spectrum, and what you see in orange is an oxygen spectrum. And first, I put an idea. We want to do temperature sounding. What do you want to know? You want to know the temperature, but the radiation that reaches the top of the atmosphere, or what the satellite senses, is not dependent only on the temperature. It also depends on the concentration of the gas. Yeah. So you consider a well-mixed gas like oxygen, so you know the concentration of the gas, and then you can estimate the temperature. And similarly, if you want to know water vapor, the amount of water vapor at different layers, a humidity sounding information, then you need to have a prior temperature sounding information. Maybe I can illustrate it with this example of this water vapor line. These channels are correspond. You see the channel 1, channel 2, you see channel 18, 19, 20. This correspond to the AMSU and MHS channels. So MHS is a microwave humidity sound. It has channels 18, 19, and 20. So if you look at the spectrum, what this part of the spectrum, here is this at this frequency is the maximum 183 gigahertz. It's a max plus minus 1 gigahertz. That is the region of maximum absorption. So when a satellite looks at that channel, from that channel, it sees the top layer of the atmosphere. At channel 19, you have less absorption because it's you see, these are values that indicate the absorption. You have less absorption, means you sense a lower layer of the atmosphere. And the channel 20, it says further lower because absorption is lower. So you can see information from a further lower layer of the atmosphere. So that's a principle of sounding. So you can get a profile information given temperature sounding information, but that's not all about it, because you have several, you can call it an ill-posed problem. You have one final product, but there is not a unique solution to it. So you need some kind of prior information for solving this kind of remote sensing problems. And on top of that, you have clouds, you have surface emission. That's why I put here sounding application selects channels not sensitive surface. I said that for an example is channel 20 here. I said that you can see a bit lower of the atmosphere, but if the atmosphere is really dry, channel 20 becomes sensitive to surface, and then you have all sorts of problems coming from where you have to separate the effects of surface from atmosphere. So this is a challenging problem, but you have several retrieval techniques or assimilation techniques to incorporate these kind of observations into your weather prediction models or to develop products based on this. Okay, I just go to an example from an Indian satellite. I think this is very much needed here. This is the Sapphire instrument from Megatropics. It's an Indo-French satellite. And what they try to do is, it's the same it's a zoomed in version of this part, where we have 3 channels here. They have put in 5 channels. So what will happen? Yeah, you have more vertical information. So 3 to 5 means you have 5 more pieces of information. So you get more profile information from Sapphire channels. That's the idea. Okay, so you talked about 3, you talked about 5, and I'm going to talk about 8,000 plus channels. This is the IASI instrument. It's a hyperspectral infrared sounding instrument, an interferometer. So this is the spectrum. Earlier I showed a microwave spectrum. This is the infrared spectrum of the atmosphere. You see, this is from about 3.6 micrometer to 15.5 micrometer. And this is a problem in satellite remote sensing. You have several units to represent even the wavelength, even the spectrum. Sometimes you use wave number, sometimes you use wavelength, sometimes you use frequencies, but they're all interconvertible, right? So you have to bear that in mind when you look at a picture. So on this axis, we have something called brightness temperature, which is equivalent to the radiance information. So what you see here is all these are channels, yeah, and they all carry information on carbon dioxide, cloud, surface, several species that I have not listed here because you cannot resolve this. You have information ammonia, carbon monoxide. So you can have tremendous. This is a source of information that is feeding into our numerical weather prediction models every cycle. Okay, and we have 3 ERZs at the moment from METOP satellite. METOP is a EUMETSAT satellite. We have 3 series of satellites. METOP A, B, and C are all currently operating, though METOP A will be deorbited in a week actually. So we will, YAS is already switched off. So we do have only 2 satellites now, but we have a similar instrument on the NOVA satellite, which is called CRIS. And we also have GEARS, which is an geostationary infrared spectrometer, interferometer in the Chinese satellite. So these are just to illustrate the amount of information, 8,000 plus channels carrying information. That's a message that I want you to take today. Okay, so now I think we should have a look at the products. I mean, it's difficult to list all the kinds of products that we can get from satellite data, but that's why I have put a dot here. But the main products that I think are significant, I have listed. So primarily variances, that is used for direct assimilation NWP models. You can get, in some applications, you have vertical profiles of temperature and humidity, and even in cloudy cases, why I wrote cloudy cases is microwave observations that can penetrate through clouds. Not cirrus clouds. Cirrus clouds interact by scattering, but all other kinds of clouds that can penetrate. You have also vertical profiles of gaseous species, so all the greenhouse gases, you can get the profile information. If atmospheric motion vectors, this is a special kind of product that you get by tracing geostationary images, the cloud images, then you get an idea of the wind, and this is very, it's an input for the NWP models as well. You get optical and physical properties of clouds and aerosols, or naming cloud top temperature, cloud top pressure, aerosol optical depth, aerosol size, radius, etc., etc. And relating to surface, you can have sea surface temperature, ocean surface wind vectors. Okay, ocean surface wind vectors comes from an instrument called scatterometer. They are active sensors, and we have one EUMETSAT instrument that is doing that now, ASCAT, and there's also an Indian instrument that is measuring surface wind vectors. These are, as far as I know, these are only 2 sensors that do that currently. You can also get information on sea ice products, so sea ice concentration, etc. You get information on precipitation, soil moisture, snow cover, land surface properties, mainly emissivity, land surface temperature, and also biogeophysical parameters, for example, the leaf area index, evapotranspiration, etc. Fire products, these are very critical these days. We hear about a lot of wildfires everywhere, and in order to support these applications, we have several kinds of fire products actually coming up. Lightning flashes, this is quite recent actually, but there are many more new instruments that are coming up to measure lightning. And ionospheric electron condensancy, the application going up to space weather. So that's why I have listed a list of application areas. I think it is very, very lame of me to list these application areas because it goes, I'm sure it goes beyond this. But this is kind of the areas where you can apply, the satellite data are really in play. But I will just highlight from here in today's talk because I'm quite restricted in time. So we will talk a bit about the numerical weather prediction application and a bit about, just one slide on a couple of application areas chosen from this. So that's where I go next. That's the use of satellite data in numerical weather predictions. You saw a bit about I don't say a bit about, but at least I mentioned about microwave sounder and the hyperspectral sounder. So this is a data denial experiment that was run in UK Met Office in 2019. In this kind of experiments, what they do is they have a control where they have all observations, all satellite observations, and all conventional observations in. Then they systematically remove observations. So first they remove microwave sounder, all microwave sounders and images from the system. from the data assimilation system, they run it, they get a result that the forecast is degraded, let's say, and that's what is plotted here. So minus 1.2%. Then they put the microwave sounder back, but they take out radio sound and they run the whole system. And that's how then they proceed like that with all the observations that they do. This is to understand the impact of the contribution from each observing system to their forecasting. And this is the result, and you can see that the microwave sounder is playing a dominant role in the data assimilation scheme. So are the radio sounds. They come second, actually. It should not be surprising, because though they are few and they are only over the northern hemisphere, their impact is actually huge. So this is why in the first slide I said we cannot deny any observation is valuable for our applications. So that's IR hyperspectral sounder, you know, the 80,000 plus channels one. So that's that one. You have aircraft, GNSS RO. I didn't mention about this. This is another technique. This is a radio occultation technique where you track the radiation that is coming from LEO and from a GPS kind of satellites. And yeah, so that's that's showing a comparison of different observing systems to the weather forecast. And this is another way of expressing the contribution of different observing systems. It's in situ versus the ones from space to error reduction in day one weather forecast. So about 60%, oh sorry, about 70% of this impact to error reduction, about 70% of contribution to error reduction comes from satellites, and about 30% comes from conventional observations. But conventional observations, I mean, we have to remember that this is not, the number of observations is not as huge as the satellite observations. It's just to illustrate that.
Srireka,
yes?
you have 3 more minutes.
Okay, fine. I quickly go through, yeah. That's hurricane forecasting. I don't know if you can see the animation. This is done by ECMWF, where on the top panel you see the forecast with satellites, and in this one they removed all the satellites from the forecasting system. So I think the picture, the animation pretty much explains the impact of satellites in that forecasting. You don't see much of that buildup of that satellite here, and similarly for the humidity and wind initial conditions. And that's another way of looking at the 2 meteosat system, which is monitoring thunderstorms over Spain. This is a 15-minute scan. That's a full disk scan where it scans from down below from Africa to Europe. And this is a 5-minute scan, which is scanning only over Europe. So while the 5-minute scan gives you a continuous image, the 15-minute scan gives you a discrete image, and they complement this information. And in the future, we are going to have something like a 10-minute scan here over the full disk and a 2.5-minute scan over there. And that's an overview of the current and future systems from Meteosat. This is our current geostationary satellites. There are 4 of them, and the current polar programs, and then the future coming. We'll just quickly go through the future mission. So we have an imaging and sounding mission. The imaging mission, like I said, you have a full disk imagery every 10 minutes in 16 bands, and you have a fast imagery every 2.5 minutes. So it has also a lightning imager, which will also give lightning flashes, imagine every 2.5 minutes over Europe. And it also has this this hyperspectral, this, you know, the 8,000 plus channels, this kind of profile information over Europe so a 3D weather cube every 30 minutes, which is equivalent to a 4D weather cube. There's also having a Copernicus air quality mission, atmospheric chemistry mission also. So this satellite will be launched end of next year, and this will be launched in 2024. We also have a next generation polar orbiting satellite will be launched in Q1 2024, and another one to 2024. This is a combination. It's a feature of the current METOP. We have 2 satellites. We have 2 satellites to cost saving, I would say. But the missions on board, if you look at it, you have the sounding, infrared sounder, microwave sounder, radio occultation sounder. So these are all looking at different aspects of the atmospheric remote sensing, from clouds to aerosols to precipitation to temperature to humidity to air quality, everything. I would in one word call this as
summarize, please.
Yeah, it's finished. A meteorological laboratory. That's my last slide. So what I showed is only EUMETSAT satellites, but there are, like I said in the before, there's a lot of new satellites program coming up in the future, and there is tremendous R&D possibilities. For example, understanding the physical processes, calibration, validation, understanding the error characteristic, synergistic use or use of images and sounders together or different satellites together, advances in the use of NWP. So what I want to say is, if you have your brains ready for remote sensing, please invest in this area, and for the next few years, you will have enough job to do. That's all I wanted to say. Thank you.
Thank you, Dr. Srirekha. Is there any questions?
There is no questions in the chat box till now.
Okay.
So therefore, sir, do you have any question for madam?
No, I don't have any.
So we can thank you, ma'am, for your nice presentation. So we can go ahead with the next presentation, sir.
Thank you.
Can I make an announcement, sir? The permission.
Please.
Yeah, sir. The three authors, they have conveyed their unavailability. Sita J, Harish Yamman, and Abhishek, we are trying to contact, but he is also not picking up the phone and not joined in our group. So there won't be three presentation most probably. So we have almost like 30 minutes. So in that place, Dr. M.G. Manoj has agreed to give a talk on aerosol and deep convection on short notice. If chair permits, we can include, if time permits. That's what I mentioned.
So he is from another session?
No. He is, because there is 30 minutes left. We cannot left out the time. So we are filling that three presentation with one presentation.
I think it is okay, because this fits in the observations theme of the today's this particular session. I think we can agree. I think what Anand.
Okay, sir. No issue, sir.
Yeah.
One question came from Prashant, whether forecast sensitivity to observation FSO experiment consider error contributed due to TLAD model.
If Srirekha is still present, she
I'm
may.
still here. Yes.
Yeah.
I think they did that actually. I can come back with an answer, but I think that is considered. It's a full system actually that they used for this data denial experiments.
Okay. So maybe we can call the next presenter, Dr. Kandula V. Subramaniam from ISRO, on characterization of convective clouds using multi-frequency spaceborne radar observations.
Yeah, hope, am I audible?
Yes, please go ahead.
Yeah, I think my slides are also visible.
Yes.
Good afternoon all. Thank you, Intromet organizations. And myself, KV Subramaniam, and I will be talking characterization of convective clouds using multi-frequency spaceborne radar observations. And the outline of a presentation is motivation, database, results, and I will be concluding the summary. And here comes as you all know that the radars operating at centimeter and millimeter wavelengths have a different in sensitivity and ability to penetrate different parts of the precipitation. And the multi-wavelength radar observations have the potential to provide a complementary and synergetic way of measurement of precipitation systems. Thus, the differential properties of these multi-frequency observations, such as scattering and absorptions, provides additional information apart from the traditional one that can be used to retrieve the key hydrometer population properties. And recently, Tenore et al. Also showed that only few regions are mapped by the single frequencies are labeled as erroneous. Erroneous means single frequency. And when we consider the global statistics, triple or dual frequency retrievals are available in roughly 2/3. Thus, it emphasizes the importance of multi-frequency. And if you see the over the different parts of the region, different frequencies can be effectively utilized with specific focus. For example, the lower frequencies are mostly useful for the larger particles and deep convective systems, while the higher frequencies such as CloudSat can be used to probe the non-precipitating cloud systems. Thus, the combination of multi-frequency observations of clouds and precipitations can be used to improve the retrieval of the hydrometer properties. That's the main objective of the present study. And the data used for the present study is CloudSat and GPM coincidence passes. I have collected the CloudSat as well as GPM passes from 8 March 2014 to 6 June 2016, and the orbits are coincide almost 6,700. But as you all know that the due to anomaly of the CloudSat battery, CloudSat operate on daytime only, that is ascending mode. So thus provides the half of the numbers of GPM coincidence process. Thus, we have taken the around 3,000 coincidence process of CloudSat and GPM has been taken for the study. And we have also regridded the data with respect to CloudSat, and the time we have restricted to plus or minus 15 minutes to remap the GPM into CloudSat data. And this picture shows the black dot shows the CloudSat passes, whereas the blue dot represents the GPM as well as KU and KA band, which represented by these schematic pictures. So what we have done is we have taken the reflected profiles from the 3 radars and estimated the dual frequencies radars by employing this kind of equations. So we try to subtract from the KU band K, KA band W band, and the KU band W band to try to see the properties of the microphysics. And this shows the potential of multi-frequency observations has been depicted in these 2 pictures, which showed coincident simultaneous observations of the different multi-frequencies starting from 13 GHz to 94 GHz. And as you all see that there are 2 important aspects when we considering into the multi-frequencies. One is complementary as well as synergetically. The circle denotes in this picture represents the complementary information, whereas square backs indicate the synergetics. Complementary means where the different frequencies are tailored to the different targets, such as lower frequencies are meant for mostly suitable to the precipitation particles, whereas the higher frequencies are suitable for the non-precipitating clouds. That is very clearly seen in this picture, where we can see that from CloudSat above 10 kilometers, the non-precipitating high clouds can be detected by the CloudSats, which are completely missed by the GPM, KU and KA band. At the same time, the KU and KA band provide the very good information during the intense precipitating systems. In those regions, the CloudSat will attenuate. Thus, the combination of the complement of these systems, which provides the comprehensive information about the cloud systems. That is one of the important main aim of the study. And this shows the various examples of the simultaneous observations of the 3 radars. And coming to these pictures, as you know that the traditional TRMM, which gives this figure shows the CFAT. This is a KU band, which operates at 13 GHz. We can see that the reflectivity values are decreasing when we are going to the higher heights in terms of their frequency of occurrence. This is all known. And also KA band also shows very similar pictures. When it comes to the 94 GHz, where W band, initially the reflected values are increasing with the height. At the 0 degree isotherm, from there it starts to decreasing. So this kind of information is typically different from the KU as well as KA band because of their sensitivities. When we try to combine these 3 frequencies into a single comprehensive picture, which is to provide a very good information, which is completely missed by when we look into using the single frequencies. We can see here the black contours indicates the CloudSat, whereas red contours indicated by KU band, KA band, whereas white contours indicated by the KU band. So the 13 GHz, 35 GHz and 94 GHz provides the much needed information on the somewhat complete picture of the convective systems. If we have simultaneously using the S band or C band, these higher range values also can be utilized more seen. So this is for the first time we try to construct the frequency of occurrence of altitudinal reflective structures using multi-frequency observations in convective clouds. And this shows the one typical cases of the where we can see that the clouds at vertical structure of convective systems, and followed by KU band and Ka band, and the corresponding reflected profiles has been shown in the middle panels, which indicates the profile number 845. So from this we can see that the different frequencies are sensitive to the different parts of the preceding systems. From the left panel represents the dual frequency ratios. As I said, we have estimated the KU, KA, KUW as well as KAW band. The blue color we can see that very nicely, almost up to 4 kilometers, the dual frequencies ratios are 0, and further above 5 kilometers, which shows a very plateau regions. So this kind of plateau region in the dual frequency ratios can be utilized to derive the liquid water condensation path, as told by Tridden et al. Also. And you can see that the DFRC is seen to converge nearer to the 0 dBc, such that these differential signals across the column can be interpreted from the resulting exclusively from the non-Rayleigh scatterings. Under these conditions, this information can be related to the ice crystal sizes, which are dominated in the top of the thunderstorm clouds by using the proper ice scattering properties. Thus, the DFR provides a very much information, and these differential radar signals in backscattering attenuations provide the additional information apart from the d to the power of 6 traditional one that can be used to constrain the retrieval of the key hydrometer properties such as water content and characteristic size. Further, we try to see that how we can try to see the identify the ice scattering or snow dominated of deep convective systems. Very Batigla in 2014, he has showed that the most of the times TRMM as well as GPM also mostly retrievals are dependent by the single scattering event. But if you see the deep convective systems, the multi-scattering also dominate. This is how it looks like. When weak multi-scattering present is there, there is a below there is a one kink, and above it is it will be prevail like a heavy. When it is going, then the multi-scattering dominant, the profile looks like a peaking at the above 5 kilometers, and it will be stretching like this. So this kind of information also we have seen in our results, where we can see that in the dual frequency ratio, same corresponding to the previous pictures. Very nicely, you can see that the below 4 kilometers, it is a kind of a pulse stretching in the convective systems. Thus indicates that in convective systems, it is mostly dominated by the multiple scattering. So one should take care of these multiple scattering to retrieve the very hydrometer properties in convective clouds. So that is what one of the very important when it comes to the dual frequency ratio. And further, if you try to see the comprehensive picture, this picture shows the KUKA dual frequency ratio in terms of height, their frequency of occurrence, and the red color gives the mean profile of this one. And similar to Ka and W band, this gives this. We can see that after 4 kilometers, it starts coming down. So this indicates that most of the convective clouds, not only single scattering, multi scattering also dominated. So what will come to know when it multi-scattering dominated, whether we will able to know the any type of the information of the nature of hydrometers? Yes. If you try to plot the dual frequency ratio of 35 KU and W band versus KU and Ka band, we can see that there is a two distinct separate regions has been observed in the scatter plot. One is below 0. We can see that very nicely here separated distinctly, which is mostly dominated by the homogeneous period hydrometers, whereas this curve represents the mainly dominated by the snowflakes. This is further evaluated with the theoretical study by Manson et al. Very recently. He also tried to see that developed in 3595 in their simulation 10 to 35 DFR, which also showed that there is a fractal particles, the curve should be like this. When it comes to the homogeneous hydrometers, the curve should be thick blue. So our results also fall with the theoretical observations. Thus, the impact of the dual frequency ratios can be effectively utilized to study their character size and their density of the snow and ice distribution for retrieval of for better retrieval of the microphysical properties in the convective systems. And further, what we have done is we try to see that their temperature dependence, whether it is having any temperature dependence or not. Yes, definitely it has. The regions in which the temperature is smaller than the -20 degrees, the DFR value is mostly below the 5 dB. Whereas when it comes to the -20 to -10 degrees, we observe a widening of distribution to higher values, and it represents to the population of the hydrometers in that temperature regions. So this further suggests that increasing the number of large aggregates of hydrometers due to the stronger growth of the precipitation particles, which is the one responsible for the observed this kind of temperature dependency retrieval. And coming to the summary, yes, we have studied the unique way of combination of cloud set as well as the GPM, KU and KA band are used to investigate the deep convective clouds and their characteristics. We observed that the convective mean dual frequency ratio values are KU and W increases with decreasing altitude, especially below the melting layer, right, than that of DFR of KU and KA band. And further, the temperature dependence of this triple frequency signature is also studied, which evidently showed that the widening of KU W DFR values between the -20 to 5 degree temperature zone is very well noted, which suggests the larger aggregates growth of the precipitation particle in that temperature regimes. Further, it is also noted that these vertical structure of dual frequency ratios can be potentially used to identify the multiple scattering signatures, which can enable to locate the areas of densely populated ice particles in the thunderstorms as well as deep convective systems. And thank you.
Thank you, Subramaniam. I have a question.
Yes.
This DFR values, how effective in retrieving the mixed phase cloud properties?
Yes, DFR can be effectively used for retrieving the mixed phase, because when it comes to the mixed phase where we have the different sizes of the ice crystal coated with the water, though that time the DFR values are differently behaves. Due to lack of time, I have not shown that one. Otherwise, what we have observed is DFR values of around 6 to 3 kilometers in that region where we have the mixed phase of the hydrometer species, the DFR values found to be around 1 to 3 dB.
So you have different thresholds for mixed phase clouds, water cloud, and ice clouds, right? On those thresholds, if DFR falls, then you will characterize them as mixed phase or water cloud or the ice clouds. Am I right?
Yes, exactly. That is what the main.
One more question is how, if you have retrieved this precipitation from these different frequencies, how they are there any good match with the ground observed observations of rainfall, rain rate, or rain intensity?
Yes, actually, I have not studied, but studies are there from the mid latitudes where they have studied the IFX campaign also with having a 3 frequencies and onboard airborne radar, then they have compared with the S-band ground radar, and it is very matching. But one thing is
problem with these 3 high frequency bands are they are having the larger attenuation capacity when the rainfall intensity or precipitation density is increasing, right? C band will be for the precipitation.
Yes, you are right. So
you will
actually similar, sir, based on similar ground, actually I had a question. Suppose your cloud structure is different. Now suppose if it is a very tall cumulonimbus and another is suppose stratified cloud. So in that case, suppose whatever the you decided weight you are using, whether that will be effective. Suppose you are looking from top, no?
Yes. No,
actually even related to previous questions sir asked actually.
Yeah. Can you just once again repeat, sir? I pardon that.
Actually, sir asked no, that attenuation is a great factor in this band. So
Yes.
when the cloud is a tall cloud and another is a stratified cloud, so both the cases, whether the performance will be similar or it will be different.
No, sorry, it will be different, but the attenuation comes to the, depend upon the density of the hydrometers for the especially higher frequencies. When it comes to the higher frequencies at deep convective systems, the attenuation will become more, so that beyond 20 dBc and that the backscatter signal will be attenuated. That is how we have seen that when we are using the 94 gigahertz beyond 20 dBc reflected values, we cannot able to see in that high frequency signals. When it comes to the stratified, let us take stratocumulus clouds under where the reflected values, the dominant or the larger reflected values are not beyond much above the 30 or 35 dBc. In those cases, the high wavelength radar also can be given very nicely, and those stratified clouds, when it comes to their vertical height, is very limited to the below 5 kilometers, and it also having the non-precipitating component as well as some drizzling components. So in those regimes of the cloud, these high frequencies can be effectively utilized, but with a caution.
Yeah. Actually, that is what I am telling. Actually, it is very good for stratified kind of clouds, but not very good for tall cumulonimbus type of clouds.
Deep convective.
Yes, sir.
Deep convective and extreme rainfall causing clouds, we will be missing it. Only for the normal stratocumulus clouds with the normal rainfall, we will be able to use. Okay, thank you, Subramaniam.
Yes,
Any other questions are there? We can take one more question. Okay, if there are no more questions, we will invite. Thank you, Subramaniam. You may leave. We will invite the next presenter, Dr. Santosh. Is he available from VSSC?
Good evening, sir. I am available in the same location.
Okay.
Santosh,
please carry on with your presentation topic: improved estimation of planetary boundaries.
Can I ask one question?
Now we started already. The next question, next person, no? Next person is online now. Patnaik, maybe. Yeah. So improved
After
estimation.
presentations are over, sir, if we can find time, then for all presenter we can take some questions, sir.
Okay. Santosh, you please go ahead with your presentation.
Okay, thank you, sir. Good evening. Thank you to Intromet for giving me this opportunity. Now, in spite of the recent progress in weather and climate prediction models, still do not fully and realistically represent the boundary layer processes, since most of these processes occur on a subgrid scale when compared to the typical model grid scales. Now, global observational data sets go a long way in improving this picture, especially when they give parameters like the planetary boundary layer height on a regional and a global scale. Now, Cosmic 2 radio occultation provides a global coverage of refractivity profiles over low and mid latitudes, from which the planetary boundary layer height can be derived.
Are you presenting this, or?
Yes, sir. I am just presenting. I started.
You will be presenting this way only. You don't have any PowerPoint slides?
I have, sir.
Okay.
But that is not visible.
Not visible now. Only your face is visible now.
Yeah, that is why
The slide is not seen, sir. Yeah. Is the slide?
Your slides are not shared.
Not seen.
Oh, sorry. Sorry. Share. Have to share the presentation. I have, where is share screen? Share. Can you see it now, sir?
Make it full screen.
Yeah. Yes, sir. Yeah. Now is it visible?
Yeah, it's fine.
Yes, sir. Yeah. So now Cosmic 2 provides the boundary layer height information over a global scale over mid and low latitudes. And Cosmic 2 is a follow-up to the Cosmic 1, which is from which a global climatology of boundary layer height has already been established, starting with the first work from Basha and Ratnam 2009 up to Basha 2019, where decadal climatological picture of planetary boundary layer heights has already been derived on a global scale. So this study is an improved estimation of the planetary boundary layer height, which focuses on the areas in which the previous studies were found to have lesser, more variability in the boundary layer height climatologies. Now, what is the need for that improvement? The first one is that there is a general overestimation of the PBLH, especially over oceanic ITCZ regions as well as over the subsidence regions. The cloud top height or the subsidence base is often misrepresented as the boundary layer height in the methods that are currently being employed. And there is no way of addressing this issue without using additional data sets, because the refractivity is dependent on temperature and humidity by this equation. So we cannot really know whether a particular refractivity gradient is a cloud top or a subsidence base or a planetary boundary layer height top. So this is the matter which is being trying to be addressed in this study. The present study proposes an objective method for determining the boundary layer heights over regions which are known to give poor boundary layer heights from RO-based refractivity profiles without compromising on the basic premise of the boundary layer detection method that is already being used. The performance is compared with the traditional method, and similarity and differences are investigated. Now, 2 years of COSMIC 2 data is being used to compare the new approach. Now, why COSMIC 2? COSMIC 2 offers some peculiar advantages which are aligned with the objectives of this study. It gives the best ever penetration depth of the RO-based refractivity profiles as compared to any other radio occultation-based profiles over the tropics and the subtropics. That is, if you see the comparison with all the previous radio occultation satellites, you can see that more than 40%, 50% of RO profiles are able to reach within 200 meters of the surface. So many of the older generation radio occultation satellites used to stop the refractivity profiles above the planetary boundary layer height. So this is a very crucial advantage which COSMIC 2 offers. And the second major advantage is that the largest number of profiles in a 5x5 grid over a particular day is being offered by the COSMIC 2 set of satellites. Now, here also, this is with reference to the COSMIC 2 was designed to offer more number of profiles. So this peculiarity of the COSMIC 2 is exploited to achieve the objectives of the present study. In addition to and these are possible because of the very different hardware, improved hardware on board the COSMIC 2 satellites. In addition to this, there is also an algorithm change. The wet PF2 profiles from COSMIC 2 are used, which use a different method to derive the refractivity profiles instead of the Abel inversion, which was normally used. So this gives an improved refractivity profiles over the tropics and the subtropics. Now, in the typical way in which the boundary layer height is derived using refractivities, we have the refractivity profile and the refractivity gradient and the wavelength covariance transform of the refractivity. So at the boundary layer top, there is a very sharp gradient which is seen, which is the ideal case. Now, we cannot really much improve this particular case, but where the improvement is concentrated is in the multi-peak case, where there are multiple peaks in the refractivity gradients which are significant. So the difference in the peak is hardly 10 to 20% between the minimum refractivity gradient and a significant gradient below the MRG, which is the minimum refractivity gradient. So in the traditional methods, we consider only the top one to determine the boundary layer height, which gives a large variability. Whereas if we make an effort to include the bottom significant profiles, then it becomes a more realistic representation of the boundary layer height. So it is basically a largest gradient versus the significant gradient closest to the surface. So this is the traditional method, which has been, a lot of studies have been published, and they use the different types of optimizations. Different thresholds are used to eliminate bad cases of refractivity profiles. Now, in this particular study, no threshold is used, which follows the approach followed by Ao et al. 2012. In this method, we determine the gradient of refractivity, determine the altitude of the minimum refractivity gradient, or a significantly strong gradient below in the 0 to 5 kilometer range. In case of multiple peaks, the lowermost peak is chosen and designated as the boundary layer height. Now the question is, how significant is significant? Now significance can be an absolute value, but we cannot use that because it has a global coverage with a different geographical and climatic conditions. And the refractivity depends on temperature and moisture, which are having a seasonal and latitudinal and regional difference. So the significance is defined with respect to the minimum refractivity gradient, which is 80% of MRG, 70, 60, and so on. So if we are able, this is just a small adjustment to the traditional method, which is already being employed. So whether this small adjustment has only a small effect or a large effect, that is what will be seen, and how significant is significant. So this particular slide, what I have shown is the first panel is the actual boundary layer height with the traditional method, and the bottom 4 panels on the left side are the difference in the seasonal mean boundary layer height obtained for 80%, 70%, and so on significance. So this is the bottom 4 are the delta PBLH, top one is the PBLH. In the same way, the peak strength at the boundary layer height is shown, and the delta peak strength, which is expressed in percentage, is shown in the bottom 4 panels. So what this gives us a picture is that just a small, lesser than 5% change in a peak strength at the boundary layer height is able to give a non-uniform decrease in the boundary layer height in the proposed method. We can see that this decrease ranges from less than 100 meters over the blue areas to about 800 meters. So, and so on. As we go on decreasing the significance, the difference between the new boundary layer height and the traditional boundary layer height keeps on increasing. Now we need to optimize and see where we can draw a line saying that this particular significance can be used. Now, this is the delta PBLH. If you see the actual PBLH on a global seasonal mean scale, we see that the features which are already reported in previous studies are represented in the delta PBLH, but it goes on decreasing in significance. And I have also shown the cosmic minus ERA 5 PBLH on the right side panel. So we can see that in the traditional method, there is a large difference in the boundary layer height obtained using the traditional method with respect to ERA 5 PBLH. Whereas just a small change in the PBLH is able to improve the agreement with the ERA 5 PBLH in a significant way. And in this entire analysis, only the daytime profiles are used for both ERA 5 and cosmic. This entire study, only daytime profiles are used. So as a way of optimizing which significance is better, as we keep on decreasing the significance, we go away from the basic premise that the significant difference between the refractivity in the boundary layer and above. So we choose 80% as the optimum significance because it balances the premise of PBL detection with least change in the seasonal mean peak strength, giving good comparison with ERA 5 PBLH. And please note that we are not trying to have ERA 5 PBLH as a standard because being an observational database, Cosmic 2 has a greater importance, greater weightage. We are just trying to compare with respect to the traditional method and the proposed method. So we are chosen the 80%. Now, if we see the seasonal mean picture of the boundary layer height using these two methods, the traditional method is in the left side and the 80% PBLH is in the right side. 2 years of data is being used and only daytime data is used. So this shows the counts per 3x3 grid scale. And we can see that most of the regional profiles are, regional features are reflected in the proposed method, except in the ITCZ areas where the boundary layer height is drastically reduced with respect to the what is there in the traditional method. So now, and this also tallies with the observational, in situ observational studies, which have reported low PBLH over disturbed areas or cloudy areas, and it tallies with the ITCZ areas which show low PBLH in the proposed method. Now, standard deviation of the PBLH on a seasonal mean scale gives the temporal variability of the boundary layer height. Now, in this particular slide figure, what I have shown in the left-hand side.
You may have to summarize now.
This is the last slide, sir.
Yeah.
So here, the difference in the standard deviation is positive, which means the proposed method has lesser standard deviation than the traditional method, which shows that the proposed method decreases the variability. And this also is coincident with the regions which have low sharpness. So effectively, we see that, and I have also given a contour of the ITCZ areas, which is the rising areas in the left panel and the subsidence areas in the right panel. So as a summary and conclusion, a small change in the traditional method of PBLH determination leads to non-uniform change in the seasonal mean daytime PBLH, ranging from less than 100 meter to 800 meter, and decreases the temporal variability by about 300 meter. The sensitivity on a seasonal scale reveals that the proposed method causes a change of less than 5% of the peak strength on a seasonally averaged basis. The proposed method shows seasonal and geographical features which are in line with reported climatology except the ITCZ regions, and it also compares better with the PBLH from ERA 5. That's the basic study. Thank you.
Yeah, good. Thank you, Santosh. I have a question.
Yes, sir.
Using this determination of the PBL height using your what is that?
Which one?
Whatever cosmic occultation method, have you how it compares with the actual normal derived PBL heights? Usual wave from radio sound or anything like maybe the very oldest question actually, how well it compares actually?
Yes, sir. The first reported radio sonde versus radio occultation based PBLH was done in 2009 from Gadanki. So they reported a Basha and Ratnam 2009. So in that work, they have reported a very good correlation, and subsequently many.
I am asking about the current the suggested new method, how well it compares.
Actually, sir, I have done an extensive radio sonde analysis over the Indian Ocean, and this is the overestimation magnitude is quantified, and it very clearly establishes that the radio sonde based the traditional method overestimates by a factor of more than 300 meters in the over the tropical oceans. The reported literature is over marine stratocumulus regions and over continental regions, which are in line. But over tropical oceans, I have not included that in this presentation. But radio sonde has shown a significant, the traditional method has shown a significant divergence. So, and it is region specific. In certain regions, it is having a very good comparison. In other regions, the traditional method doesn't do so well.
Why then 80% of the confidence? Why not 90% significance of the significant?
Yes, sir. We have to have a balance between a better comparison with available data set with respect to the traditional method. For example, in this.
You quickly you tell one sentence.
Yes, sir. So 80 and 90 are effectively the same. So it is just, I have used the example of 80%.
Okay.
Yes, sir.
Any more questions? Thank you.
Thank you, Santosh ji.
Santosh. Yeah.
Thank you, sir. Thank you.
Next presenter, I think, if I remember rightly.
Yes,
she's not there.
CJ is not attending, I think.
And Harish is there. Then Abhishek from IIT Kharagpur.
No.
Then Achu Kufos.
Yes, sir, I'm here.
Yeah. Achu, you please start your presentation.
Yeah, sir. Yeah, I think my screen is visible, isn't it? Can somebody help me?
Visible, please go ahead.
Yeah, it is visible.
Actually, okay. I think my video too will be visible. Okay, fine. I think, yeah, I think my presentation is a bit different from those who presented others. Here I'm talking about landslide modeling using deep learning. And I'm Achuel from Kufos, Kerala University of Fisheries and Ocean Studies. And my presentation title is Spatially Exhibit Deep Learning Model for Landslide Susceptibility in the Mapping of Western Ghats in Southern India. This is my outline of presentation. I will talk about the background relevance of my study, then study area, methodology, result and discussions, conclusion, and references. So let me start my presentation. As you know well that recent extreme weather events accelerated the number of landslides in India, especially the southern India, including Kerala, and we have a lot of casualties due to the extreme, due to these landslides caused by or initiated by extreme climate event. It is nearly 66 million people globally live in highly landslide-prone areas, and approximately 70% of fatalities are caused by landslides. And it almost causes $4 billion and 5,000 fatalities every year. And unfortunately, about 16% of the world's landslide event, I'm talking about non-seismic event, during the last decade was reported in India, especially Himalayas and the Western Ghats. And nowadays the Western Ghats become more and more popular due to the landslides and perhaps a landslide hotspot in India. And the rugged and steep Australian slopes of the Western Ghats with abundant rainfall, especially Indian summer monsoon, causes frequent landslides every year. And that's why we are doing this study. And you can see that 2018 Kerala flood and heavy rains and associated thousands of landslides occurred. Almost 400 people lost their lives, and over 2.2 lakh people were displaced. And there was a lot of casualties. And Idukki was one of the most affected districts in Kerala. And we had a landslide susceptibility map that was prepared in late 2000s. That's somewhat older, and it was on a coarser scale. I think it's 1:1 lakh scale. And all the mitigation purpose was carried out on that scale. And so we thought, the repeated landslides are occurring, and most of the landslides are not accounted in the all landslide susceptibility maps. That's why we are proposing a new methodology. And using in Idukki itself, as you can see in the figure also, 2020, Petum landslides, one of the largest one in the state. Then even 1 month before 2021, Kokkar and critical landslides, which also there were, I think 80 or 90 landslides were occurred, and almost 20 people lost their life. So this is a continuous series of landslides. So in order to model these landslides, we choose Idukki districts, perhaps the landslide hotspot nowadays in India. And in addition, the district is famous for many international tourist spots like Munnar, and it's throughout the year there will be tourists in the district. And the nature of the district is somewhat agroclimatic. It's suitable for cultivation of different plantation crops like tea, rubber, coconut, coffee, cardamom, pepper, etc. And most of these district areas nowadays were witnessed dynamic land use changes. Plantation were everywhere, tea as well as cardamom, pepper were everywhere. And with these dynamic land use changes and the extreme events, which caused 1,239 landslides in 2018 alone, which caused nearly life losses of 115 people and exorbitant losses. So what we did is that we just created a landslide database and also a spatial database, which includes 14 landslide conditioning factors. That means the factors which affect or which control the landslide occurrences. Then we just checked the correlation between these spatial database, the landslide conditioning factors, to avoid the correlation. That means the redundancy between the factors. Then we implemented a deep learning algorithm that's called deep neural network to model the landslides. And thereafter, for curiosity, we just cross-checked, or we just compared this result with a traditional machine learning algorithm. a well-known algorithm called random forest. So we got some interesting result. Then finally we proposed our landslide susceptibility map based on this deep learning neural network. So this is my methodology. Then as I talked earlier, we just collected 1,239 landslides, and these are surveyed in the field in late December 2019 and January 2020, just before the COVID coming. Then these landslides were further divided into 17 and 13% ratio for model construction as well as validation. Then we implemented 25 cross validation, 25-fold cross validation to avoid the model fitting. And based on the literature as well as the availability of the data on a desired scale, we chosen 14 landslide conditioning parameters, including lithology, land use, slope angle, road lineaments, and so on, as you can see in these slides. And we rasterized all these pixels with ensuring a common resolution of 30 meter and a common coordinate system of ET1 WGS 9084-43 node zone. And we, as I mentioned in methodology, we just conducted a multi-collinearity analysis using Pearson correlation method. And there are two highly correlated variables. Those variables were omitted, and there's a cross-sectional curvature and longitudinal curvature. Then further modeling is carried out. Then the modeling method we use is deep learning neural network or deep neural network, which is a multi-layer perceptron neural network with more than one hidden layer. And for achieving a better or reasonable accuracy, we need to hypertune the deep learning. So we use a tune grid to hypertune the DNN, and I will talk that hypertuning in the result and discussion section quickly. Then result and discussion. So yeah, here is a training and loss function graph on left side and right side. We just used 13 hypertuning parameters, including activation function, hidden layer, epoch, regularization, that means L1 and L2, then ROHO, momentum stables, and dropout ratio. We got the better result by using ReLU or rectifier linear with the dropout, and we got a hidden layers like 50 into 50 into 50. Then the better result was obtained at a epoch of 210, and all other parameters are mentioned here. And we used the softmax transfer function to transfer the probabilities generated from ReLU activation functions. The softmax transfer function retains the probability of occurrence of landslides as well as the occurrence of non-landslides. Then finally, total input factors and 50 into 3 hidden layers and 2 output layer DNN was constructed for landslide susceptibility mapping. And the accuracy and other parameters are listed here. It shows DNN shows a better ability to identify the pattern, and that means identify the landslide and non-landslide areas with the area under curve value of 0.972 in the training and 0.968 in the testing section. And besides, the difference between training and testing is very narrow, that implies the absence of overfitting. And the right side you can see the random forest training as well as random forest testing sections, which is also quite good. It obtained 0.892, that means 89.2% accuracy in training and nearly 85.6% in testing. So the interesting fact is that when we plotted it in a spatially to check the spatial variability, because both the ROC and other true positive, true negative, all parameters are just modeling parameters. They are non-spatial parameters. When we check the spatial parameter, we obtain that deep learning have a better ability to find the pattern well in landslide susceptibility modeling. If you are seeing the right top corner, the left is DNN model and the right is random forest model, you can see that some of the areas where landslide is not affected, it is predicted as extremely susceptible area by random forest, whereas it's a stable or least susceptible area by DNN. Following the sub images also, you can find somewhat a overfitting tendency by random forest, whereas clearly a terrain-based spatial variability is more frequent in DNN modeling. And the next is, what are the key factors that control the landslides? We use the variable important analysis that is available within the DNN model. And we found that the slope angle and roads and rainfall are the major parameters which controls the occurrence of landslide in the study area. And aspect, plan curvature have and lineament have less significance. And all the parameters have predictability greater than 0. And distance from the road is also indicates the anthropogenic disturbances, which I will talk in the next slide. Here you can find some of the land use changes as well as the construction of roads, which goes to the landslide initiation. You know well about the Western Ghats. It's a fragile one, and you see in the right top the famous gap road, which is constructed from going to Munnar, which goes to continuous landsliding every year, and the unscientific land use practices.
You may have to summarize now.
Yeah, this is my last slide, right?
Yeah.
So these field images can be clearly about that in anthropogenic disturbances is a major factor which causing the landslide susceptibility in the study area. So I would like to summarize that the study indicates about 10.66% area of Idukki district is extremely susceptible for the occurrence of landslides, followed by other figures. Then DNN is more effective in identifying the spatial pattern because most of these landslides are triggered by intense rainfall. And therefore it shows a pattern. So DNN is more more effective in identifying the pattern when compared to the traditional machine learning model like random forest. And the computation time from my end of DNN was similar to those of one which are used in hyperparameter tuned random forest. Then slope angle, distance from the road is somewhat major parameters which control the occurrence of landslide, followed by anthropogenic disturbances. So with this, I summarize. Thank you. Thank you.
Thank you, Achu.
Please, sir.
We have a question on the chat box. On what basis the percentage of training and validation data is divided?
You see, it's purely based on the literature review because the studies conducted in India as well as the other parts of the, especially the European Alps, that which implies that 70% for training and 30% for testing yields more accuracy and avoid overfitting. So that's why we chosen that criteria.
Okay. I'm a layman with respect to landslides, but still I'm asking. Is there a possibility that using this method you will be able to have a predictive model of landslides? You'll be able to predict with this susceptibility mapping. Further, can you add to say that these are the areas with we can have landslide prediction?
Yes, sir. This is the first step. Actually, this implies that the susceptibility, that means the probability of occurrence, and you can say that this area is susceptible. Okay. Then one more thing is that rainfall based analysis that can say that when and will the landslide is going to or supposed to be occur. Okay. If you can merge these things together, then it will be a better decision for policy making and other land use plans.
Okay. So, thank you.
Okay.
Actually, I have one query. Okay. In your methodology, you have put rainfall one of the parameter and soil also another parameter.
Yes, sir.
But soil moisture is not a parameter in your model.
Yes, sir. But I came to know that recently that soil moisture data is freely available. That's why I couldn't able to include that model. And these rainfall, I took the Indian summer monsoon average of Indian summer monsoon for 35 years. So that time I was also not aware about the availability of the soil moisture data for a long time. That's why I couldn't include it. So what my next planning is that when next is I'm going to conduct a rainfall based threshold analysis in near future. It's a part of my PhD. So that time I'm just trying to whether the soil moisture can increase the rainfall threshold because these are correlated.
I think Achu, we'll maybe further we can discuss of the
Thank you, sir.
situation. Okay. Now we are running out of time.
Yeah, sure,
I'm requesting now Dr. Manpreet Kaur from IITM, if she is present to Please yes, start your presentation. Yes, your slides are visible. Please go ahead. I think you are muted. Your voice is not coming up. Your voice is not coming up, Dr. Manpreet. On your screen, the left mic, you see down it is.
Hello.
Yeah, now it is audible. Yeah, please go ahead.
So let me just start sharing again. I'm sorry. Okay. So I'm here to present synoptic to large scale feature of monsoon 2021 in multiphysics framework for extended range. Um, Before I go to multiphysics system, I would like to recap on existing extended range prediction system, which is operational at IMD. This system has two model variant coupled CFS and atmospheric GFS with two resolution 382 and 126 running with perturbed initial condition ensemble. Also, the real-time SST from CFS goes to GFS as boundary conditions. So coming to the multiphysics framework, we are incorporating intra-model spread by using physics ensemble in this system. So for that, we have taken combination of convection and microphysics options. At present, we have total of 6 combinations. And as far as resolution is concerned, we have taken seamless horizontal resolution in which high resolution of 574 will transition to 382 after 15 days. This will this will help the system to control the error growth and also maintain the computation efficiency. So we run the system every 1st, 6th, 11th, 16th, 21 and 26th of every month. To compare the skill of monsoon rainfall with the existing system, so here I am just presenting the CFS from version 1 ERP and multiphysics CFS in the bottom panel. So we can see that this is the subdivision wise anomaly correlation. So we can see that at week 1, week 2 and week 3 and week 4 forecast, we have better skill in multiphysics system than the version 1 CFS. So now multiphysics system is also better than the entire ERP system, which is the combination of CFS and GFS. So further, now I will discuss the main features of monsoon 2021. So I have picked up some 7 occurrence during this year monsoon. So first I'll start with the cyclonic storm yes and monsoon onset, then the heat wave like condition over northwest region, mid-July active spell, intense rainfall over Kota, Rajasthan, and active August break spell, deep depression over Bay of Bengal, and finally the cyclonic storm towards the end of September. So the cyclone yes, which occurred during 23rd to 28th May, I am showing the cyclogenesis probability. So this is the track which is also confirmed with the ERA 5 reanalysis cyclogenesis probability. So from this multiphysics system, from 3 far to near initial conditions, we can see that our system is able to give indication of this upcoming event. Also the probabilities increases, the magnitude of probabilities increases as we move from far to near initial condition as expected. So for the monsoon onset criteria, so there is this area average rainfall over this Kerala coast and area average zonal wind over this region. So this is the time evolution. We can see that this black line represents the observed rainfall, and here it is the ERA 5 reanalysis for zonal wind. So the color line show the CFS, multiphysics CFS from 3 different initial conditions, and we can see that model has ability to capture this temporal evolution very well despite some errors. Especially for the zonal wind, the model has a better prediction from the near initial condition than the far initial condition. Supplementing to this, the width of the depth of zonal westerlies are included in the monsoon onset. So we can see that in ERA 5 reanalysis, the nice distribution of this zonal winds, which is also represented in our model very well. Coming to the after this initial onset, there was a hiatus in monsoon progression, and I am here showing 28th to 8th July, which was like very dry conditions over northwest regions and hot conditions as well. So this is 2-meter temperature anomaly, and above is rainfall anomaly for this period. So we can see that from model 3 initial condition also we have indication of these dry as well as hot conditions over this region. Revived by this mid-July active spell, these conditions, we can see now here from 19th to 29th July, the positive rainfall anomaly over the country, which is very well, which can be seen in a multiphysics CFS forecast from 3 initial conditions. Down, I am showing the percentage anomaly over monsoon zone and over equatorial Indian Ocean from these 3 initial conditions, and we can see that around this period we have positive anomalies over monsoon zone and the negative anomaly over the equatorial Indian Ocean. The subsequent break spell is also indicated in this in these forecasts, which I'll be discussing shortly. So there was an intense spell over Kota, Rajasthan from 3rd to 5th August, probably mostly associated with the low pressure area developed over Bay of Bengal on 27th, and which was present, which lay over this region on 4th August, shown by this MSLP contour in observation. So we can see the enhanced rainfall blob for this period in accumulated rainfall from model as well as from observation. Coming to the break spell, the high positive negative anomalies of rainfall can be seen over the central parts of India. This is also represented well in the model from 3 initial conditions. There is one issue in the mid initial condition where this this blob of rainfall, this Rajasthan rainfall blob is little bit spatially extended in the model. This is also confirmed with the model forecast is also confirmed with the percentage anomalies taken over the monsoon zone and over equatorial Indian Ocean. We can see that there are negative anomalies over the monsoon zone and positive anomaly over equatorial Indian Ocean in all 3 forecasts, which is the peculiar signal of monsoon break. 12 to 15 September, we had a deep depression from over Bay of Bengal, which has given immense rainfall over adjoining regions. And similarly, from observation and model forecast, we can see this strong presence of this deep depression as well as the offshore monsoon trough. This system is also indicated in our cyclogenesis probability forecast, which from even from farther initial condition we have some indication of this system. Finally, coming to the cyclonic storms, this is a 2-in-1 cyclone which originated in Bay of Bengal as cyclone Gulab and then ended as cyclone Shaheen in Arabian Sea. So we can see that from ERA 5 reanalysis, the cyclogenesis probabilities are very well depicting this. A multiphysics system also could give indication of this system. So to summarize, I mean, overall, the multiphysics CFS has potential to capture the monsoon 2021 features to some extent. So
I think it's okay. Manpreet, fine. So due to paucity of time, I am requesting Manpreet to stop here, and we will, if organizers are okay, then we can invite Dr. Manoj. But he has now very less time. If we are having some more 5 minutes more beyond our schedule, then he will have 10 minutes time. So
yeah,
I request, can the session be extended by 5 minutes beyond the session timing?
We have no problem, sir. Actually, this is the last program in this hall, so that we have.
Okay. If there are no further hall requirement, then I think we can go ahead. So, Dr. Manoj, you please carry on your presentation. We are waiting. You are not audible, actually. No, not yet. No, not yet. Your video.
Your audio is not configured with Zoom. Please configure your audio.
Is it okay now?
Yeah, is it okay now? Yeah.
Okay. Thank you, sir.
Carry on.
Okay. I first of all thank the respected chairs for allowing me to present. And today I will be presenting on. I will share the screen right now. Is it okay?
Yeah.
Slide
Go ahead.
can be. Yes.
Go ahead. Yeah.
So the title is How is Deep Convection Favored in a Polluted Atmosphere? The scientific objective of the problem is to assess the relative role of combating aerosol-induced thermodynamic and microphysical effects in triggering deep convection over the Indo-Gangetic plane using observation and modeling. So the basic methodology is we make the composites of aerosol and cloud and meteorological parameters during the formation of a deep convective event under both light and heavy pollution conditions, and then contrasted the resulting parameters to elucidate the aerosol effects. We know that more number of aerosols in the atmosphere can lead to, especially those of absorbing aerosols, can trap a lot of heat in the lower atmosphere, which in turn will be reflected by the temperature in the temperature profile. So there will be an inversion resulting from the absorption of light energy, and this increase in the temperature will lead to a possible stabilization of the planetary boundary layer, which can suppress convection. This is the general notion, but we can see that sometimes deep convection do form under heavily polluted conditions. So under those conditions, what is the role of aerosols we wanted to examine. This is the basic methodology. You can see that this is during a relatively cleaner atmosphere where you can have a shallow convection and the CCL is much lower. But if you have an enhanced layer of absorbing aerosols in the boundary layer or just in the lower troposphere, then as a result of the enhanced warming, your temperature profiles become modified. And you can see that the CCL is lifted up. But concurrently, there is an increase in the convective available potential energy for driving the convection. So how is it happening under these both polluted and cleaner environment? This is the question under investigation. For this one, I selected certain at least 8 events, deep convective events along the Indo-Gangetic plains, that is Nainital, where we had a very complementary experimental facility for measuring various aerosol and cloud parameters in the vertical using aircraft and lidar, etc. So this is the region where observation happened, and we considered this box for studying deep convective events. You can see that the aerosol optical depth is very high over this region, and the cloud optical depth also concurrently goes up, and the cloud top pressure, you can see that this is also changing in accordance with the deep convective events, and there is an increase in the cloud optical ice and cloud effective radius, cloud ice path, cloud fraction. And you can see that most of these aerosols presented here in the form of AOD, they are mostly like absorbing aerosols. Even though there is a data missing, you can see that here they are mostly like absorbing aerosols. So this is the general pattern that we investigate. And now we categorize this deep convection into two categories. One is deep convection convective events, that is a DCC, under high aerosol loading, and a deep convection under low aerosol loading, and then contrast them to elucidate the effect. So as a preliminary step, you can see that as the aerosol optical depth increases, there is a concurrent increase in the cloud iso-optical depth also, because here why we have taken the iso-optical depth, because that represents the higher clouds, and this is colored with respect to the eyes effective radius. And this is the HADCC cases, that is higher aerosol or polluted case. This is cleaner case. You can see that lot of inversions. This is a temperature profiles. Lot of inversions, small and large scale, as high as 1.2 type degrees Celsius of inversions are taking place in the high aerosol cases. And you can see that those are in accordance with the theory that there may be increase in stability, but this stability is somehow overcome. What is the factor that is responsible for that? But we have seen the boundary layer height also we have seen during the HADCC and LADCC, and you can see that during this case there is more boundary layer height also increases, because as evident from the difference between HADCC and LADCC, you can see the boundary layer height is deepening, and there is a lot of evaporation. So how it is happening again? Then I calculated the moist static energy, because from today's first lecture we have seen that the moist static energy has a crucial role in controlling deep convection. And you can see that this is the CPT is the internal energy, GZ is the potential, and the LQ is the latent energy. I have examined this one, the latent energy and the internal energy, and you can see that this is for the internal energy first panel, this is for the latent energy, and this is the MSC total of all the three. Then you can see that under HADCC conditions, all are increasing as evident from the difference between these two. So we now know that during the deep convective event, there is a substantial increase in the moist static energy, which can drive convection right from the lower atmosphere. And if you can see the moisture convergence required for deep convective cloud formation, you calculate the moisture convergence flux based on this equation, and that the vertical profile of that moisture convergence also shows enhanced moisture convergence in the lower atmosphere, extending up to more than something like a 650 HPA. Then the cloud ice water content also increases. The vertical velocity also increases during the deep convective events, irrespective of or in spite of the high pollution event. So we can see that further to that one, the total cloud ice water content, the CAPE, the high cloud fraction, all are increasing in line with the HADCC cases. So but the problem is again how what's the physical mechanism responsible for that? The physical mechanism proposed is as a result of the enhanced absorbing aerosol concentration concentrated in the lower troposphere, there is enhanced warming. That enhanced warming can lead to low level moisture convergence. So as a result of this moisture convergence in the lower level, this can actually overpass or surpass the stability induced by aerosol direct forcing. So this is the mechanism, that is the moisture feedback is ultimately what determines whether there should be a low convection or high convection. And these absorbing aerosols, through their warming potential, increases the moisture moisture in the lower level. Now we have seen whether the aerosol microphysical process has any role, and we estimated the aerosol indirect effect using the equation given here. This is for the HADCC cases, and this is for the LADCC cases. Then also here also you can see that the weak atomic effect could actually suppress the warm air or warm cloud formation, so that once the warm clouds are suppressed, it will stay there in the atmosphere for longer time, and further they can be lifted up due to this moisture convergence to freezing level. So once they go to the freezing level, additional latent heat is released because of the latent heat release of freezing, and that can further help to develop this deep convection. Now, what we did, we run a model, WRF model with these specifications, and we prescribed the aerosol, observed aerosol concentration converted into CCN, and run the model. And this is the extension coefficient for HADCC in red, and in blue you can see that there is enhanced aerosol layer for these cases. And we made the experiment by reducing the observed aerosols concentration to 1/4 of what is actually observed, because in line with a certain literature we could do that, so that in the model we have a heavily polluted atmosphere and a clean atmosphere, or relatively less pollution, and we wanted to simulate what is the resulting thermodynamical parameters. And you can see that this shows the vertical profile of the potential temperature difference. That is basically the stability parameter, static stability. You can see that there is a difference between these two are actually negative, showing that enhanced stability during heavily polluted conditions. But as then here you can see that the average difference between the sensible heat flux also showing negative, in line with the theory, and the moist static energy also supports our observations. And if you see the vertical profile of the difference in moist static energy, you can see that in line with the observation, enhanced moist static energy is seen in the lower atmosphere. And you can see that the moisture convergence also increases in the lower atmosphere in model simulations. So the is the case with the latent energy and the heating rate, especially if you can see that there is a substantial heating, almost 1 to 1.5 degrees Celsius more in the HADCC cases compared to the LADCC cases. So all these simulations do support our observations. And finally, this is the slide. You can see that the enhanced rainfall, accumulated rainfall over the 24-hour period, if you can see that for the deep convective events, these absorbing aerosols are really responsible for enhanced rainfall in convective events. And from the study, we really confirm that although heavy loading of absorbing aerosols might stabilize the planetary boundary layer and weaken the convection, observational analysis highlight the seminal role played by aerosols in increasing the moist static energy, thus increasing the convection potential of the lower atmosphere. Thank you so much.
Thank you, Dr. Manoj. I don't know if any questions are there. Quick questions. One. If there are none, then thank you, Dr. Manoj. And I, on my own behalf and as a co-chair on Dr. Anand Das' behalf, I thank the organizers for giving us an opportunity to share the session. I hope we conducted in a good manner, but time, though 3 presenters were not there, still we have surpassed the time limit. I'm sorry for that. So that's all from my side. Anand, is anything you would like to say?
Yeah, sir. Thank you, Dr. Mahesh Kumar, co-chair. Sir, I am also thankful to organizer, and also we are very happy to listen all the speakers who are presented different topics and different kind of study. So this session was very good, sir, and certainly will be, sir, providing a short report on the session to the organizer.
Thank you, all the presenters also. Yeah.
We thank Dr. R.S. Mahesh Kumar and Dr. Anand Kumar Das for chairing this session. We thank all the speakers and delegates and those who watched the session online and offline. There is an announcement. Kindly join for the memorial lecture in honor of Professor Anna Mani by Dr. C.R. Sridharan in hall number 1, Pamba at 6:30 p.m. Thank you.
Thank you.